Since humanity first looked skyward, we have dreamed of taking to the air, skirting the laws of physics and pushing engineering science to ever greater heights. The power of flight ranks among humanity's greatest achievements. In this episode, we journey from the experimental breakthrough of the Wright brothers to the contemporary icon of commercial travel that is the Boeing 747. And from today's cutting edge of experimental flight, the lightning strike, to tomorrow's vision of interplanetary travel in SpaceX. This is the story of air power. Invisible, but far from intangible, air is the name given to the Earth's atmosphere. Itself a source of power, both devastating and helpful. Air provides resistance to travel. Each time we take to the sky, we are working with air and against it. October 25, 2007. This was the first commercial flight of the largest passenger plane in the world, the Airbus A380.
It's no different to any other aeroplane, whether tiny, medium-sized, large or huge. The aerodynamic principles are exactly the same. But of course it's rather more interesting watching something that big fly.
Nicknamed Super Jumbo, this enormous craft measures 73 metres long, with a tail fin standing at the same height as a 10-storey building. Such is the scale of this craft that 530 kilometres of wiring runs it. Weighing a massive 580 tonnes, the A380's paint job alone tips the scales at around 650 kilograms. With a plane this huge, one question looms large. Just how does it get airborne?
To achieve that, you need a very aerodynamically efficient aircraft. So you need very large, very efficient engines combined with very aerodynamic design and very efficient and very large wings to generate the lift to keep the aircraft in the air.
Powered by 4 turbofan engines, the unique aspect of the A380's flight is the aerodynamic design of its wings. A design that began as a compromise. The optimal wingspan is 90 metres, well outside airport restrictions.
So had they built it with a straight wing, it would have become too large for basically all the airports in the world. So it would not have been allowed to start or land anywhere just because of its size.
Scaling its wings back to 80 metres, the A380 added unique wingtip fences to maintain an extended aspect ratio without extending length. These distinctive wing fences also serve to reduce the potential hazard of this huge and hugely powerful craft.
When you have an aircraft, the flow around the wing creates something that is known as the wingtip vortex. So the bigger the wing, the bigger these vortices.
An aeroplane's wing generates lift by creating pressure changes in the air. As the wing passes through the air, air moves quickly over the top and slower underneath, resulting in the upward force of lift. A byproduct of this is wake turbulence. With the high and low pressure air left swirling behind the wing to effectively form a horizontal tornado.
These vortices present two primary problems. One, the most important, is that they significantly degrade the efficiency of the wing, its ability to generate lift without generating drag. The other is that they actually present a safety issue for aircraft following behind.
The extended wing fences of the A380 serve to distribute the wake turbulence and drive it upward rather than down. Not a bad result for a wing design that started out as a compromise. with little else by way of compromise, to understand how so many of us can so easily and so comfortably take to the sky, we must look back to more humble beginnings. A little over 100 years ago, in this inauspicious North Carolina field, a truly auspicious event in aviation occurred. It was here, in December 1903, piloting a craft of wood, fabric and wire, that Orville and Wilbur Wright became aeronautical legends. Covering a distance less than the wingspan of a modern 747, this was the first time in history that a powered, heavier-than-air aircraft achieved sustained flight. While the Wright brothers were not the first to pilot experimental aircraft, their fundamental breakthrough was in controlling that flight. It was the Wright brothers' work selling and repairing bicycles which convinced them that a flying machine could be steered and balanced with practice. With the right controls, the Wright brothers believed that learning to fly was like learning to ride a bike. So while their contemporary aviation research focused on building more powerful engines, the Wright brothers worked on steering. And it was the invention of their three-axis control system which was the game changer. This ingenious design, which today remains standard in all fixed-wing aircraft, allows the pilot to steer and maintain equilibrium.
The fixed-wing design was very successful, and from that point onwards, fixed-wing aircraft became the dominant form of aviation.
By the early years of the 20th century, powered flight had become an established technology. The potential of aeronautics for combat, sport, exploration or travel was increasingly recognised around the world, and a period of rapid development was ushered in. A period where the true power was in human bravery. Perhaps no one better exemplifies the pioneering spirit of aviation's golden age than this man, Charles Lindbergh. Known as Lucky Lindy, this former US airmail pilot shot from obscurity to world fame in the course of a single flight. Piloting a purpose-built monoplane, the Spirit of St. Louis, Lindbergh's 5,800-kilometre journey from New York to Paris was simultaneously the first solo transatlantic flight and the first non-stop flight from North America to mainland Europe. Short on funds but high on self-belief, Lindbergh piloted his single-engine craft for a grueling 33.5 hours. Battling storms and navigating by the stars to land in Paris as a hero on May 21, 1927.
Everyone wanted to meet this daring young man. Even as he posed for these films with members of France's distinguished Aero Club, the entire world was clamoring for its brand new hero.
A feat of both human and mechanical endurance, the achievement brought new public interest to aviation, sparking what was known as the Lindbergh boom. A period in which airmail volume increased by 50% and pilot license applications tripled. For all the bravery and sacrifice of aviation's golden age, the limits of the piston engines that powered these flights were well known.
So after the Second World War, we really saw the rise of the gas turbine, the jet engine as a technology.
Invented years earlier by Frank Whittle for the Royal Air Force in 1921, the jet engine works by firing gas backward in order to thrust aircraft forward. A breakthrough almost as revolutionary as the Wright brothers' first flight.
The attraction of the gas turbine is that you could get even more power out of a given size and a given weight.
Breathing in air through a gas-fired turbine, the jet engine compresses this air through a series of high-speed rotor blades. Forced into a combustion chamber, the compressed air is then sprayed with fuel and ignited. With the expanded gases forced out through the propelling nozzle at the back, the aircraft is thrust forward at high speed. Though still in its infancy, by the end of the Second World War, the turbojet represented the next great leap in aviation. During the war, high-altitude, high-speed bombers were in high demand, leading the English Electric Company to develop designs for just such a plane, the Canberra.
The Canberra is a high-altitude light bomber with great striking power and a speed believed to be over 600.
Featuring an elegant, streamlined design, the Canberra is more notable for the fact that it was the Royal Air Force's first bomber to utilise the power of the newly developed turbojet engine. Coming into service after the war in 1951, the Canberra set a new world record as it flew from Northern Ireland to Canada, becoming the first jet aircraft to make a non-stop transatlantic flight.
As for the trip, that smashed all records as we know. 4 hours, 40 minutes from Aldergrove to Gander, Newfoundland.
Throughout the 50s, Canberras flew higher not only than other bombers, but than any other aircraft at the time. Repeatedly setting world altitude records, the highest a Canberra flew was in its third record-breaking flight, reaching 21,430 metres in 1957. The power of the turbojet combined with its clean design made the Canberra a remarkably versatile aircraft, filling a variety of roles from tactical bombing to photo reconnaissance. Although retired from more than 50 years of military service, Canberras remain in the air today, performing meteorological research and ground mapping work. With peaceful skies, the established power of the turbojet and a surplus of heavy bomber airframes ready for conversion to passenger transport, the end of the Second World War also marked a turning point for civil aviation.
Probably the most rapid period of development in aerospace, certainly in aviation, was that following the Second World War.
One of the first to forge ahead in this new and exciting space was the Vickers Viscount. Employing the gas turbine engine to power propeller blades, the Viscount brought the turboprop aeroplane to the public. But it was the de Havilland Comet that truly burst onto the scene, claiming the glory of being the world's first jet airliner. Manufactured in the United Kingdom, the Comet featured a sleek modern design with 4 turbojet engines buried in the wings, large square windows and a pressured cabin, allowing for comfortable and efficient flying at high altitude. But these commercial pioneers were doomed by a fatal design flaw. If passengers are to breathe while flying at high altitude, a plane's cabin must be pressurized against the low air pressure outside. Increasing cabin pressure while ascending and decreasing it while descending places the structure of the plane under tremendous stress as it expands and contracts with each takeoff and landing. This is what led to the Comet's downfall. A series of tragic and highly publicised accidents saw several of the planes burst apart in mid-flight, resulting in dozens of deaths.
This is the tragic scene of the Comet disaster near Calcutta. Wreckage of the aircraft smashed almost beyond recognition.
After extensive testing, a structural weakness was finally identified around the Comet's square window frames. Suffering metal fatigue after repeated pressurization cycles, the Comets effectively became ticking time bombs, unable to contain cabin pressure at altitude. Despite undergoing a period of extensive redesign, which saw the craft rebuilt with oval windows and reinforced structures, the airline's reputation never recovered. But the quest to conquer commercial airspace did not end, and heeding the lessons from the Comet's design failing, rival manufacturers developed new and improved airliners in quick succession. In the 60s, Douglas Aircraft was the more established manufacturer, and its DC-8, the first commercial transport of any kind to break the sound barrier, took a commanding share of the market. One plane went on to change all that. With its wide body and distinctively humped upper deck, this is one of the most recognisable planes in the air. It is the original jumbo jet, the Boeing 747.
Well, that was a name that was conjured up by the popular press, not by Boeing. There's still people in Boeing who don't like it being called the jumbo jet. It rolls off the tongue, doesn't it? Jumbo equals big, jet, and it's stuck.
Entering service in 1970, the 747 surpassed the DC-8 to take control of the commercial air market by offering vast improvements in performance and comfort.
It revolutionised airline travel, there is no doubt about that. It was able to carry 2.5 times as many passengers as the Boeing 707 and the Douglas DC-8, which were the standard international airliners of the time, which meant that the seat mile costs were lower.
The engine technology was moving from what we call low bypass turbofan technology to this brand new idea of high bypass turbofan technology, which is really the basis of all modern transport engines.
With air entering the turbojet through a fan, the bypass ratio is the amount of air that bypasses around the engine versus the air directed to the engine's core for combustion. All air passing through the initial fan has increased velocity, allowing turbojets to take some thrust from the core and some from the fan. So while combat aircraft use a low bypass ratio, burning more fuel for maximum power, commercial jet engines make use of a high bypass ratio for increased fuel efficiency.
Air travel was still the domain of the richer part of society. But as aircraft size grew, what that meant was that you could bring the cost for the individual traveller down.
There's millions of people who could not previously afford to fly internationally suddenly could. And that was the revolutionary part of the 747. It brought in the current era of mass air travel.
Thanks to the advances in civil aviation, this is what modern air travel looks like today. Often taken for granted, it is the ground-level infrastructure that has enabled the omnipresent reach of air travel. But for all the advances in air power, the forces of nature can still bring us back to Earth. Volcanic eruptions are some of the most awesome natural forces on the planet. Firing clouds of ash high into the air, these particles can enter and potentially stall aircraft engines, creating no-fly zones spanning tens of thousands of square kilometres.
The single biggest improvement in aviation safety was the move from piston engines to gas turbines, because gas turbines are inherently more reliable. The problem is they're designed to ingest air. They're not really designed to ingest particles.
Volcanic ash clouds may be a rare inconvenience for planes, but for helicopters, the risks posed by dust particles are faced every time they take off or land on sandy surfaces. Beyond limiting visibility, sand stirred up by helicopter rotor blades is breathed in by the air intake of the engine.
So while it's not necessarily the belief that a single flight through the dust will result in catastrophic failure of the engine, we're certainly extremely worried that multiple flights will degrade the performance of those engines.
With helicopter engines running at high speeds and high temperatures, once inside, sand particles are sped up and superheated. Captured at 4,000 frames per second, this footage shows the high-speed sand particles slamming against and melting onto the internal engine hardware. The result is an underperforming, unreliable engine deteriorating at approximately 10 times the normal rate, a real risk to the lives of those on board. The solution may look something like this. currently experimenting with the durable, heat-resistant properties of ceramics. Military scientists are hopeful of developing an engine coating that can withstand the ravages of sand. Finding the right chemistry is a process of elimination, but initial results are encouraging, powering helicopters, indeed all aircraft, to operate in an even wider range of conditions. Of course, it wasn't so long ago that the challenge was operating a helicopter under any kind of conditions at all. Unveiled in Nazi Germany in 1936, this is the craft that proved the viability of the helicopter, the Focke-Wulf FW-61. While not the first to achieve rotary flight, the FW-61 easily outperformed contemporary rivals to establish itself as the first truly practical helicopter, providing the basic design that future helicopters went on to develop. Bearing the name of its principal designer, Professor Henrik Focke, the Focke-Wulf took the fuselage of a light aircraft and replaced the wings with steel outriggers in order to mount three-bladed rotors on either side. These large rotors spun in opposite directions, providing stability. And while the forward propellers on the engine gave the FW-61 the look of an autogyro, their shortened blades did not provide power for forward flight, instead cooling the 160 horsepower engine. And this is where Focke's chief innovation lies. Taking the gas turbine engine that revolutionized aeroplanes, Focke converted it so that instead of producing jet thrust, the engine powered a spinning shaft which in turn spun the rotors. This is turbo-shaft propulsion, and it is the system still used by the majority of helicopters today. So impressed was the Nazi government with the FW-61 that it became part of their propaganda campaign during the war. Placing Germany's famed female pilot Hannah Reitsch at the helm, the helicopter was flown for nightly shows in front of large crowds. Such indoor displays could easily have ended in disaster, but thanks to the FW-61's robust control system, Reitsch, with less than 3 hours practice, successfully flew the craft night after night without incident. Following the war, the most significant advances in helicopter technology took place not in Europe, but in the United States. And there is one man who deservedly takes much of the credit for this: Igor Sikorsky. Born in Russia, Sikorsky was already an established aircraft engineer and pilot when he migrated to the US in 1919. Founding the Sikorsky Aircraft Corporation, he established himself in America as a leading innovator in aviation. And it was this craft, first flown in 1940, which cemented his reputation: the Vought Sikorsky VS-300. Here, the famed innovation concerns a long-standing, or rather long-spinning problem with helicopters: how to stop them spiraling out of control.
And of course, the big problem is that if I have a rotor spinning in the air, then I need to stop the aircraft spinning in the opposite direction.
Newton's third law states that every force has an equal and opposite reaction. And in spinning rotor blades to fly, a helicopter's body tends to spin in the opposite direction. This spinning force, called torque, must be counteracted in order to achieve stability in the air.
And then we need to use things like tail rotors or have more than one rotor to provide that anti-torque to stop the aircraft spinning. And that adds extra weight, complexity, and more points of failure. So these problems have hounded aeronautical engineers for many decades.
Enter the VS-300. With just a single set of lifting rotor blades and a single main gearbox, anti-torque is achieved through a vertical tail rotor. Power is traded off here, with the tail rotor counteracting the main lifting rotors in the name of stability. But the simplicity of its design made the VS-300 worth the compromise. And it's hard to argue with success, with the tail rotor blade configuration pioneered by the VS-300 still seen on most helicopters today. And Of the helicopters today, there is one that casts a long shadow over all others. The Boeing AH-64 Apache. Heavily armed and heavily armoured, the Apache has been compared to a flying tank. Equipped with radar jammer, bulletproof glass, sophisticated sensor equipment, laser-guided targeting, chain guns, and the aptly named Hellfire missiles, the Apache is tricky to detect, difficult to damage, and near impossible to hide from. And to its targets, utterly devastating. But here is where the flying tank comparison falls short. The Apache is also incredibly agile. Modifying the tail rotor blade configuration pioneered by Igor Sikorsky, the Apache employs dual tail rotors, each with 2 blades. More than providing anti-torque force, this setup in combination with a digital stabilization system is optimized to provide remarkable maneuverability, a handy trick when evading enemy fire. A deadly combination of strength, firepower, and agility, the Apache has ruled the skies since it began service in the 1980s, with over 1 million combat flight hours to prove it. But today, a new breed of combat helicopter is rising. This is the Sikorsky S-97 Raider, a compound helicopter designed to provide the one thing conventional helicopters lack: speed.
The limitation of most helicopters is they can't fly very fast, because as the aircraft flies faster and faster, one of those blades is going so slow that the air over it stalls and it no longer produces lift.
On the battlefield, speed is power. And the Raider is built to get into the fight fast and get out even faster. It does this in 2 ways. The first is a coaxial design, essentially stacking 2 counter-spinning rotors on top of each other to eliminate torque without diverting power from their lift and thrust capabilities. Eliminating the need for a stabilizing tail rotor, the Raider is free to bring in its second addition, a pusher propeller out the back to provide even more forward thrust.
There's always been this problem of trying to go faster in a helicopter. We reach a speed of about 200 knots and we can't fly any faster. So these compound helicopters use wings or extra propulsion systems to put less load on the rotor, and by doing that they can actually get faster.
The Raider offers more than pure speed. It aims to revolutionize all aspects of helicopter performance with increased range, altitude, and payload performance. From assault missions to search and rescue, the Raider is customizable to suit a variety of roles as the next generation of military helicopter. With varying degrees of sophistication, helicopters of all sorts have long boasted a particular advantage over planes: the ability to take off and land without a runway. This inevitably raised the question, could a plane do the same thing? Needing a runway is a particular problem for combat aircraft. Air bases represent large, valuable infrastructure, difficult to protect from enemy attack. The need for fighter jets that could operate from improvised bases close to enemy lines was clear, and this was the solution. The Harrier, better known by its informal name, the jump jet. Continuing development throughout its lifetime, the first jump jet emerged in the 1960s as a rare success story in the quest for vertical takeoff and landing capabilities. So how did the jump jet succeed where so many others failed?
They had 2 pairs of nozzles, and so in combination, the Harrier could generate thrust at different angles to either short takeoff, manoeuvring in the air, or vertical landing.
Once airborne, the nozzles revolve to push the plane forward. Simple in theory, difficult in practice. Such maneuvers demand tremendous skill on the part of the pilot and tremendous power on the part of the plane. Capable of hovering for just 90 seconds, in this time the plane uses over 500 litres of water to cool the engine. Vertical takeoff is not possible when the plane carries its full loaded weight, so in most cases, a short takeoff is employed. Shortening the runway, ramps are often used to allow the plane to jump into the air, hence the name. In addition to the limitations of their vertical takeoff, jump jets were only capable of subsonic flight.
By going to that large high bypass engine, you are restricting the ability to make the aircraft aerodynamically efficient for supersonic flight.
Nonetheless, the Harrier jump jet was for many years the only plane capable of vertical takeoff and proved its worth in combat.
There was a desire to develop a follow-on to the Harrier that could have all the attributes of the Harrier, of short takeoff and vertical landing, but also be able to fly supersonically. We now see a successful solution, and that successful solution is the F-35 Lightning II, developed by Lockheed Martin.
Today, while the jump jet has retired from active service, its legacy remains as the first aircraft to successfully combine the best aspects of helicopters with planes. At DARPA, the Defense Advanced Research Projects Agency, the search continues for the ultimate aircraft that can do it all. And DARPA is not afraid to think outside the box. This unconventional creation may represent the future of vertical lifting technology. Named Lightning Strike, the unmanned craft has entered into experimental testing. With a hybrid electric system powering its array of 24 thrusters, the Lightning Strike is seeking to set a new benchmark, taking off and hovering efficiently and going faster than any rotorcraft before it. The power of flight takes many forms, and in the 1960s, an ancient technology was reinvented, taking us to new speeds and new heights. It was this technology, 700 years after it was first discovered, that ultimately launched us into the space age. The rocket. Dating back to at least 13th century China, rockets operate on the simple principle of action and reaction. With the majority of their weight consisting of fuel, rockets burn this fuel in order to expel high-speed exhaust, thrusting them in the opposite direction. Simple, but effective. Long used in fireworks and artillery, it was the introduction of liquid fuel instead of gunpowder that brought rocketry into aviation. Compared with air-breathing engines, rockets offer a lightweight source of tremendous power. And it was rocket power that took us faster and further than ever before. This is what the marriage between rocket and plane looks like. The North American X-15. Operated by NASA and the US Air Force from the late 50s to the early 60s, the X-15 was the most successful of the X-planes. A series of experimental aircraft built to test new aviation technologies.
It's essentially a rocket that flew only for about 2 minutes every time, so it had just only fuel enough for that.
And so the X-15 had two primary missions. One of them was to fly as fast as it could through the atmosphere, and that was to look at thermal structural design. The other was to fly as high as it could to the very edge of the atmosphere where you could no longer use traditional control systems.
Almost half a century since it was last in the air, the X-15 remains the fastest manned plane ever flown. With an unofficial top speed of 7,274 kilometers per hour.
That could go up to more than 6 times the speed of sound, so Mach 6. And that holds the record of the fastest atmospheric vehicle that was ever built and flown.
Just how did the X-15 power such astonishing speeds? With this, the XLR-99 rocket engine. This was the world's first large rocket engine capable of increasing and decreasing its power, as well as stalling and restarting. The XLR-99 also provided a frightening amount of power, burning a propellant mixture of oxygen and ammonia to produce a staggering 250 kilotons of force.
It was really a multi-stage system because it was not able by itself to take off from a runway. Instead, it was hung under the wing of a B-52 bomber, and so that B-52 bomber became the first stage. And so that carried it to altitude, and that meant that it already had a head start when it was launched. And then once clear of the B-52, it would light its rocket engines. So it had onboard fuel that it would burn for a very short period, but that was enough to accelerate it all the way up to Mach 6.7. So that's almost 7 times the speed of sound, which is 3 or 4 times faster than a fighter jet, a supersonic fighter jet.
The test flights of the X-15 made history, not only setting a speed record that remains unbroken today, but an altitude record that went unrivaled for 40 years. Of course, the goal of these flights was about more than setting records. It was about research. Over the 199 flights the X-15 undertook, data was collected across all areas of aviation, testing everything from heat shielding and hypersonic flight to the physiological stress on pilots. Considered the most successful flight research program in history, the data gained through the X-15 proved invaluable for the next great frontier of aviation. The quest to fly beyond the atmosphere of the Earth into outer space is a dream as old as humanity. This dream came to a head in the space race of the 1960s.
It was actually the Cold War and the effort to beat the Soviet Union into space and the government funding and the defense backing that really resulted in all the achievements in space.
The Soviets took the lead early, launching the world's first satellite in 1957, and 4 years later, successfully placing cosmonaut Yuri Gagarin into orbit, making him the first man in outer space. But the ultimate objective remained, as outlined by President Kennedy.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
This ambitious goal was tasked to NASA's Apollo program, which began in 1961. And 8 years later, on Apollo's 11th mission, it was 2 men, Neil Armstrong and Buzz Aldrin, who achieved that goal. And what powered the Apollo 11 on its voyage to the moon? Rockets. Really big ones. The Saturn V was the rocket that shot the Apollo 11 into history. Almost 40 years later, it remains the tallest, heaviest, and most powerful rocket ever built. Operating on a 3-stage system, the first and most dangerous stage was simply getting this giant into the air. Packed with 770,000 litres of kerosene and over 1 million litres of liquid oxygen for combustion, the first stage rocket ignites and, with thrust confirmed, is released from the launch tower.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Burning for 2.5 minutes and carrying the vessel to an altitude of over 60 kilometres, the first stage shuts down and separates, falling back to Earth, where it will be burnt up by the atmosphere. Switching to a mixture of liquid hydrogen and oxygen, the second stage rocket propels the spacecraft into the Earth's orbit before being jettisoned. Expelling exhaust to transfer momentum, once in the vacuum of space, rockets are able to work at maximum efficiency, and it is from here that the Saturn V's remaining rocket engine propels the craft towards the moon, with the lunar module making history by touching down on the surface of the moon. Getting to the moon is one thing, getting back safely is another, with the most dangerous part of any space mission being re-entry into Earth's atmosphere.
Anything that comes from outer space typically travels with tremendous speeds, speeds of several kilometers per second.
Travelling through the vacuum of space, there is nothing to slow movement down. But when fast-moving objects, like meteors or Apollo command modules, encounter an atmosphere, the atmospheric gases in front of them are compressed extremely rapidly, causing them to heat up.
They have a several kilometers per second speed by the time they get into the atmosphere. If they were to crash with that speed onto the surface, that would be a major explosion and certainly very unpleasant for all involved.
The Apollo command module has a blunt body design, intended to create high drag and push against as much air as possible.
You have to slow down, and the best way to do this is to convert the kinetic energy, the speed, into heat. And you do this by generating a massive shockwave, because that's exactly what a shockwave does. A shockwave slows the flow down and converts the kinetic energy into temperature.
The shockwave around the Apollo module kept the flaming atmospheric gases from coming into direct contact with the vehicle. Nonetheless, the command module got hot, with its surface reaching temperatures of over 2,700 degrees. Coated with an ablative heat shield designed to melt away, it appeared from below that the command module had caught fire, when in fact it was functioning perfectly. With the shield eroding away from the vehicle, it diverted heat, keeping the history-making occupants safe for their eventual splashdown into the Pacific Ocean. Spurring the desire for further research and exploration of space, the Apollo missions highlighted the need for a more sustainable spacecraft, one that could make multiple trips to and from space. This was NASA's solution.
The Space Shuttle system, an amazing vehicle, probably one of the most amazing machines ever built, one of the most complex machines ever built. One of its prime aims was to bring the cost of space access down.
These were the vehicles that helped build the International Space Station and conduct cutting-edge space research. They remain the only manned space vehicles to have made multiple flights into orbit.
The Space Shuttle partially achieved reusability. So the orbiter is the only part that goes into orbit and then comes back. There were also some more traditional, large, solid-fueled booster rockets strapped to the side of the stack. Once they had expended all of their solid fuel, they would be released from the stack as it continued towards orbit, and they would fall back towards the Atlantic Ocean. The shuttle continued towards orbit, still attached to its external tank, and so when that tank was empty, when it had expended that fuel, that tank would be released and that would fall back through the atmosphere. And so it would actually burn up during its descent, and so that was not recovered.
Once in orbit, the shuttles provided the crew with everything they needed to live and work in space. And as with the Apollo program, returning to Earth was the most dangerous part of the mission.
The crews that flew the space shuttle were coming through the atmosphere at about 23 to 24 times the speed of sound during their initial re-entry. They were entering 7 to 8 kilometers per second. And so we would probably say that to date, that's the fastest manned winged aircraft.
The angle of re-entry is crucial, with the slightest error causing the craft to break up or skip off the Earth's atmosphere like a stone over a pond. After gaining re-entry, the challenges continue. Now without power, the shuttle must rely on pure aerodynamics to land. Generating lift with its small, swept-back wings, the shuttle slows its descent in a series of S-shaped banking turns before gliding onto the runway for touchdown. The Space Shuttle program was not without tragedy, but the desire for space exploration has not abated. With unmanned satellite and probe technology continuing as a safe and reliable means of space research, the challenge for these crafts is in harnessing an efficient form of power in the vacuum of space. This is the answer: the plasma thruster.
So if you've got a satellite in orbit and it's got a mission life of 2 years, 5 years, 10 years, you need the fuel that you put in that satellite at launch to last that long. Now, with chemical thrusters, you would not be able to make it last that long, but with a plasma thruster, you can because it's highly efficient.
We're using plasma to generate thrust on a spacecraft. And we do that by converting electrical energy, which you can store very efficiently on a spacecraft, into kinetic energy.
While they may look like the stuff of science fiction, plasma thrusters are actually an incredibly simple and well-established form of propulsion in space. One with the promise of powering space exploration into the future.
Once you're in space and there's no friction and there's no gravity to counteract your movement, you can use these plasma thrusters, which are incredibly efficient, to go to Mars, go outside of the solar system, anything you want to do.
Today, the space race remains as competitive as it ever was. The only difference is that the race is no longer between countries, but companies.
When I was a kid, I read a lot of science fiction, and a lot of the science fiction that had been written envisaged that it would be, the American dream was that private companies, rich individuals, would actually lead the journey into space. Because, that's how America saw itself, as the home of the entrepreneur. Fortunately, in parallel to this thinking, of course, was that we had a number of very successful, very rich individuals who had grown up with the dream of spaceflight that had been inspired by what NASA had done.
With shared goals of commercializing space travel and even colonizing other planets, 3 companies have emerged as leaders in the modern space race. Under founder Richard Branson, Virgin Galactic is seeking to become the space line for Earth. Blue Origin, set up by Amazon founder Jeff Bezos, has even loftier ambitions, with Bezos describing his ultimate goal as having millions of people living and working in space. Also working on big rockets, SpaceX is seeking to reduce the cost of space travel and harbours hopes of colonizing Mars. Such goals could be dismissed as science fiction, but with billionaire tech entrepreneur Elon Musk as CEO, SpaceX is already breaking records and setting new standards for space transport. Through experiments with reusable launch system technology, SpaceX has refined propulsive landings to the point where in 2017, it became the first to successfully relaunch and land the first stage of an orbital rocket. In their race to revolutionize space technology, these companies have set their sights on more than that. This is the forefront of aviation's next great leap. Daring to dream big, the corporate space race is drawing on the funds of its eccentric billionaire backers, but also on the power of the human spirit and its drive to explore and discover new worlds. From the first powered flight to the first lunar landing, the astonishing and rapid progression of aeronautic science has changed the world many times over. Proof that with the power of mastering the air, not even the sky is the limit. Since man first lifted off the ground, the quest for air power has been ceaseless. It is a quest fueled by relentless innovation, brave pioneering, and creative experimentation. Not without failure and tragedy, the desire for mastery of the air has carried us ever forward and ever faster. In this episode, we soar from the experimental Bell X-1 that first proved the possibility of supersonic flight to the modern jets like the F-22 Raptor that weaponized it. And from some of the largest craft ever to have taken to the sky to the miniature insect-inspired drones set to redefine the nature of combat. This is the story of air power. The world's most advanced multi-role jet fighter. This is Lockheed Martin's F-35 Lightning II. With three variants, the F-35A is the conventional takeoff and landing model, built for traditional Air Force bases. The F-35B is the world's first supersonic jet capable of short takeoffs and vertical landings.
Rather than having swiveling nozzles that take the flow through the engine and vector it downwards, what it does is it uses a completely separate lift fan that is positioned horizontally behind the pilot and in front of the single main engine.
The F-35C specialises in operating from aircraft carriers, utilising catapult-assisted takeoffs and barrier-arrested recoveries. All three variants of the Lightning are fast and highly manoeuvrable. With its array of weapon configurations changing to suit the mission, the F-35 is surprising proof that it's what's on the inside that really counts. Gaining the edge in combat, less through armament and more through information. Information is power, and the F-35 is essentially a flying supercomputer.
One of the key differences with F-35 and fifth generation platforms is rather than having a head-up display system, they actually project the imagery onto the helmet that you're wearing. So you're immersed in sensory information about what the aircraft's doing at the time.
An increase in situational awareness equates to an increase in pilot responsiveness, providing an advantage that can be the difference between life or death in combat. Prior to the integration of computers and the internet with military jets, the quest for superiority in the sky came down to one crucial component: speed.
The military always wants faster, and we generally want speed. If you can go faster, you can get to where you need to be quicker, or you can run away from danger quicker.
Speed, for many years, was pursued as the ultimate weapon in the sky. But one barrier stood in the way: the sound barrier. This is the craft that sought to break that barrier. Nicknamed a bullet with wings, the rocket-powered Bell X-1 was in fact modelled on a Browning .50 caliber machine gun bullet, known to be stable in supersonic flight.
The first proper picture of an object going faster than the speed of sound was taken in 1888 by Ernst Mach, after whom the Mach number later was named.
Questions loomed as to whether a plane could achieve the same speeds and whether a pilot could survive them.
Hoisted into the modified bomb bay of a superfortress, the Air Force's supersonic XS-1 rocket plane is set for an assault on the sonic barrier at Muroc, California.
Chuck Yeager was selected to pilot this potentially deadly experiment, a role he was so determined to have that he kept secret the 2 broken ribs he'd sustained in a horse riding accident just days prior to the flight. In such pain, he was unable to seal the X-1's hatch by himself. Jaeger nonetheless took to the sky on October 14, 1947.
This was a rocket-powered aircraft designed pretty much along the same lines as people had designed it in the 1940s. Straight wings, which you don't see these days anymore.
Drop launched through the modified bomb bay of a B-29 Superfortress, Jaeger and the X-1, which he'd named Glorious Glennis for his wife, had only a short window before the high-powered rocket engine used up its fast-burning fuel.
Captain Charles Jaeger climbs down into the cockpit of the rocket craft. The release mechanism is tripped, and Uncle Sam's ace in the sky drops clear.
Quickly ascending to over 13,500 meters, Jaeger chased down history, accelerating to the sound barrier breaking speed of 1,100 kilometers per hour. Because sound travels through the air in waves, if an object, such as the X-1, is fast enough, it can catch up to and overtake these waves. As the X-1 closes in on the velocity of its sound waves, these waves begin to pile up in front of it, creating a barrier of sound. The resulting change in pressure as the jet bursts through and overtakes its own sound waves is heard as a sonic boom.
It simply means that if something is flying supersonically, the air will only be changed or will only realize this when this object reaches them. If it's flying subsonically, the air already knows that the object is coming even before it has reached them.
Jaeger's monumental flight was kept top secret until 1948, but once the story was leaked, he became and remained one of the most famous test pilots of all time. Continuing to set speed and altitude records throughout his career, in 2012, Chuck Jaeger recreated the X-1's historic flight to mark its 65th anniversary, again going supersonic at 89 years old. The success of the experimental X-1 supercharged the military's need for speed, and soon, rockets weren't the only things going supersonic. A figurative and literal black project from Lockheed's highly secretive Skunk Works division, this plane set the world record for the fastest air-breathing aircraft in 1976 and has held it ever since. The SR-71 Blackbird. Designed for stealthy reconnaissance missions over foreign countries, if the Blackbird ever found itself in trouble, the plan was to simply outrun the threat using its supersonic afterburners. An afterburner injects fuel into the engine exhaust to burn the remaining oxygen in the exhaust stream.
The expansion of the gas through the nozzle accelerates the fuel out the back, and Newton's law says there's an equal and opposite force that pushes the aircraft forwards.
For most fighter jets, the afterburner gives added power for short bursts of 3 to 5 minutes. For the Blackbird, its engines were designed to run continuously in afterburner for hours, only slowing for mid-air refueling. But high speeds come with a cost.
At full speed, it takes something like 100 nautical miles to turn around because its aerodynamic lift, or your ability to actually turn, is so restricted at the very high speeds.
The Blackbird was engineered to withstand the stresses of sustained supersonic flight, the main one being heat. For the Blackbird, surface temperatures could reach over 480 degrees Celsius.
When you fly very fast, the friction between the flow over the vehicle and the structure of the vehicle produces heat through friction. And this heats the vehicle up, and that challenges the structural design. Things start to distort, to fail when they get hot.
Constructed largely from titanium to provide durability at high temperatures, in order to accommodate the metal expanding as it warmed up, gaps were left between the body panels, meaning fuel would leak when the Blackbird was on the runway. It was only when airborne and warmed by friction that the metal would expand and the gaps would seal. Gathering mission-critical intelligence during the Cold War for the 25 years the Blackbird was in service, over 4,000 missiles were fired at it. Thanks to its superior speed, not a single one hit it. Speed is useful in avoiding a fight. It is also useful if you're looking to pick one. And if you throw range, maneuverability, stealth and weapons into the mix, you get a craft you do not want to mess with. You get the Lockheed F-22 Raptor. Considered the world's strongest combat aircraft, while much of the Raptor's capabilities remain classified, it's no secret that it has speed to burn. The F-22 is the first American fighter jet capable of achieving supersonic speeds without the use of fuel-guzzling afterburners. Known as supercruising, the Raptor achieves this through a highly aerodynamic design and a highly powerful set of Pratt & Whitney F-119 engines. Producing more thrust than any other fighter engine, the F-119s allow the Raptor to fly faster for longer and with less fuel. In carrying less fuel, the Raptor can carry more weapons. And by deploying these weapons while supercruising at high altitude, the Raptor provides its munitions with a helpful boost, increasing their range by about 50%. Beyond its supercruising abilities, the Raptor is also super maneuverable. Using a thrust vectoring system to direct its engine's exhaust up or down, the Raptor can pull off high-speed maneuvers that are the envy of its enemies. But it was a lack of enemies that ultimately defeated the Raptor. With a hefty price tag and a period of relative peace, the Raptor program was cancelled in 2009, with less than 200 ever produced. The military were not the only industry to see the potential of supersonic flight. And commercial airliners raced to develop a passenger plane that could match fighter jet speeds. While the Concorde may be first to mind, this is the plane that won the race, the Soviet-built Tupolev Tu-144. Codenamed Charger, the Tu-144 first flew on New Year's Eve of 1968, beating its Anglo-French rival by 2 months to claim honours as the first commercial supersonic plane ever flown. Jokingly labelled the Concordski by its European competitors, the design of the Soviet-built craft did bear a striking resemblance to that of the Concorde.
Engineering problems tend to drive you to similar solutions. And so the Russian aircraft was similar in many ways. It potentially had more engineering issues though.
Both the Concorde and the Tu-144 feature distinctive hinged noses, dropping downward during takeoff and landing so that the pilots could see in front of the high-angled plane. And while both planes employed a delta wing design, never since used on commercial aircraft, the Charger had a unique added feature, its retractable forewings. With its delta wings offering limited lift at low speeds, the Charger's forewings, or mustache canard as it was known, was used to boost the plane's lift during takeoff and improve handling during landing. While the Tu-144 was first in the air, and the first commercial transport to exceed Mach 2, at the Paris Air Show in 1973, disaster struck. The high-profile fatal crash delayed production of the Charger for years.
Even though it did see commercial operation within the Soviet Union, it never came close to the success of the Concorde.
Speed has always been the big selling point of a civil airliner. It's universally agreed that the next step should be supersonic flight.
The product of a successful English-French partnership. This is the iconic craft that truly took supersonic travel to the masses. The Concorde.
An amazing machine that really has yet to be surpassed in its success as one of only 2 supersonic transport aircraft.
With its first commercial flight in 1976, the Concorde made the technological feat of supersonic travel an everyday reality. Across its quintessential route between London and New York, while a subsonic carrier might take around 8 hours, the Concorde did it in 3.5. Travelling beyond the sound barrier, the Concorde was subjected to tremendous pressure. Due to the intense heat of such high speeds, the Concorde's frame was designed to allow expansion of over 25 centimetres. The key to unlocking supersonic flight for a plane as big as the Concorde was here. The distinctive delta-shaped wings, though they came with a compromise. Only generating limited lift when flying at low speeds, for the Concorde to get off the ground, a high-speed takeoff was necessary. And even more nerve-wrackingly high-speed landings were required in order to control descent. But once the plane got up to speed in the air, the delta wings were more than worth it. When a plane breaks the sound barrier, the shockwave boundary folds back toward the plane. With a conventional wing design, the shockwave would strike the plane at the wings, creating drag. The delta wing's thin, streamlined profile avoids the shockwave entirely, enabling efficient and stable supersonic travel.
There are not many aircraft really that come anywhere close to the Concorde and be able to sustain such high speeds for such long periods of time. And so that comes down to this idea of an aeropropulsive balance, that the faster you fly, the more drag you produce. And so you need very, very good aerodynamic design to minimize that drag. But then to overcome that drag, you need very efficient engines. So you need the combination of powerful, efficient engines with very efficient aerodynamic design. So we see that in the Concorde.
In service for 27 years, the Concorde made just under 50,000 flights in its lifetime, allowing some 2.5 million people to experience flight beyond the speed of sound. There was controversy in the form of noise complaints from the sonic booms it generated, but ultimately, it was economics that led to the Concorde's retirement in 2003, with the supersonic plane not profitable against the carrying capacity of its larger, slower rivals.
There is a lot of work currently underway through various engineering companies around the world designing what will follow the Concorde. What we are likely to see in the pretty near future is the emergence of operational supersonic business jets.
Incorporating advances in aerodynamics and jet engines with lighter, cheaper composite materials, startup company Boom Technology aims to have a fleet of mini Concordes by 2023. Set to fly faster and more efficiently than their iconic predecessor, Boom proposes ticket prices on par with traditional carriers, making supersonic flight more accessible than ever before. Ever since Chuck Yeager first piloted the Bell X-1 to supersonic speeds, experimental aviation has been faced with a question: how to get from supersonic to hypersonic.
Hypersonic is going much faster than the speed of sound. So there's a barrier at the speed of sound where you start to form shockwaves. And supersonic is faster than that, and hypersonic is more than 5 times faster than the speed of sound.
Today, this is the cutting edge of hypersonic flight. NASA's X-43A.
The X-43 is a supersonic combustion ramjet engine, or a scramjet engine. And that's an engine that's designed to burn fuel faster than the speed of sound.
A single-use unmanned craft, the X-43A broke its own previous record of Mach 7 on November 16, 2004, when it reached a staggering speed of approximately 10,600 kilometers per hour, close to 10 times the speed of sound. To reach such speeds, the X-43 is first carried into the air by a customized B-52 Stratofortress. When it is drop-launched, the X-43 is attached to a Pegasus rocket booster which fires up to carry the craft even higher and faster.
Launch. Sequencer reset. Ignition. Ignition.
After leveling out at an altitude of over 30,000 meters and already flying at 5 times the speed of sound, the X-43 switches to its own scramjet engine and leaves the rocket behind.
Separation. Fuel is on.
Unlike a turbojet that compresses air with a rotating compressor, a scramjet uses forward velocity and aerodynamics to achieve the same effect without moving parts. In the X-43, the craft itself is integrated with the engine, with the front designed to scoop up oxygen, forcefully compressing the supersonic airflow before combusting it with hydrogen fuel. The expanding hot gases are expelled through the aft of the plane, which acts as a nozzle to accelerate the exhaust, generating its tremendous thrust.
Normally, if you want to go really fast, like you want to go into space or something, then you would use a rocket. But a rocket has to bring its oxygen with it. If you have an engine that can use the oxygen in the air, then you don't have to bring it with you and you can carry more payload.
Generating tremendous thrust without the need for onboard oxygen, the X-43 is proving scramjet technology.
I think we'll see scramjets with military purposes, so perhaps for fighter aircraft, certainly for missiles, and potentially for access to space.
While the power of speed remains prized in the air, size can also be an asset or a liability. The longest flying machine and largest by volume, the LZ-129 Hindenburg launched to great fanfare in Germany on March 1936.
The Hindenburg, Germany's latest and greatest dirigible, rises from Friedrichshafen on her first demonstration flight.
It was massive. It was 245 metres long. That's 3.5 times the length of a Boeing 747. It was huge.
Powered by 4 reversible Daimler-Benz diesel engines, the Hindenburg gracefully made 17 round trips across the Atlantic.
Complete success crowns the Hindenburg's first South Atlantic crossing, and the biggest airship ever built lands safely at Rio de Janeiro.
Heralded as the future of air travel, today it is remembered as one of the world's biggest air disasters.
It had a fatal flaw in that it was filled with hydrogen rather than an inert gas like helium, which is what you would use today.
Nearing the fatal end of her first Atlantic trip of the season, the Hindenburg approaches the mooring mast at Lakehurst. Scarcely 100 feet above ground, the giant airship with her framework encasing 7 million cubic feet of inflammable gas is being carefully maneuvered towards her hangar, when suddenly...
May 6th, 1937, the Hindenburg explodes into flames while docking in New Jersey. With a simple spark of static electricity, 36 people lost their lives, marking the end of the airship era. But the quest for scaled-up air transport continued. And during the Second World War, the need to fly troops and material across the Atlantic resulted in the largest aeroplane ever constructed, the Hughes H-4 Hercules. Built by the larger-than-life businessman and aviator Howard Hughes, the construction of this flying cargo ship was made more challenging by US wartime restrictions on metals, resulting in it being built entirely from wood.
It was intended to be a flying ship, and it was designed at a time when conventional shipping across the Atlantic was being sunk in very high numbers by German U-boats.
Howard Hughes' flying boat has a wing spread of 320 feet, and that gives you some idea of its size. Howard Hughes himself checked the controls before the first tests were carried out at Long Beach, California.
Powered by 8 Pratt & Whitney Wasp major engines, the largest aviation piston engines ever mass-produced in the US, the craft made just one flight in 1947. The unannounced decision was made during a taxi test, and with Hughes himself at the controls, the airboat reached an altitude of around 20 metres for a single minute.
The aircraft remained in ground effect during that whole flight, which meant it was still being supported by the effect of the wings on the ground or the water underneath. So we don't know whether it would ever have flown like a conventional aircraft, but it flew. We did it. That was Howard Hughes. That's the way he operated.
The Second World War drove demand not only for large-scale transport, but for heavy bombers. One of the largest operational aircraft during the war, the B-29 Superfortress was also the most expensive US weapons project of its time, outspending the Manhattan Project that developed the first nuclear bomb by more than $1 billion.
The B-29 Superfortress is highly advanced for its time. It had things like tricycle undercarriage, which was unusual in those days. It had pressurisation of the cabin, which was most unusual in those days. Remotely controlled defensive guns. It was a bit of a technical marvel. At the end of the day, it was the aircraft that ended the Second World War.
At 2:45 in the morning, August 6, 1945, Colonel Tibbets takes the Enola Gay down the runway into the air.
Flying under 4 Wright duplex Cyclones, the most powerful radial engines ever made in the US, the B-29 cruised at high altitudes, beyond the range of ground defences. The heaviest production plane of its day, the B-29's ultimate power was in the nuclear weapons it was equipped to carry. And in the final stages of the war, this ultimate power was used, with 2 separate B-29s dropping 2 separate nuclear bombs on the cities of Hiroshima and Nagasaki.
At 9:15, the bomb is dropped. The aircraft banks away at high speed.
Killing an estimated 129,000 people, these controversial and devastating bombings forced the surrender of Japan and remained the only use of nuclear weapons in warfare. Another Boeing giant designed to carry nuclear armaments, the B-52 Stratofortress, is a Cold War relic that refuses to die. First flown in 1952, the Stratofortress was built as a high-altitude nuclear bomber. Designed to fly above the range of ground-based defence systems and deliver its nuclear payload anywhere in the world. As the Cold War hotted up, the B-52s became the only bomber that mattered. With Operation Chrome Dome ordering nuclear-equipped B-52s to fly the Soviet Union's borders 24 hours a day for 8 years running.
The B-52's main role is a strategic bomber. Its capability has developed over the years from one of dropping just unguided dumb bombs. It's now able to carry and deploy a full range of guided weapons.
Scheduled to remain in service until at least 2040, the B-52 Stratofortress will be flown by the great-grandchildren of its original pilots, proving this huge craft's unparalleled power in terms of sheer longevity. Powered by the rising property of heated air, or by harnessing gases less dense than air. Throughout the long history of ballooning, the technology has remained simple, while the achievements have become increasingly impressive. In 1906, the world's first international air race, the Gordon Bennett Cup, was established for balloons, a race that continues to this day.
Paris was the starting place of the recent balloon race. Yes, balloon racing has begun again, in spite of all the more recent inventions and advances in aviation.
First reaching the stratosphere in 1932, balloons continue to take us higher, with new benchmarks constantly being set. And balloons, the first form of air power, continue as a significant force today, carrying us ever further. High-flying and efficient, balloons have been incorporated into NASA's space research program, where they have proven to have a range of advantages over rockets.
High-altitude space balloons are a way where you can do space-like environments cheaply, more efficiently, and they often end up being a test bed for bigger experiments that eventually do go into space.
Comprised of a thin film of polyethylene, about the thickness of a sandwich wrap, building a balloon is hardly rocket science. And it's a lot cheaper. With a balloon launch attracting far less red tape than a typical rocket launch, this old-school technology is once again at the cutting edge.
I think the biggest thing that I'm impressed by is that they fly. They look so flimsy. I mean, the material it's like cellophane. You would think that how could this thing survive the harsh environments of going all the way up 30, 40, 50, 60 kilometers, staying for that long, and then just gently land on the ground?
Capable of lifting over 3,500 kilograms, NASA's balloon program uses two different types of helium-filled balloons to transport scientific payloads into the atmosphere.
So we have what we call zero pressure balloons. So these are really enclosed balloons, but because the higher you get into the sky, there's lower pressure, so gas expands. But by going really high, air eventually escapes and eventually seep out, and you come straight back down.
Superpressure balloons, on the other hand, are completely sealed, holding a relatively constant gas pressure in the face of changing temperatures.
It acts like a bladder, so it's like a balloon inside a balloon. You have hydrogen in one shell, helium in the other, and you expand and contract that inner bladder, and that allows you to keep in a stable altitude, in a stable orbit, or a stable position of the Earth. And these can go for hundreds of days or even months.
The scale of these scientific balloons is truly enormous. With a size well over 1 million cubic meters, a fully inflated balloon can easily contain a sporting stadium. The quest for new sources of power in the sky is unending. With its array of photovoltaic cells and battery storage units, the Swiss-engineered solar impulse is powered purely by the sun. And it is already breaking records. Among them, the first circumnavigation of the world by a piloted solar aircraft. The aim now is to repeat the feat without stopping. Quieter, cleaner, and more efficient, this flying solar panel has greater ambitions than just breaking records. Seeking to move flight beyond limited fossil fuels to a source of endless renewable energy. In certain areas, the power of the pilot is every bit as important as the power of the plane. Almost as old as flight itself, aerobatics and air racing today is codified into a popular spectator sport. Stunts such as these test not only a plane's maneuverability, but a pilot's nerve and skill. A successful aerobatic pilot needs to manage the G-forces that their bodies are subjected to, as well as the physical stress on the body of the plane. The stunt plane of the military world. The Mikoyan MiG-29 is capable of aerial feats that would be impossible with regular aerodynamic controls. Designed as a multi-role fighter capable of operating from improvised airfields at the front lines of the Cold War, the MiG-29 first took to the sky in the late 70s. Codenamed Fulcrum, this was one of the last cutting-edge jet fighters produced before the collapse of the Soviet Union, and it continues to serve in the Russian Air Force today. With twin Klimov RD-33 turbofan engines spaced widely apart to provide additional lift, the lightweight Fulcrum boasted excellent acceleration with a top speed exceeding Mach 2, faster than its American F-16 rival. But the MiG-29's real claim to fame is its super maneuverability, proven by the demanding move known as Pugachev's Cobra.
This is a rapid pitch-up manoeuvre, so the aircraft is flying along, pitches its nose up even beyond the vertical, and then can recover that back down and resume normal flight, which for a conventional aircraft is just impossible. The aircraft would stall and lose altitude very rapidly.
The Fulcrum's wing shape generates a vortex of air over the front edge.
That vortex is generating quite a bit of force. It's maintaining the lift at an angle of attack of the aircraft well beyond where a normal aircraft would stall.
For all its agility, the MiG-29 was undermined by some notable shortcomings. A lack of modern electronics meant that its pilots had limited situational awareness. And with a range of less than 1,500 kilometres and no in-flight refuelling ability, the Fulcrum was a multi-role fighter in name only, primarily serving in defence or frontline support. Despite these limitations, with a reasonable price tag and recent upgrades to address some of its shortcomings, this Soviet-era jet continues to serve in militaries around the world. As jet fighters engaged in increasingly risky maneuvers at increasingly high altitudes, the question of how pilots could safely bail out came to the fore. This is how it was answered. Riding a high-altitude balloon into the stratosphere Colonel Joseph Kittinger performed a series of experiments throughout the late 50s and early 60s as part of the US Air Force's project to develop safe ejection equipment for high-altitude pilots. Kittinger's job was to jump. Wearing a pressurized suit to prevent his blood from boiling at the extreme heights, in 1959, Kittinger stepped out from the balloon's gondola to perform the world's first stratospheric space dive. It was a first, and nearly a last for Kittinger, as an equipment malfunction caused him to black out, with his automatic parachute saving his life.
Our bodies are built to be on the Earth with gravity and relatively normal temperatures, not to go through extremes and in extremes in only a few minutes. So you're really pushing your body to the limit when they do these jumps.
Indomitable, Kittinger returned to the stratosphere twice more. And it was during the ascent for his final jump in 1960 that the seal on his right glove failed. Kittinger kept quiet as his hands swelled to twice the normal size and lost function.
These stratosphere jumps have a huge team of medical doctors monitoring every part of it, because when they land, they need to know how to treat them. Are they deprived of oxygen? Have they had hypothermia? Are there pressure problems? Can they see? Are they going to have a heart attack?
Kittinger persevered, ascending to a manned balloon altitude record of 31 kilometres before again taking the plunge.
I had made the jump 1,000 times in my mind, so when it came time to go, I was ready to go. I reached 614 miles an hour. I free fell for 4 minutes and 36 seconds. And then once the parachute was open, it took about 10 minutes to get to the ground. And when I landed, my team was there, and we were happy campers.
Man is capable of remarkable feats in the air. But today, a new trend in aviation is seeing the pilot taken out of the plane. Today, we are witnessing the rise of the drones.
Pilots get tired, they need to be fed, they need to go to the toilet, whereas a robot machine can just keep flying. As long as there's power and there's fuel, it can just keep going and going and going.
Unmanned aerial vehicles, or UAVs for short, have been in the sky in various forms since 1916. With advances in technology, these flying robots are now a genuine power in the sky and are only becoming more powerful. With a range of sizes and capabilities, drones are used in everything from agriculture to racing. It is the military that has produced the greatest leaps in drone technology. And this is the result. General Atomics MQ-9 Reaper. The first unmanned hunter-killer designed for long endurance missions and high-altitude surveillance.
The Reaper is powered by a 900 horsepower turboprop engine. That enables it to fly for 14 hours at heights up to 50,000 feet.
More powerful than previous models, the Reaper can not only fly further, but can carry a heavier payload. With a wealth of advanced sensors in its bulbous nose, and weapons including laser-guided bombs and Hellfire missiles, the Reaper is the world's deadliest drone. Connected by a satellite link, the Reaper is always monitored by a pilot, analysing the images the craft provides and issuing commands from the safety of a ground control station thousands of kilometres from the conflict. And progress continues with Northrop Grumman's X-47B. first strike fighter-sized drones to achieve carrier-based launches and recoveries.
It has a unique capability that it can be launched and recovered to a ship at sea, which means the force and the power of that vehicle can be projected to anywhere in the world.
The X-47B has also demonstrated the first autonomous aerial refueling of an unmanned aircraft, setting the stage for entire fleets of carrier-based UAVs. A new generation of military drones are already taking to the sky. And with the pilots staying grounded, the machines have gotten small.
We're going to see drones that are smaller, and we're going to see drones that are smarter.
Instead of people, these micro-drones can carry communications payloads such as cameras, able to penetrate spaces inaccessible to conventional UAVs. They offer applications ranging from counterinsurgency to search and rescue. Or they can be weaponized. Released from Air Force bombers, clusters of explosive drones are set to replace the cluster bomb. Staying aloft to perform aerial maneuvers, they adopt a holding pattern before diving down at the right moment and self-detonating with enhanced precision. The new aerial arms race is smart and small, and within a generation, the nature of conflict could be rendered almost unrecognizable. But going small poses a big problem. At this level, everything we know about powered flight ceases to work, and a new understanding of fluid dynamics is required. An understanding provided by nature. Essentially, the smaller you go, the more resistance air provides. And on the insect scale, the air is a thicker, stickier medium. Moving through air at this level is more like swimming than flying. And this is where fluid dynamics comes in. When an insect flaps its wings, a swirling vortex of air is formed, creating an area of high pressure to push the wing up from below. Before flapping down again, the wing rotates to create a backspin force, pulling a faster stream of air over its top surface. As the wing hits the vortex from its previous stroke, it generates additional force that can be directed up or down by the angle of the wing, a principle called wake capture. While humans are yet to manufacture a machine that perfectly mimics insect flight, the power of wake capture is being used to create a range of insect-inspired machines.
Nature as inspiration is particularly useful for these really small scales of flight because it provides a way to overcome this scaling problem and say we can more efficiently generate flight at these small scales.
While nature has had millions of years to perfect animal flight, humans have just had a few hundred. In returning our focus to the natural world, our understanding of flight and the unique properties of air is being revolutionized. And the skies are set to become a very different place. To travel the land, one thing is prized above all else: speed. Since the fast production methods of Henry Ford put the world on wheels, speed has influenced every aspect of the car, and the car has literally shaped our world. In this episode, we surge from the once ubiquitous utilitarian Model T to the muscular V8 stylings of the Mustang, and from the jet-powered supersonic thrust to the electric game changers of Tesla. This is the story of land power. While only 29% of our planet is land, this is where we all live. And that 29% still equates to more than 92 million square kilometres to get around. 92 million square kilometres of mountains, ice, deserts, jungles, and everything in between. In order to efficiently traverse this vast terrain, often rugged and often inhospitable, man has evolved to walk upright. And the evolution has not stopped there. Today, this is where the evolution has taken us. The latest and greatest vehicle from a long-standing auto manufacturer, founded on the belief that nothing is too beautiful and nothing is too expensive. This is the Bugatti Chiron.
I believe they're in a league of their own. There's no one close to it for that level of hyper car.
The Chiron is the worthy successor to Bugatti's Veyron, the fastest street-legal car in the world, with a top speed of over 430 kilometres per hour.
The Veyron is a marker in the sand. It is the world's fastest car, and it will probably stay as the world's fastest production car for a long, long time to come.
The Chiron uses very similar technology to what was developed in the Veyron, and it's sort of a last hurrah for non-hybrid hypercars, where we have a nice big engine with 4 turbochargers and everything's mechanical.
With its speed electronically capped at 420 kilometres per hour, the Chiron, as the company likes to put it, brings beast to a very high level of beauty.
In terms of what they are, there's no electric motors or anything like that, and it's still raw brute power.
While its speed may be capped, the Chiron's 16-cylinder W configuration engine delivers a 25% performance increase over the Veyron, thanks largely to its 4 double-powered turbochargers.
They use W16 engines, meaning that you have W cylinder arrangement, and that can accommodate up to 16 cylinders in it, which is crazy.
With the engine mounted centrally in the car, more weight is placed over the rear tyres, increasing both acceleration and sensibly braking. Weight is otherwise kept to a minimum with a light and highly aerodynamic carbon fibre body. Defined by its sweeping C-shaped curves, these design features are integrated into the performance of the car, optimizing airflow to an engine that gulps a massive 16,000 litres of air per minute. Directing airflow is vital for speed, but in a car this overpowered, it's also necessary to keep it from flying off the road. Along the flat aerodynamic underbody of the car, a series of forward flaps adjust their angle at high speeds to keep downward pressure on the front tyres. The slit-raised wing at the back does the same for the rear wheels and serves as an air brake. With a multi-million-dollar price tag and taking an average of 6 months from construction to customer delivery, Bugatti releases around 70 Chirons per year, placing them among the world's most exclusive production vehicles.
No one will ever build anything like that ever again. It's a very iconic car in that sense. It's a one-off. You'll never see anything like that ever being produced, not on a mass scale. So it is a very, very special car.
More exclusive, though less luxurious, automobiles of various designs could be seen on the roads as far back as the early 19th century. The car has no single inventor. Rather, it's an evolution of the sum of an estimated 100,000 patents from dozens of inventors around the world. Experimenting with various forms of power, the first horseless carriages ran on steam, gas, or electricity, until one innovation steered them in a particular direction. Built by German engineer Nikolaus Otto in 1876, the Otto cycle was a compressed charge internal combustion engine that went on to define the dominant power source of automobiles for more than a century.
An internal combustion engine works by converting chemical energy into heat energy and then into mechanical energy. So by igniting a fuel-air mixture, we can increase the pressure within the combustion chamber, which drives the piston of the engine down. Now that downwards motion of the piston in turn rotates a crankshaft, and that crankshaft gives us rotational energy, which we can then use to drive the wheels.
While the concept of internal combustion engines had been around for many years, even after the technology was proven, it would be years before it was put into a car. To Carl Benz, we owe the first practical mass-produced automobile, the Benz patent motor wagon of 1885. The three-wheeled construction featured a four-stroke engine of his own design, with an advanced electric ignition system and rudimentary steering. The motor wagon went on to become the first commercially available automobile in history, aided by a unique marketing campaign.
So internal combustion engine, the idea was there for hundreds of years, but then it was first commercialized and tested in a real vehicle by Mr. Benz and his wife.
Unbeknownst to Carl, his entrepreneurial wife Bertha took the vehicle and their two sons on a 100-kilometre journey to visit her mother, famously notifying her husband by leaving a note. This journey was the first long-distance drive, proving the viability of the automobile.
And that, by record, is the first driven internal combustion engine powered vehicle in the world history.
As cars continued to grow in practicality, they remained costly contraptions owned only by the rich. More than any other, one man and one car changed that forever. Henry Ford and the Model T. Born to a Michigan farming family in 1863, from an early age, Henry Ford showed an aptitude for mechanics. And after turning 16, he left farming life behind to pursue a career in engineering. Establishing the Ford Motor Company in 1903, Ford's vision was to manufacture inexpensive cars using skilled workers earning good wages. He did this by developing the assembly line technique of mass production. Installing lines of conveyor belts in his factory, Ford workers, who were paid a generous $5 a day, were at the height of production able to churn out more than 300,000 Model Ts annually. Offered to the public in any choice of colour, so long as it was black. The reason behind Ford's famous pronouncement was that Japanese black enamel was the only finish capable of drying fast enough to keep up with his production method. Model Ts could be put together in as little as 93 minutes, and these savings in time translated to financial savings for the customer. Because of Henry Ford and the Model T, car ownership in the US became affordable to the many rather than the few. And by 1918, half of all cars in America were Model Ts. Started via hand crank, the Model T's four-cylinder 20-horsepower engine reached a top speed of about 70 kilometres an hour, more than enough on the largely unpaved roads of the day. Utilitarian in appearance, uncomfortable to drive, and incessantly rattling, the Model T's many shortcomings were the source of many affectionate jokes. Nonetheless, this affordable mass-produced car is credited with powering a social revolution by providing independent transport to the masses. Ford would also be at the forefront of the next great revolution in automobiles, the V8 engine. First patented in France in 1902, the V8 engine was initially more common in speedboats and aeroplanes before it found its now iconic place in cars. The V in the V8 comes from the angle at which the 8 cylinders are mounted on the crankcase. Split into two opposing banks of 4, the cylinders drive a common crankshaft. which, as in a standard engine layout, converts the piston's linear energy into rotational motion that is transferred through the gearbox to the wheels. With the overlapping power strokes of the 8 cylinders largely eliminating unwanted engine vibrations, the V8 is an inherently balanced design. But the V8's principal innovation was that it generated more power without an increase in size.
By increasing the size of the engine, then you can produce more power. It is just a question about how to fit that certain volume that's large into a limited space.
Introduced in 1932, the Ford Flathead V8 was the first affordable, mass-produced V8 engine. The Flathead revitalized and redirected the Ford Motor Company. This engine whetted the appetite of power-hungry consumers, and the design of cars changed radically to keep up. From the V8, a new generation of car was born. While fast, overpowered cars had been produced before, it was in 1960s America that they went mainstream. With petrol cheap, the economy strong, and the youth market lusting for fast, sexy vehicles, the era of utilitarian transport gave way to a period of tire-smoking excitement in the form of muscle cars. These affordable small to mid-size cars, with their powerful V8 engines, could be driven for everyday street use or pitted against each other in formal or informal drag races. With automakers competing for supremacy on the racetrack as well as the sales chart, the motto became, race on Sunday, sell on Monday. And this was the sales success story of the 1960s, the Ford Mustang. Coming onto the market in 1964, the Mustang, with its low price, good looks, and long options list, took America by storm. Although not initially marketed as a muscle car, the Mustang, with its optional range of gutsy V8 engines, certainly had the power to qualify. Instead, this high-performance compact created its own market category, the pony car. A huge factor in the Mustang's initial success was its low price point, owed to the fact that it shared much of its engineering with an existing Ford product, the Falcon. But it hardly mattered to the public. The Mustang offered enough stylistic points of difference to be its own car. Ranging from a 164 horsepower model to the high-performance version boasting 271 horsepower, the sales sensation of the 60s, the Mustang created a trend with the muscle car market that other automakers were bound to follow. Arriving fashionably late to the pony car party, Pontiac's 1967 Firebird made quite the entrance. Built with the specific purpose of competing with the Mustang, Pontiac had a little over 2 years to design and engineer the Firebird, which in car-making terms equates to a mad dash. To meet its deadline, the Firebird, much like the car it was striving to beat, started out by borrowing parts from existing vehicles, namely those of the Chevrolet Camaro. Chevrolet and Pontiac were both brands owned by General Motors, and both the Camaro and the Firebird were aimed at cutting into the Mustang's dominance over the muscle car market. Like the pony car it was made to compete against, the Firebird was offered with 6-cylinder engines as well as a range of V8s. And the V8s were by far the most popular. While the Firebird stirred the same levels of passion in its drivers, it never met the sales levels of the Mustang it was designed to tame. Remembered with a fondness beyond sales charts, the Firebird remains a much-loved product of the competitive spirit that characterized the muscle car era. Coming to an end in the 1970s, the period of muscle cars was short-lived, but their influence has remained strong and fed into other types of car. cars like the Dodge Viper.
The Dodge Viper is an all-American action supercar. It is traditional, big engine, big loud, brash car.
Some engineers at Dodge had the great idea of stuffing the biggest engine that they had lying around into the smallest car they could fit it into, and the Dodge Viper was born. It's a point-and-shoot muscle car that will go incredibly quickly in a straight line.
First roaring onto American streets in 1992, this heavily muscled sports car and its voluptuous stylings pay loving tribute to the muscle cars of the early 60s. In a period where the prevailing trend was toward efficient, conservative cars, this gas-guzzling extrovert was a throwback to a different time. The chief selling point of this impractical vehicle was that it offered what few others in the more sensible 90s car market could: brute power.
It's got an 8.3 litre V10 engine, which is literally out of a truck, but they've transformed it into a performance car engine that just is brutal.
Recruiting the expertise of supercar manufacturer Lamborghini, which was owned by Chrysler at the time, the Viper delivered a rating of 400 horsepower at 4,600 revs per minute, numbers almost unheard of in the early 90s.
It produces about 480 kilowatts in its top spec, which is probably about 5 times the average small hatchback, and around the same sort of power as most of its supercar rivals.
Delivering great gobs of power to its extra-wide Michelin tyres, there was plenty of traction, and the Viper stuck to the road like the snake it was named after. Car lovers could not get enough, and the trend-bucking Viper, with its nostalgia for the muscle cars of a previous generation, was a top-selling instant classic. Before production vehicles were built and sold with race car power, the race for pure speed was long in the running. During the pioneering days of speed racing in the 1920s and 30s, few figures captured the public's adoration quite like Sir Malcolm Campbell. Holding the land speed record 9 times during his life, as well as setting 4 water speed records, the British-born motorist received a knighthood for his contribution to the field. Racing in a series of several cars he named Bluebird, the fastest of these was the Campbell-Railton model, built in collaboration with British automotive engineer Reed Railton. A design of the modernist 30s, the Campbell-Railton Bluebird featured a low rectangular cross-section, spanning the full width of the wheels for reduced drag. Its distinctive tombstone radiator grille could be closed with a movable flap, briefly enhancing the aerodynamic profile during record runs. Powered by a Rolls-Royce V12 engine, the Bluebird made record-breaking runs across the hard-packed sands of Florida's Daytona Beach in 1933 and again in 1935, clocking what was an unprecedented top speed of 445 kilometers per hour. Campbell knew the car was capable of more. Believing that a lack of traction on the sand was holding the Bluebird back, Campbell's quest for speed led him to the Bonneville Salt Flats of Utah. Here, on September 3rd, 1935, with his young son Donald watching on, Malcolm Campbell set his last land speed record of 484 kilometers per hour. Dying in 1948, Sir Malcolm Campbell was a rarity among the speed racers of his day, not only with his long list of successes on land and water, but for the fact he died from natural causes rather than in a crash.
Well, Dad, I'm mighty glad you reached the 300, but I felt sure you'd do it.
Right, old chap, I'm very pleased too. But I reckon you've had a real good time whilst you've been over here in the States, because everybody's been so awfully kind to you, haven't they?
They sure have.
Following in his father's racetracks, Donald Campbell set land and water speed records throughout the 1950s and 60s. While a generation before, his father Malcolm had been the first to break the 300-mile-per-hour mark on land, it was Donald's great ambition to go even faster, with his sights set on breaking 400. This was the vehicle that he hoped would do it. the Bluebird Proteus CN7, the first car to be powered by a gas turbine engine, an engine that up until this point had only been used in airliners. Drawing air into the engine through the car's open nose, this painstakingly streamlined vehicle was thought to be capable of over 800 kilometres per hour. Returning in 1960 to the site of his father's last record in Utah, Donald crashed during a test run at around 580 kilometres per hour. Thanks to the tremendous structural integrity of the vehicle, he survived.
I have survived the fastest crash that mankind has ever survived.
Despite being intensely superstitious, Donald Campbell's bad luck continued. With the car completely rebuilt, a more promising racing ground had been located on the dry lake bed of Lake Eyre in South Australia, a site that had gone without rain for 9 years. Shipping car and crew to the remote location in 1962, the heavens opened up and the lake was ultimately flooded to a depth of 3 inches. Finally, after 18 months of waiting, Donald made his courageous record-setting attempt on the still damp track. He achieved his goal, scraping past the 400 mile per hour mark and setting a new land speed record of 648 kilometres per hour. Never getting the chance to race on land again, Donald died 5 years later during a water speed attempt. From the early 60s, the land speed record climbed steadily higher, with the title of fastest man on Earth being traded back and forth between a handful of drivers. Californian Craig Breedlove claimed and reclaimed the honour several times before putting an end to things, at least for a while, in 1965. Using a surplus General Electric J47 engine, common in military aircraft, Breedlove's first record-breaking runs were not accepted by the International Automobile Federation because his vehicle, the Spirit of America, had 3 wheels instead of 4. After a near-fatal crash in 1964, the undaunted Breedlove returned a year later with the 4-wheeled Spirit of America Sonic 1. Powered by a superior J79 engine, he held the official land speed record for all of 5 days before it was surpassed. But the very next week, Breedlove responded with a new record of 966 kilometres per hour. This time, the record would last 5 years before being broken in 1970. To claim it back, Breedlove set his sights on going faster than the speed of sound. But he was not alone. This was the vehicle that Breedlove was up against, the Thrust Supersonic Car, SSC for short. Designed by a British team headed by Richard Noble, who himself set the land speed record in 1983, this jet-propelled car had the express purpose of not only breaking the record, but breaking the sound barrier.
If you want to go faster than the speed of sound on land, your problems actually are larger than in air, because you have the solid boundary, the Earth, on which you're traveling, and that means there is a very small gap between the moving object and the Earth.
Propelled by a pair of afterburning Rolls-Royce Spey 202 jet engines, the same used in F-4 Phantom fighters, the Thrust SSC produced an awesome 110,000 horsepower, making it the most powerful car ever built. Designing a car this powerful was one thing. Finding someone to sit behind the wheel was another. With a select few capable of the job, a rigorous testing process arrived at this man, Royal Air Force fighter pilot Andy Green.
It's like a man walking on the moon. It's the 4-minute mile. It's climbing Everest. It's something that nobody's ever done before. It's something that no team has ever done before.
Green's challenge was immense. unable to house steering gear at the front of the vehicle due to aerodynamic restrictions, the Thrust SSC was steered via its asymmetric rear wheels. Whether such an unusual system was viable at the speed of sound was uncertain.
From the aerodynamic point of view, make this very dangerous. You have this very slim cushion of high-speed air sitting underneath the vehicle, and there is a serious chance that this vehicle would be lifted.
Or if the nose were to dip, the car would drive itself into the ground. Everything hinged on having a perfectly neutral aerodynamic profile. Even if everything performed perfectly, the question of what happens when a land vehicle pierces the sound barrier remained unknown. There were fears that the resulting shockwave may derail or destroy the car, along with its driver. Nonetheless, in October of 1997, Andy Green and Craig Breedlove squared off in the Nevada desert to find out. Sadly for Breedlove, he never had his opportunity. With his latest Spirit of America suffering engine damage during a test run, he was forced from the contest and could only watch from the sidelines as Andy Green and the Thrust SSC took to the sands. 50 years and 1 day since Chuck Yeager and the Bell X-1 rocket plane first broke the sound barrier, Andy Green and the Thrust SSC joined the club, blitzing along the desert at a top speed of 1,227 kilometers per hour. This was the first time a car had gone supersonic. The record stands to this day, but it is not safe from attempts to break it. And Andy Green and the Thrust team are among those seeking to go faster still. Henry Ford is quoted with saying that auto racing began 5 minutes after the second car was built. With formalised racing events dating back to the emergence of gasoline-fueled cars, the racetrack has a long history of serving as a competitive testing arena, spurring continual improvements across all areas of vehicle performance.
The only race of its kind in the world, there were 49 starters in this year's Grand Prix.
More than any other, the world's oldest active endurance race, Le Mans, is credited with inspiring technology that has translated into consumer cars. Held annually in France since 1923, Le Mans has been called the Grand Prix of endurance and efficiency. Racing for 24 hours, competitors strive to cover the most distance around a circuit that mixes public roads with professional racetracks. With modern distances easily exceeding 5,000 kilometres, Le Mans tests not only a vehicle's speed, but its fuel economy, reliability and safety.
Le Mans is an interesting race in that the engines have to be designed for both power and efficiency. Because it is such a long race, going for 24 hours, if your engine is inefficient, you'll be making a lot of fuel stops. And obviously, while you're stopped refilling your car, your competitors are going to be driving past you.
The long, fast straight known as the Mulsanne has fostered developments in aerodynamic performance. And with the unique safety rule that requires cars to be switched off while being refueled, hardier vehicles that can restart multiple times are de rigueur. Despite the emphasis Le Mans places on safety, deaths have occurred here, with the greatest tragedy being this crash in 1955, resulting in the death of 80 people. In response to the disaster, Le Mans, as well as other races around the world, enhanced its safety measures. But as safety standards improved, so did the power of cars, with vehicles adopting more extreme designs to attain more extreme speeds. Vehicles like the Porsche 917. The development of this now legendary car came about due to a rule change in motorsports that allowed for a new class of cars to enter endurance racing. With engine capacity capped at 5 litres, Porsche began work on a smaller engine version of its 908, and in just 10 months, the 917 was built.
Definitely the 917 broke all records and really made people have a look. Absolutely amazing car.
The car, in spite of its often garish 1970s paintwork, is today considered one of the greatest race cars ever made, and was even immortalised in film, starring alongside Steve McQueen in the 1971 movie Le Mans. But the 917 did not achieve instant greatness. In early models, the power of its 12-cylinder engine, capable of going from 0 to 100 kilometres an hour in 2.4 seconds, exceeded the vehicle's handling, and Porsche had a hard time finding drivers willing to pilot what was considered an accident waiting to happen. And at the 1969 Le Mans, the accident did happen, with driver John Wolfe losing control of his 917 and dying in the resulting crash. But Porsche persisted, and chief engineer John Horsman found the solution to the 917's problem. In studying the splatter of dead bugs over the vehicle following test laps, he noticed that the insects were concentrated on the bodywork, not the tail. No bugs meant no airflow, and therefore, no downforce. At high speeds, a race car's tail, or wing, is designed to do the opposite of wings on a plane.
Race cars tend to have downforce, so that is, they have aeroplane wings that are upside down that press the car into the surface, which increases the pressure that the tyre has to deal with, and they get very hot, so the slick tyres tend to be very strong construction and very, very sticky rubber compounds to keep the race car on the track.
With its lightweight aluminium frame and fiberglass body, the key to making the Porsche 917 into the dominant race car it became was in perfecting the design of the tail. Adding shorter, more upswept fins provided a clean flow of downforce-inducing air over the rear wheels. With a dramatic improvement in the car's handling, Porsche suddenly had a race winner on its hands. And in 1970, this car provided the German manufacturer with its first win at Le Mans. The following year was even more impressive, with the car again taking out Le Mans as well as 8 of the 10 races for the World Trophy, cementing the 917's enduring legacy as one of the most powerful street-legal race cars. With technology proven on the track, a class of cars emerged featuring the best performance and design the auto industry had to offer. Supercars. The term supercar has been used in the car market since the 1920s. Today, this is what it means. This is the Lamborghini Huracan. With its V10 engine delivering 610 horsepower, the highly powerful, highly luxurious Huracan can go from 0 to 100 in a blistering 3.2 seconds, securing it the honour of Supercar of the Year upon its release in 2014.
So it sounds amazing. I suppose the magician's back at the factory. A lot of it's with the engineering, with the exhaust and the manifolds and the way the sound gets delivered.
Using aerodynamica Lamborghini Attivia technology, ALA for short, the Huracan bends air to its will. On the front, a horizontal splitter blocks air from flowing beneath the car, maintaining downforce on the front tyres. When downforce and the drag associated with it is unnecessary, a pair of flaps open in a split second, allowing air to flow through for improved aerodynamics. On the back, air intakes can direct airflow above or below the rear wing, again balancing downforce with drag. The wing itself contains a hollow chamber, allowing airflow to be directed internally to either side. When cornering at high speed, the ALA system directs airflow, and therefore downforce, to the inboard half of the wing, balancing the load on the rear tyres.
The Lamborghini Huracan engine is a V10, which means that there are 10 cylinders in a V configuration, 5 on each side. The engine can produce 610 horsepower, which is equivalent to the amount of work 610 horses could do over 1 hour.
With its high power and high performance, the Huracan is an instant classic of the elite supercar genre. Not all supercars are created equal. And even in this rarefied world, it is possible to go one better. The best of the best. The top 1% of supercars are classed as hypercars. Cars like the Lykan Hypersport. Made by the United Arab Emirates company W Motors, this is the first hypercar of the Middle East. And carrying a price tag well in excess of $3 million, it is also among the most expensive production cars ever to go on sale. With a twin turbocharged flat 6 engine positioned behind the driver, the Lykan produces 750 horsepower. Going from 0 to 100 in a breakneck 2.8 seconds. The car's top speed is just shy of 400 kilometers per hour. With only 7 Lykans produced, they are among the most exclusive cars on the market, even by hypercar standards. Much about this enigmatic and excessive vehicle remains a mystery, including how many have been sold. Though it is safe to say that this is an extremely powerful car, owned by extremely powerful people. With supercars continuing to develop new technology and improve performance, for a vehicle like the Lykan to attain hypercar status, it must be at the very forefront of engineering and design. But the bar continues to be raised, and what is extraordinary today may be commonplace tomorrow. While it may be some time before diamond-encrusted headlights are standard, the innovations that have come from cars have the power to change the world. Literally reshaping the land, roads allowed cars to reach their full potential. And as cars came to travel faster and more frequently upon them, safety technology needed to accelerate to keep pace. First performed in the 1930s, crash testing quickly became a popular means of investigating a vehicle's structural integrity. With crash test dummies introduced in the late 40s, the impacts on a car's occupants became better understood, and this form of testing led to a suite of safety innovations. As the shortcomings of simple lap seatbelts were demonstrated, Volvo developed the now standard 3-point seatbelt. Rather than patenting the technology for profit, it was made freely available in the interest of saving lives. Airbags, unpopular at first, became more effective with improvements in seatbelts and are standard today. And as cars have become safer in accidents, the trend has shifted towards accident prevention, with a host of smart technologies designed to monitor driver performance or take over driving altogether. Just as it was in Ford's day, the greatest influence a car has is not the car itself, but how it is built. And today, vehicle manufacturing is on the cusp of a revolution, more world-changing than Ford's assembly line.
3D printing is a revolutionary engineering tool. It has the ability to manufacture quite complex shapes, layer by layer or in a blown system. So things like design complexities are not an issue anymore. Virtually anything can be manufactured using 3D printing.
Not only can 3D printing change the way we make cars, it can change the cars we make. With current methods needing to stamp out big pieces of metal into shape, cars are designed around parts that are mass-producible, not necessarily optimal. 3D printing offers a means of making optimal components mass-producible. With the freedom to add extra material to stress points for enhanced strength, or leave gaps to reduce weight, 3D printed vehicles are both stronger and lighter. But that is just the start. By customizing every detail of every car part, the possibilities of 3D printing are endless. Doing away with inflexible, mile-long assembly lines, small-scale factories will be empowered to produce an endless array of cars. With no need to retool an entire factory of machines, a 3D printer can go from making a truck to a small car with no downtime at all. Major manufacturers already use 3D printing to produce prototypes of vehicles that will later be produced en masse using assembly line methods. And with vehicle manufacturing one of the most environmentally damaging industries, the waste-reducing benefits of 3D printing promise a sustainable future for the auto industry. For cars to be truly sustainable, a new source of power is needed. Harmful to the environment and human health alike, the emissions from fuel-burning engines are increasingly being regulated by governments around the world. And as oil decreases in abundance, oil-derived fuels are increasing in cost. Fortunately, cars from their very inception have a history of running on alternative power. Hybrid cars decrease their dependency on fuel by incorporating an additional power source, typically electricity. Running an electric motor alongside an internal combustion engine, hybrids seek to improve fuel efficiency as a means of decreasing pollution and running costs.
Hybrid vehicles can be configured in a number of ways. The electric motor and the petrol motor or diesel motor can complement each other. They can work in parallel or they can work in series. So there's a lot of flexibility when it comes to designing a hybrid vehicle.
The first car to combine an internal combustion engine with an electric motor was constructed in 1898 by a young Austrian doctor with the familiar name of Ferdinand Porsche. 100 years later, the hybrid is back in vogue.
You basically have two power sources in any hybrid engines. The way they work is you have power split device right in the middle. And you have internal combustion engine running when it's needed to generate electricity, or directly linked to the power shaft and make the vehicle move. And this power split device sitting in can be used to control, either use that mechanical motion to generate electricity so that there's some energy can be stored in a battery, and then the electricity can be used when it's needed.
Electric engines also have the advantage of acting as self-powering generators, capturing energy that would otherwise be lost and converting it to electricity. This is particularly evident in regenerative braking. In conventional cars, brakes produce friction with the brake rotors in order to slow down, dissipating the vehicle's kinetic energy as heat. Regenerative braking slows the wheels by putting the electric motor into reverse. While running backwards, the electric motor is functioning as a generator, producing electricity and feeding it into the vehicle's batteries for later use. Economical and environmentally friendly, the long-known energy-saving technology of hybrids is today steering performance cars in new directions. A plug-in hybrid, the BMW i8 delivers near supercar performance with the fuel economy and emission standards of a compact vehicle. Marketed as the world's most progressive sports car, BMW claims the i8 is a vision of the future. And as the world's top-selling electrified sports car, they may be right. Chargeable via an ordinary wall socket, its high-voltage lithium-ion battery bank is maintained at an optimum operating temperature by an innovative cooling system. The turbocharged 1.5-litre three-cylinder petrol engine produces a healthy 230 horsepower. Sitting above the rear axle, the combustion engine takes a back seat to its electric counterpart.
BMW i8 approach, it's a little bit different. Your vehicle will be operated solely by AC motor, and internal combustion engine, it does not produce direct power supply to your power shaft, but it's more or less generating electricity, and then the generated electricity is used to run the AC motor. So the AC motor is the core element to produce power.
Obviously, the more motors you can have delivering power at any one time, the faster that car can go. It can be configured to just drive the wheels with the electric motor and use the engine as a generator. It's like carrying a power plant around with you in the car.
With an electronically limited top speed of 250 kilometres per hour, the i8 provides performance with impressive fuel efficiency and minimal emissions. With a choice of 4 driving modes, at one end of the spectrum, Sport mode makes the most of the petrol engine for maximum power. At the other end, eDrive relies solely on the electric motor, which can take the car for around 37 kilometres without using a single drop of fuel. The i8's highly aerodynamic design and its lightweight body, featuring carbon fibre reinforced plastics, adds to the efficiency and sports car performance. This is an energy-efficient, environmentally friendly vehicle that does not skimp on the power and fun of a traditional sports car. The need for a new source of power, reliable, sustainable and affordable, has brought us to the cusp of a new era in automobiles. One car maker is counting on it. Tesla is both an auto manufacturer and a renewable energy company. Specialising in battery storage, it is the marriage of car maker and power provider that has seen Tesla lauded as the world's most important car company. Named in honour of Nikola Tesla, the genius Serbian engineer who invented the induction motor and alternating current power transmission, Tesla builds electric cars that don't just measure up to conventional vehicles, but outperform them. And with a maverick CEO in the form of Elon Musk, Tesla is using a business model all its own to make different cars for a different future. Tesla's first car, the Roadster, released in 2008, was the first high-performance all-electric car. Going from 0 to 100 in 4 seconds and able to travel more than 320 kilometres on a single charge. Constantly improving, the more recent Model S, with its ludicrous mode, goes from 0 to 100 in a staggering 2.7 seconds.
Essentially, the ludicrous mode on a Tesla just runs the electric motors up to their maximum rated power, which is inefficient, so it creates a lot of heat and it drains the batteries very quickly, but you can go fast. You can go very fast.
The key to this speed is the instant torque provided by the electric engine.
Torque is essentially the strength of an engine, or how much force it can put out, whereas power is the product of that force and the speed that the engine is turning at. So how many times per second that force is being applied is what gives us power.
The power advantage of an electric motor is its access to full torque from a standstill. Needing to force air into the engine for combustion, conventional engines have to build torque over a period of acceleration. For electric motors, the torque is produced not from the explosion of igniting fuel and oxygen, but from an electrical charge that winds the motor. Therefore, torque is produced the instant electricity is applied. Where once the internal combustion engine set a course for cars to follow and for innovators to build upon, today, the electric motor is set to overtake it. Tesla is building toward a world where electric vehicles will have levels of ownership beyond those of the Ford Model T. And as the revolutionary mass manufacturing techniques of Henry Ford put the world on wheels, now the radical possibilities of 3D printing are disrupting the established order. As we race ever forward, the story of how cars evolved in the past offers telling insight for their evolution in the future. The automobile has changed the world we live in. Colossal networks of roads have reshaped the land, carving paths between cities and towns themselves, built around the needs of cars. But land-going vehicles are not confined to tarmac. And the true freedom and mobility afforded by automobiles is in their ability to take us beyond. In this episode, we venture from the rough and ready revolution of the military Jeep to the smart tech-driven future promised by the BMW Motorrad, and from the heavy-duty powerhouse of the Caterpillar Series 7 to the flying cars turning science fiction into science fact. This is the story of land power. When it comes to all-terrain vehicles, this one truly lives up to the name. Taking inspiration from the legendary mountaineering Sherpas of the Himalayas, the Russian-built Sherp ATV takes on just about anything nature can throw at it.
I have never seen anything like it in my life. It's just amazing. And that's technology, like, comes so far in that type of vehicle these days. And so they can build an ATV that can go anywhere, basically. I'm just gobsmacked by what they can do now.
Extremely manoeuvrable, the Sherp's lever steering mechanism controls the speed of its oversized wheels on both sides of the vehicle, allowing for skid steering and turning in place. The patented tyres also let the Sherp do this. The buoyancy of its tyres and their paddle-like tread allow this mini monster truck to swim at an impressive 6 kilometres per hour, jumping in and out of the water with ease. This amphibious car is all but unstoppable. Running on ultra-low pressure, the tubeless tyres mould around obstacles, allowing the Sherp to climb obstructions over 2 feet tall. And self-inflatable, they can be adjusted for optimum performance over varying terrain. Sitting proud of the vehicle, the custom tyres are so large that in top-of-the-line models, they house additional fuel tanks. Drawing just 44 horsepower from its Japanese Kabuta 1.5-litre turbo diesel engine, the Sherp maxes out at around 45 kilometres per hour, commanding the land less through engine power and more through sheer ruggedness of design. With a durable polymer coating for extra toughness and a smooth protective underbody, the Sherp is built to withstand a tremendous amount of punishment. Should a problem occur, ease of maintenance has been factored into the design, with the transmission simply bolted onto the tub-like steel frame. The company also boasts of the vehicle's high survivability, claiming it can continue driving on just 2 wheels. A go-anywhere car without equal, the Sherp was built to serve workers in the most demanding environments on the planet. Nonetheless, with its adult-sized Tonka truck appearance, a sense of fun here is inescapable. Perhaps unsurprising, given that the fun and freedom of recreational off-roading has its origins in some very no-nonsense vehicles. Vehicles like the Unimog. Few automobiles can boast the enduring success and celebrated versatility of the Unimog. Even fewer can claim to have emerged from such bleak circumstances. Entering production in 1947, the first of these universal motor vehicles featured all-wheel drive and a flexible frame integrated with the suspension. Aspects that were unique at the time.
Unbelievable climbing, the angles you can get them at is just amazing. Amazing off-road abilities, big, high, once again, high centre of gravity, but great for troops, carrying heavy loads, that type of thing.
Carrying power takeoff points and machinery mounts, the early Unimogs were put to use operating saws in forests or harvesters in fields. In the 1950s, with Mercedes-Benz taking over manufacture and industrial restrictions on Germany easing, the Unimog expanded beyond the farm, adding more powerful engines and more sophisticated technology, including different attachment systems for a wider range of jobs. The Unimog's potential was realised as a vehicle that could not only go anywhere, but could do anything, and the evolution has continued to this day. Adaptable to an endless array of purpose-specific customisation, Unimogs have been put to use in industry, military, emergency services, and recreation. A combination of car, truck, and tractor, the Unimog has proved itself as the ultimate all-rounder. and an indestructible living legend. Hailed as the godfather of modern-day four-wheel drives, the US Army's Jeep was designed for a very specific wartime purpose, but went on to have a much wider influence in times of peace.
Way back then, they were pretty ordinary, pretty rough to ride in, not the sort of thing you'd want to be taking your family around in.
The first of its kind, this tough and agile go-anywhere vehicle laid out the essential blueprint that lightweight 4x4s would follow for years to come. The origins of the term Jeep remain unclear, but the development of this iconic vehicle stemmed from the vision of the US Army and the coerced collaboration of several car companies. Anticipating entry into the Second World War, the US military knew it needed to modernize. Putting out hundreds of tenders for equipment and machines, one such tender called for a command reconnaissance vehicle, the vehicle that would become the Jeep. With the Army setting exceedingly strict demands for power, performance, weight and size, none of the original prototypes they were presented with made the grade. But three companies came close: Ford, Willys and Bantam. And through the grudging, possibly illegal, sharing of their designs, the combination of all three companies' efforts resulted in the Jeep. Core to the Jeep's design is a separate chassis carried on leaf springs over live beam axles, allowing power transfer to all four wheels. While the solid beam axle prevents independent movement of the wheels, meaning that the motion of one affects the other, their mechanical simplicity provides a crucial off-road advantage: durability. And durable is exactly what the Jeep proved to be, fulfilling its envisioned Second World War role as a reconnaissance vehicle, and doing just about everything else the Army asked of it. Versions of the Jeep remained in service until the early 1980s, and the Jeep had a lasting appeal in peacetime too, beginning the world's love affair with recreational off-roading.
World-renowned for its reliability is the Land Rover. In this British factory, the Land Rover is manufactured.
This is the off-roader that bridged the gap from the military to the civilian world. With its origins in agriculture like the Unimog, and bearing more than a passing resemblance to the Jeep, the Series 1 Land Rover went from humble origins to open up the planet like no other vehicle. The British Rover Company had built its reputation on luxury cars. But in post-war England, such vehicles were hardly in demand. To remain in business in a time of austerity, a short-term solution was needed. And while driving his war surplus Jeep on his rural property, Rover's chief engineer, Maurice Wilkes, hit upon the idea of designing a civilian version of the wartime workhorse. Within months, his idea was approved, and the first series of the Land Rover was rushed into production. With two ranges of gear, too high and too low, the original Land Rovers used a transfer box to make maximum use of engine torque.
Generally, the biggest difference between four-wheel driving engines and high-performance car engines is that a four-wheel driving engine is centered around torque and reliability, where that four-wheel drive is not going to be necessarily going very fast, but it needs to have a lot of strength, essentially, to get up steep cliffs or over boulders. And it also needs to not break down when you're in the middle of the desert.
With an immensely strong box section, steel chassis, and waterproof wiring, these vehicles willingly went anywhere and kept on going. Despite its minimal comfort levels, this simple and robust 4x4 found its place not just with rural buyers, but with the new breed of off-road adventurer. And with ready markets across the British Commonwealth and former empires, Land Rovers exported to Africa, the Middle East and Australia, giving access to uncharted and inhospitable parts of the world like no vehicle before. The demands of both civilian and military drivers for enhanced off-road performance culminated in a car that served in both worlds: the high-mobility, multi-purposed wheeled vehicle, better known as the Humvee.
As an SUV, it is huge. It fits right in America because everything is big in America. It would literally cast a shadow over the rest of the traffic.
In the late 1970s, the US Army was again looking to upgrade and began seeking a light tactical 4x4 to replace its aging fleet of Jeeps. The vehicle needed to have the latest in off-roading capability and be versatile enough to fulfill the jack-of-all-trades role that had so aptly been served by the Jeep. Of the three companies that presented prototypes, AM General's Humvee won out and entered service in 1984. First entering combat in the US invasion of Panama in 1989, it was the Humvee's widespread use in the Gulf War of 1991 that saw it enter civilian consciousness. With its wide-set machismo, the vehicle's most prominent admirer was former Terminator and future California Governor Arnold Schwarzenegger. So dismayed with AM General's refusal to sell its military vehicle to a civilian, he lobbied the company to produce a civilian version. And in 1992, it was Schwarzenegger who became the first owner of a civilian Humvee, known as the Hummer. Larger and with a much wider track than a Jeep, the Humvee maintained the Jeep's low profile, but managed to nearly double its ground clearance by raising the drive shafts and fitting the axles towards the top of the wheel, rather than in the centre.
Well, it is huge to start with. It's got a lot of ground clearance so it can get over boulders, and a really solid four-wheel drive system that allows it to plough through the bush and mud tracks anywhere it wants to go.
With torque biasing differentials at the front and rear, each output shaft to the wheels is able to rotate at different speeds. So when a decrease in torque is detected in a wheel slipping over loose terrain, increased torque is transferred to the opposite wheel, boosting power on one side of the car to compensate for a loss of traction on the other. While its off-road prowess is beyond question, the Hummer's excessive size and poor fuel economy has made its transition to civilian life a controversial one. Also controversial when introduced in 1980, BMW's R80 GS went on to inspire a new style of motorcycle for a new style of riding, adventure touring. When first released, this motorcycle bucked the trend towards specialised machines by aiming for a crossover skill set. At the time, few thought a two-wheeler was able to incorporate off-road capability with on-road performance. Today, after more than 30 years on the market, the ongoing popularity of the GS series has silenced its initial detractors. Among a host of design innovations, the GS helped pioneer a new style of motorbike suspension.
You've got long suspension travel, you've also got a 21-inch front wheel, and that also helps to absorb bumps, particularly if you're on the off-road surfaces.
Tough and surprisingly smooth, the GS was a revelation for two-wheel touring enthusiasts and more. Like the early four-wheel drives that preceded it, it was the versatility of the GS that saw it exceed expectations. The first successful production bike to provide off-road guts, on-road speed, and everyday practicality. The GS reinvigorated motorcycle design, taking bikes back to their roots as the original go-anywhere vehicles.
And this is Windy Lindstrom from Oakland, battling his way up that terrific 76% grade. Come on, you Windy! And he makes it in 8 3/5 seconds.
Smaller and lighter with a greater power-to-weight ratio. From their very inception, motorbikes had the go-anywhere advantage over cars. Like their four-wheeled counterparts, the motorbike cannot be traced back to a single idea or invention. Instead, they represent the combined and ongoing work of engineers and inventors around the world. But there is one revelation that made mass production possible: the Didion Bouton engine.
I wonder what would happen if this fella let go. Fall off, I guess.
Invented in 1895 by French engineers Jules Albert Didion and Georges Bouton, the single-cylinder four-stroke engine generated half a horsepower, a remarkable achievement for the time. Compact, lightweight and high revving, the Didion Bouton engine set a benchmark that motorcycle manufacturers the world over would copy and build upon. With the onset of the First World War in 1914, cars were not yet able to provide dependable off-road transport, and it was the motorcycle that filled the gap. Phasing out the horse, motorcycles were used extensively by both sides of the conflict to gather reconnaissance, deliver communications, and even engage in combat. Following the Second World War, many veterans, particularly in America, gravitated towards motorbikes as a substitute for the thrills and danger of wartime action, finding camaraderie in outlaw motorbike gangs. And there was one bike that transitioned from an admirable service in the military to an image of rebellion on the road. Few vehicles of any kind can boast of an iconic status quite like the Harley-Davidson. Celebrated in pop culture and supported by the company's own clever marketing, these bikes carry with them an aura of bad boy mystique, American individualism, and of course, power. Barely a decade old when the First World War began, the conflict had a defining impact on the Harley-Davidson company. Dedicating itself to the production of military motorbikes, when hostilities ended in 1918, more than half of the US Army's estimated 20,000 bikes were Harley-Davidsons. This translated to a market of returned soldiers already familiar with and fond of the brand. And by 1920, Harley-Davidson had grown to become the world's largest motorcycle manufacturer. Instantly recognizable by the unique throaty rumbling of their engines, Harley-Davidson have largely remained true to a basic engine formula centered around an air-cooled V-twin engine with its cylinders set at a 45-degree angle. With their long piston stroke, Harley engines are low revving and provide plenty of torque.
Harley-Davidsons make a very distinctive sound due to their V-twin engine layout, where there are two cylinders aligned in a V configuration that give a very lumpy sound as the two combustion events happen close to each other, and then there is a break before they happen again. So rather than having the power coming down like this, sounding nice and even, they go bang, 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 bang.
Part of the feel and part of the rawness of that engine is what you feel, and that is what makes people either really not like them or like them a lot.
Because of their big engines, Harleys tend to be big bikes, and this made them ripe for customization. Starting in California in the late 1950s, the desire for faster bikes resulted in the chopper. Stripping motorcycles of all unnecessary parts, DIY enthusiasts took to chopping up factory frames and welding them back together to produce lower and lighter vehicles capable of greater speed. The characteristic stretching out the front rakes may have sacrificed the bike's low-speed handling, but provided truer steering when traveling at speed. Harley-Davidsons provided the basis for some of the most recognizable choppers, and the craze had its influence on the style of bike the company went on to produce. But whether riding a factory-built Harley-Davidson or a customized chopper, the anti-authoritarian image remained the same. Debuting in 1970 as the XS1, the Yamaha XS650. While Japanese bikes had largely focused on more utilitarian offerings than Western manufacturers, the 650 was a stylish departure from this tradition and sought to take on the Western firms at their own game. It also marked Yamaha's entry into producing four-stroke engines. While the Yamaha Motor Company had staked a reputation on two-stroke engines, in 1970, the XS650 took the risk, branching out in an effort to match the four-stroke offerings of its competitors.
In four-stroke engine, you have valves that controls precisely the amount of air going in and exhaust gases coming out. So to produce more power, even in motorbikes, you do need 4-stroke engine.
And Yamaha's engineers were up to the challenge. Having collaborated on the high-performance Toyota 200 GT car, their 4-stroke credentials were proven, and it was a scaled-down version of the Toyota's engine that made it into the 650. Affordable, reliable, and enjoyable, the XS650 was a groundbreaking bike for Yamaha, spawning a 13-year production run and a particularly devoted following among flat-track racers. And it was racing that proved the technical triumph of Japanese bikes to the world. From the early 1960s, the big 4 Japanese manufacturers, Honda, Kawasaki, Suzuki, and Yamaha, became the dominant force on the racing circuit, with bikes offering more power and better performance than their American and European rivals.
After the Second World War, Japanese engineers were banned from producing aircraft. They went to the automotive industry, and that's where the Japanese basically started producing motorcycles.
Success on the track translated into success on the sales floor, with factory-bred races available to a power-obsessed public at a competitive price. But for all the thrills of enhanced acceleration and knee-dragging cornering on the road, the true go-anywhere nature of motorbikes is seen when they leave the ground altogether. Freestyle motocross does not compete with speed, instead focusing on the daredevil skills of riders as they seek to outdo each other in gravity-defying stunts. Emerging from off-road dirt bike racing, today this high-flying, high-adrenaline spectacle is one of the most popular extreme sports in the world.
The power they produce in such a light, small capacity, and then the amount of travel the suspension has would probably be the 2 main key components that set those bikes apart from other bikes in the industry.
Not requiring the fine engine tuning of racing vehicles, the bikes here are essentially ridden as stock, so long as the riders can grab a handful of throttle for rapid acceleration over a short distance. The rest is up to their own ability and courage. Lightweight dirt bikes running on small to medium displacement 2-stroke engines are favoured, and again, it is the offerings of the Japanese manufacturers that are most prevalent. Modifications are minimal, removing seat foam to give a wider range of motion, or adding a steering stabilizer to keep the front wheels straight when letting go of the handlebars. Other than that, the bikes, with their strong suspension and high traction tyres, are largely factory standard, meaning that just about anyone, provided they have a suitable launching point and no fear of heights, can take these versatile 2-wheelers off-road and into the air. Unveiled as a part of BMW's vision for the next 100 years, the Motorrad is the motorbike of the future. A future where helmets and leather are a thing of the past. With self-balancing wheels and gyroscopes serving to keep the bike upright, even at a complete standstill, the stability of this concept vehicle is set to eliminate the need for safety gear as well as a kickstand. And with a degree of autonomy in its driver-assisting technology, a late reaction from the rider will see the bike take over to balance itself out, essentially making it an anti-crash motorbike. A visor replaces both the helmet and the instrument cluster, with its integrated screen providing a heads-up display. Controlled by the rider's eyes and simple finger gestures, these data goggles collect information from the environment and feed back as little or as much detail as the rider desires. When riding, the Boxer engine extends out from the sides of the bike, improving aerodynamics and weather protection. And it's promised to be emission-free. But perhaps the bike's most revolutionary aspect is its carbon fibre flex frame. Changing shape in response to the movement of the handlebars and relaxing or stiffening depending on speed, the flexible structure allows maneuverability without bearings and joints. Integrating form and function, The Motorrad is steering the future of motorbikes in a new direction. In the here and now, for many work vehicles to have go-anywhere freedom and functionality, size matters. This is the Caterpillar Series 7. Serving in mining and heavy-duty construction, these ultra-class trucks are among the biggest ever built. With earth-moving machinery growing larger and more efficient, hauling vehicles are needed to keep pace. In 1997, Caterpillar, with the then latest computer-aided design technology, engineered the original Series 7 vehicles to offer the greatest payload capacity of any mechanical drive-haul trucks.
The 797F truck is an amazing vehicle, and only approaching to this vehicle in a mine site, you can have a clear idea of its huge dimensions. It is 15 meters long, almost like a coach bus, and is 9.5 meters wide and 6.5 meters high.
Nearly 8 meters tall and 10 meters wide, the latest Series 7 weighs a staggering 690 kilograms, and that's while empty. With a suitably enormous pillar-like hydraulic suspension system, the real heavy lifting is done by the 6 specially designed Michelin radial tyres, each weighing over 5 tons. All this powered by a turbocharged 20-cylinder 4,000 horsepower engine.
The 797F was developed because the machines that are used in a mine site to dig and to load the material are becoming bigger and bigger. They can load up to 100 tons of material in just one single scoop.
Owing to the Caterpillar's exceptional size and weight, they cannot be driven on public roads. Delivered to site in pieces on the back of 12 semi-trailers, assembly requires a team of 7 Caterpillar mechanics working around the clock for 20 days.
One of the most exciting things about this truck is to climb the ladder in front of it. And when you reach the cab, the view that you have from this level, that is like staying 2 stories off the ground, is amazing.
A huge truck with a huge role to play, the Series 7 range works in the service of even bigger vehicles. Vehicles like this, the Bagger 288.
These mammoth excavating plants combine the efficiency of conveyors with the utility of bucket excavation in a single gigantic earth-moving machine with relatively few continuously moving parts. The Bagger 288 can move the equivalent of 30 football pitches in the space of an hour.
A mobile strip mining machine, the Bagger 288, is truly mountainous, a handy attribute when your job is literally moving mountains. Taking 5 years to design and manufacture, and another 5 to assemble, upon completion in 1978, the Bagger took the record as the heaviest land vehicle in the world. After 23 years of service at Germany's Hambach coal mine, the giant excavator had exhausted supply and needed to make the move to a new mine some 22 kilometres away. Travelling at a leisurely 10 metres per minute, this equated to a 3-week journey. Sitting atop 3 rows of 4 Caterpillar track assemblies, each 3.8 metres wide, the weight of this epic excavator is incredibly well distributed. Nonetheless, special grass was sown ahead of the Bagger's journey to prevent it from sinking. Today, the Bagger continues work at its new home, where its coal-moving efforts help produce 15% of Germany's annual power supply. Already common in big industrial machines, driverless technology is poised to make it onto the highways, promising to enhance safety and efficiency in some of the largest street-legal vehicles. Mercedes-Benz is accelerating the transition with its future truck 2025.
You have virtually all of the automotive manufacturers now striving to introduce greater and greater levels of autonomy over the next decades.
With eyes in the form of radar sensors, Future Truck makes real-time decisions based on its immediate vicinity. And with data gathered from other connected vehicles and satellites, it makes accurate predictions along its entire route.
The car might still want you to be available to take control of the car if it runs into a situation that it doesn't know how to deal with. Then from there we go to mind-off driving, where you can for the first time really sit back and not worry about it. When the car takes over, you're not expected to be available anymore.
On the highway, the system operates much like autopilot on a plane, taking over the controls for the monotonous hours of long-haul transport, with the human driver free to relax or perform other tasks. When the truck leaves the highway, the driver is back behind the wheel, steering the Future Truck to its final destination. Before autonomous technology changed the way we thought about driving, this vehicle had been there and done that.
That popular little car, the Mini, is in the news again.
The Mini is a tiny car with a towering legacy. And after the Ford Model T, this ultra-compact economy vehicle is regarded as the second most revolutionary car of all time. Produced by the British Motor Corporation and its successors, this icon of 1960s pop culture was lent an enduring appeal thanks to its uncanny knack of going or fitting in surprising places. Built in response to the fuel rationing imposed by the 1956 Suez Crisis, which saw Europe cut off from its Middle Eastern oil supply, the Mini has transcended its purpose-built origins with a design so endearing it has barely changed from across 40 years of production. The key to Mini's mold-breaking success was its transverse engine layout. While previous cars with sideways-mounted engines had been limited to small two-stroke motors, Mini designer Alec Issigonis saw room for improvement. Incorporating the original Mini's transmission into the engine's oil sump freed up the extra space needed to fit a bigger, more powerful four-cylinder engine above the front wheels. And by utilising front-wheel drive, there was no need for a drive shaft, allowing 80% of the car's flat floor plan to be used for passengers and luggage. This layout brought a surprising amount of room and a respectable amount of power to an otherwise unassuming vehicle, influencing a generation of car makers. Since the Mini, almost all small front-wheel drives use a version of Issigonis' configuration. With its 10-inch wheels placed on each corner of the car in a bulldog stance, and with a suspension system of compact rubber cones rather than conventional springs, the low-set front-wheel driving Mini handled like a go-kart. While Issigonis was initially reluctant to depart from the Mini's image as an everyman's car, he came to collaborate with race car builder John Cooper. The result was the first Mini Cooper. With a souped-up racing-tuned engine putting big power into the little car, the Mini Cooper claimed 3 victories at the Monte Carlo Rally, helping cement the vehicle's reputation as a game-changer. Production of the original Mini continued into the year 2000, but its legacy still lives on. BMW took over the Mini marque and to this day are producing cars inspired by Issigonis' design, a design that changed the way people thought and perhaps more importantly, felt about small cars. Big or small, in the quest to go anywhere, sometimes wheels just aren't enough. With its origins traced back to the mid-19th century, the continuous track has enhanced the off-road capability of wheels by increasing traction and decreasing ground pressure. Contacting the ground only with their bottom portion, wheels concentrate their grip and their weight on a relatively small surface area, limiting traction and increasing the risk of sinking. Contacting a far larger surface area, the continuous track distributes a vehicle's load across the entirety of that area, improving grip and allowing travel over more unreliable surfaces. Employed in heavy off-road machinery such as the Bagger 288, the continuous track's most famous application is in tanks. And when it comes to tanks, there are a few more famous than this. the M1 Abrams. Developed during the Cold War, the M1 Abrams is today the principal battle tank, not only of the US Army and Marine Corps, but the armies of Australia and much of the Middle East. The race car of the tank world, the Abrams can approach speeds of 100 kilometres per hour. But because of the risks posed to the crew and the vehicle itself, an engine governor limits speeds to 72 kilometres per hour on-road and 48 kilometres per hour off-road. Nonetheless, the Abrams remains one of the fastest main battle tanks in service, all the more remarkable for the fact that it's also one of the heaviest.
So that tank has a gas turbine engine that, rather than developing thrust via an exhaust nozzle as we do on aircraft to propel aircraft, spins a shaft that via a gearbox drives the wheels and the tracks of the tank. And so what that allows the Abrams to do is very, very quickly bring on large amounts of motive power to drive that tank, that very heavy tank, to very, very high speeds for a tank.
Effectively a jet engine, the Honeywell AGT 1500 offers an increased power-to-weight ratio over a conventional piston engine and takes up less space. Running on anything from kerosene to jet fuel, the gas turbine is also significantly quieter, earning the Abrams the nickname Whispering Death. Quicker and more manoeuvrable than other tanks, the Abrams turbine engine comes with two drawbacks. It drinks a lot of fuel and generates a lot of heat.
There is a heat exchanger system on board the engine of the Abrams tank that allows it to recover some of that waste heat. For a tank, it has the additional advantage, of course, of not rejecting exhaust gases at very, very high temperature that can be easily detected by the adversary. So, of course, if you can take some of that exhaust heat out, you can use it within your engine, within your tank, and it also means that the exhaust flow will be that much cooler, and therefore you can more easily hide your thermal signature.
But tanks aren't made to hide, they are made to fight. And to that end, the Abrams' main weapon is its 120mm M256 smooth-bore cannon. Blasting high-velocity, armour-piercing and explosive rounds, the cannon is guided by a cutting-edge fire control system. With sensors monitoring the tank's tilt, its motion and even the wind, the cannon is computer-adjusted to keep targets in sight, allowing the Abrams to fire with accuracy while on the move. Strong and fast, the M1 Abrams is an almost unbeatable tank. For now. In the world of military technology, the battle for superiority never stops, and new innovations are always waiting in the wings. Innovations like this. At the US government's Defense Advanced Research Projects Agency, better known as DARPA, the search to find new transport systems has led to the rise of the machines. Machines that borrow from nature. Rather than reinventing the wheel, DARPA and engineering company Boston Dynamics have turned their attention to the efficient methods of movement developed by animals over 4 billion years of evolution. The Legged Squad Support System, LS3, is in essence a robotic pack horse.
Let's go back to cowboy days when you had your pack horse. That's the same concept, except this thing is a robot that follows you around. It can carry a lot of weight and go up and down terrain and do all those sorts of things. So you don't have to feed it.
The motorised quadruped uses a combination of cameras and laser sensors mounted in its head to negotiate rugged terrain, all while carrying over 180 kilograms of equipment. Intended to relieve the weight burden carried by military dismounts, LS3 was designed to operate alongside ground troops.
They quite literally look like large dogs or mules. And four-legged, and it just follows them around.
Proving itself in field tests, LS3 was ultimately shelved due to noise concerns. But it provided the launching point for the next generation of animal robot. The cheetah. While this running robot may not yet match the speeds of the fastest animal on Earth, it can cover over 12.5 meters per second, making it faster than any human. Coming along in leaps and bounds, animal-inspired technology is set to change the way we think of going off-road. Going off-planet, more traditional wheeled vehicles have made remarkable achievements.
So we kind of take advantage of being able to build cars and vehicles on the Earth. You know, we know friction, we know how it stays, but the lunar dust is drastically different. You know, there's a reason we've always had those pictures of, you know, someone's footprint landing in the moon and that footprint still being there. That's because lunar soil is drastically different than Earth soil.
While officially named lunar roving vehicles, these cars, taken to the moon on the last 3 Apollo missions in the early 1970s, will be forever remembered with their affectionate moon buggy nickname. Weighing a little over 200 kilograms, these lightweight compact vehicles were folded into 3 parts for storage in the cramped Apollo lunar modules. After assembly on the moon's surface, each buggy ran on a series of 4 electric motors mounted in the aluminium wheels. Producing a total of 1 horsepower, it was enough to clock up a top speed of 18 kilometers an hour in the low-gravity atmosphere. Designed to give astronauts a wider range to explore and collect samples around their landing site, the moon buggy also revitalized a flagging public interest in the Apollo missions, bringing a sense of fun to the lunar surface. Today, the cutting edge of off-planet off-roading is all business.
Order of 11, 12 rookies.
Eagle Dodge, you remain strong.
Touchdown confirmed. Receiving.
Touching down on the Red Planet in August 2012, this is the Curiosity Mars rover. The 4th unmanned NASA rover sent to Mars, the Curiosity is the biggest and toughest of them all.
So you have to build special tires, special traction, special dust filters, because, you know, if you get finely grained dust and it's going to clog up your dust filter, you know, think of how many problems we have just driving into work every day. But then your work is on Mars, and the destination is you not dying, right? You know, it's such a dramatic scenario that these things have to go through. They have to be robust, they have to be rigorous. And I think we take for advantage the fact that some of the Mars rovers have passed a decade.
While previous Mars rovers ran on solar energy, Curiosity runs on plutonium oxide. As the radioisotope decays, it gives off heat, which Curiosity converts to electricity through its thermoelectric generator. Going nuclear also brings more power, and despite being the heaviest of the Mars rovers, Curiosity moves at twice the speed of its predecessors. With a powertrain free of moving parts and a fuel source with a 14-year life expectancy, this nuclear power plant on wheels is set to keep on keeping on. To make sure this is the case, Curiosity utilizes NASA's rocker bogie suspension system. Foregoing axles or springs, this spider-like assembly of jointed titanium tubes is more robust and better balanced. The system allows the rover's 6 wheels, made of aluminium so thin that they flex like rubber, to move independently, maintaining constant ground contact over even the most difficult terrain. This balanced distribution of force provides maximum traction to all wheels at all times. Initially piloted by remote control from Earth, Curiosity has largely switched to autonomous navigation.
You've had rovers robotically going on Mars for over a decade, and I think it's just amazing how well that engineering has come to make that happen. Because they're not designed for a decade. You know, NASA designed something for a definitive mission, usually anywhere between 3 months and a year, but you know, to get year 7, year 8, year 9, year 10, it's just amazing how well it works.
More independent, more sure-footed, and more powerful than anything before, this Martian workhorse is the model for future Mars missions. Using the same design platform as Curiosity, and even a few of its spare parts, the unnamed 2020 rover upgrade is less a different model and more a different mission. Taking the next step from Curiosity's search for signs of habitable conditions in Mars's past, the 2020 will go searching for signs of life itself. And with a scientific payload that includes an experimental machine for converting the toxic Martian air into breathable oxygen, this vehicle is set to pave the way for humans to make our first interplanetary journey. Back on Earth, the long-held science fiction promise of flying cars is close to becoming reality. Classed as a roadable aeroplane, the Transition is, as the description suggests, a hybrid car and plane. In development since 2006, the Transition's 3 prototype models have all been proven in drive and flight tests, and the development company Terrafugia today plans on entering market production by 2020. Designed to fit in a standard household garage, in drive mode, the 2-seater carbon fibre vehicle operates via a typical steering wheel and foot pedals, and carries other standard car features such as bumpers and airbags. With a top speed of 110 kilometers per hour and reasonable fuel economy, upon reaching the airport, the Transition really distinguishes itself. Within 1 minute, its electromechanical wings fold out, and the rotary 100 horsepower engine transitions to drive a pusher propeller. Provided the driver has a sport pilot license, they can take the twin-tailed light aircraft to an altitude of over 3 kilometers and a cruising speed of over 170 kilometers per hour. In the air, fuel economy takes a nosedive, but the Transition is hardly designed to appeal to conservative motorists. And with the air allowing commuters to travel straight as the crow flies without speed limits, this vehicle of the not-too-distant future is set to create a whole new genre of off-roading. For a flying car that is on sale now, consumers with $500,000 to spare can today order their very own personal air and land vehicle, the PAL V1. Melding aspects of car and helicopter, this Dutch-designed roadable aircraft is far harder to categorise. Driving on 3 large wheels of its tricycle undercarriage, the PAL V1 is able to lean into turns like a motorbike. The PAL V1 can be converted in around 5 minutes to an autogyro, an aircraft that obtains lift from rotor blades and thrust from a propeller. With its unique Rotax dual propulsion engine now powering the propeller, the 2-seater can attain its same land speed of 180 kilometers per hour. Thanks to vehicles like the PAL V1 and the Transition, the future of land-based transport is no longer limited to the land. The quest to go anywhere is an ambition as old as civilization. From the dawn of the motorized age, cars, motorbikes, and others that defy labels have sought to provide the power and the wherewithal to take us wherever we needed or wanted to go. Today, we are redefining the concept of go anywhere, changing the way we move in order to open up our world in new ways and open up worlds beyond. For centuries, the fight for command of the seas has determined the rise and fall of empires and nations. To rule the waves, navies around the world have been locked in a battle to develop the most powerful and technologically superior vessels. In this episode, we chart a course from the once revolutionary steam-powered dreadnought battleships to the nuclear-powered fortresses that are the Nimitz-class aircraft carriers, and from the ever-evolving arms race below the surface to the new wave of amphibious craft and autonomous vessels above. This is the story of sea power. On the high seas, this is the height of technology. A guided missile destroyer, the USS Zumwalt is the most advanced ship from the world's most advanced navy. Fast, stealthy, and heavily armed, this vessel has been designed to combat the military threats of today and those of the future. With its futuristic appearance, the Zumwalt may stand out on the water, but its trapezoidal shape actually serves to hide it.
It's designed the way it is to reduce its radar cross-section. So if there's someone looking for it, if they can't see it with their eyes, then what they'll see on the radar is a much smaller return. They'll think it's something closer to a fishing vessel.
A big part of that comes from the ship's unusual hull, which narrows from the waterline to the upper deck. Known as a tumble-home hull, this design not only serves in stealth, it changes the way the ship moves through the water, slicing through waves rather than riding over them.
From a stealth perspective, you probably want a lot of sort of fairly straight angle panels that are not pointing straight back at any particular area.
Highly automated, the ship can run with as few as 130 crew members, less than half needed on similar-sized warships. The most powerful destroyer in the history of the US Navy, the Zumwalt is also the first naval surface combatant to run on all-electric propulsion. Driving its electric generators are a set of two of the most powerful marine gas turbines in the world, the Rolls-Royce MT30, producing 78 megawatts of energy, enough to power 10,000 homes. The Zumwalt has more than it needs to drive its propellers and power the ship's service and combat systems. The excess energy is anticipated to power weapons and sensor systems upgrades, ensuring the ship remains at the cutting edge well into the future. For all its advances, the Zumwalt is not without its critics. The incorporation of a radical design with a host of experimental technologies has sparked concern as to whether this ship of the future can live up to expectations today. With only one completed and in service, the Zumwalt has yet to be tested in battle, and only time will tell if it charts a course for the future of the Navy. Since mankind could take to the sea, we have sought to control it. And naval warfare can trace its origins to ancient Greece, the Romans, and the seafaring raids of the Vikings. From ancient times, it was sail power that ruled the waves. But in the late 18th century, a new technology arose, bringing an end to the age of sail: the steam engine. First appearing on boats in the 1770s, steam engines used external combustion to harness the heat energy of steam, converting it to mechanical motion through a paddle wheel or propeller. Redefining what ships were capable of, the steam age gave rise to a new generation of vessel. No longer dependent on the vagaries of the wind, ships became faster and more reliable. As ships grew in scale and power, the first armoured vessels, the ironclads, emerged in the mid-19th century. Slow and cumbersome, it would take another boost in power before armoured warships would rule the waves. In 1884, British engineer Charles Parsons invented what he believed would unleash the full power of the steam engine: the steam turbine. Seeing the potential for maritime industries, he set about building an experimental ship that would demonstrate this increased power to the world. The first steam turbine-powered ship, the Turbinia, though not equipped to fight, would shape the future of warships. With Parsons' turbine generating 1,000 horsepower, he calculated a top speed in the region of 30 knots. a record-breaking feat for the day. The problem was that in testing, the Turbinia failed to perform, unable to reach even 20 knots. What followed was a 2-year period of intensive research that led to a breakthrough in the understanding of cavitation. Because water at a lower pressure boils at a lower temperature, the low-pressure zone created by a spinning propeller can effectively boil seawater. The bubbles formed by cavitation are not filled with air, but with steam. As the steam bubbles implode, the resulting shock waves wreak havoc on any nearby moving parts, rapidly enhancing wear and dramatically decreasing performance. Parsons' research led him to understand that by increasing the blade size of the Turbinia's propellers, he could delay the inception of cavitation. Sporting this enhanced propeller system, the Turbinia took to the water again in 1897, reaching a top speed of 32.7 knots. It astonished onlookers and easily became the fastest ship of its day. The unprecedented power unleashed by the steam turbine engine was quickly seized upon by naval forces around the world, helping usher in a new era in battleship design, the dreadnought era. From the early 20th century, several navies around the world were toying with the concept of a battleship that would carry a uniform armament of heavy guns. Launched in 1906, it was the HMS Dreadnought that proved the revolutionary power of the concept. The fastest battleship at the time of her launch, the HMS Dreadnought was the first lead ship to be powered by steam turbines and sparked an arms race for bigger and better battleships that reverberated around the world. Fast and powerful, Dreadnought battleships were characterized by the exclusive use of turbine propulsion for speed and an array of large caliber guns for fighting. At the time, naval guns were unguided, and gunners relied on the splashes of missed shots to adjust their aim. The development of rapid reloading 12-inch naval guns meant that gunners could zero in on enemy targets more quickly and with the weapon that actually mattered. Equipped exclusively with these weapons, Dreadnought battleships became the most lethal force on the water and the dominant naval power throughout the First World War. Technical developments continued to advance rapidly, and by the dawn of the Second World War, the Dreadnought class was superseded by a new style of multi-role battleship. The Iowa class represents the culmination of the battleship era and the ultimate decline of such ships in the ever-evolving world of naval warfare. The first of the 4 Iowa-class ships entered service in the US Navy in 1943, representing the most powerful class of battleship ever built.
With her complement of about 2,000 men, the giant fighting ship goes through the battle maneuvers in readiness for that moment when her full weight will make itself felt in battle itself.
Speed, once a guiding principle in the Dreadnought era, had been sacrificed in preceding classes of US battleship in favor of heavier armor. But with the longer-hulled Iowa class, speed was back at the forefront. And courtesy of 4 cross-compound steam turbine engines, they were the fastest battleships in the world, capable of a top speed of 32.5 knots. With battleships having long since moved away from the Dreadnought all-big gun configuration, the Iowas carried a range of firepower, from its array of small 20mm anti-aircraft cannons to its 9 huge anti-ship and shore bombardment guns. Lobbing 16-inch shells for an incredible 32 kilometres at maximum range, the devastating projectiles could spend nearly a minute and a half in flight. For all their firepower and speed, in the Second World War, decisive naval battles were becoming a thing of the past, and the Iowas were relegated to an artillery support role in the island-hopping campaigns of the Pacific Theatre. All the while, debate continued as to the relevance of battleships. In a time when superior power was to be found above the ocean and below it. And it was below where the greatest revolution in naval warfare took place. With the widest range of types and capabilities of just about any aquatic vessel, submarines changed the dynamics of naval power forever. Experimentation with submersible craft dates back to the 16th century. But the myriad of engineering challenges posed by the underwater environment, from stability and navigation to life support and pressurization, meant that it was hundreds of years before viable designs were proven. And for this, much of the credit goes to one man. Considered the father of the modern submarine, John Holland was an Irish-born engineer who, in the late 19th century, built the vessel that proved the possibilities of underwater craft.
John Holland was an Irish-American who developed basically the modern concept of the submarine by understanding the buoyancy and the weight relationship and understanding how to make the submarine dive and return again safely to the surface in a consistent manner.
Combining an internal combustion engine for travel on the surface with an electric motor for propulsion beneath, Holland's prototype was the first vessel to run for any considerable distance while submerged.
It was that enabling technology of the propulsion that enabled both flight and also it enabled submarines.
The US Navy purchased Holland's model in 1900 and quickly ordered 6 more, inaugurating the first submarine fleet in the world. Today, what we know as the submarine owes much to the military, and the military was drawn to submarines for one reason: their ability to be weaponized. Named after the torpedo fish that hunts by delivering a stunning shock to its prey, the torpedo remains the most lethal anti-ship and anti-submarine weapon ever invented. While work on underwater missiles had taken place previously, it was English engineer Robert Whitehead that is credited with creating the first self-propelled torpedo in the mid-19th century. Fired from a tube above or below the water, Whitehead's torpedo used a 3-cylinder compressed air engine to travel towards its target. With its worn nose designed to detonate a charge of explosive gun cotton on impact, Whitehead's chief innovation was the addition of a hydrostatic valve and pendulum balance connected to the rudder, allowing the weapon to maintain a constant depth. The latter addition of a gyroscope mechanism allowed the torpedo to correct its course against underwater currents, greatly enhancing its accuracy. Devastating to ships and difficult to defend against, the torpedo was the ultimate naval weapon. And able to close into an effective range while undetected beneath the surface, submarines were the ultimate craft to deploy it. Thus, it was the torpedo that transformed the submarine from experimental oddity to fearsome weapon of war. And throughout the 20th century, there were perhaps no submarines more fearsome than the U-boat. German for undersea boat, these craft, like all submarines of the era, were more submersible ships than true submarines.
And the U-boats in the First World War and the Second World War were just continuations of the same technology and the same design and the same thoughts that Holland had.
Sinking beneath the surface to avoid airborne attacks and to conduct stealthy torpedo strikes on enemy craft. It was this underwater ability that made the U-boat so deadly throughout both world wars. The most significant of the U-boats was the Type 7, relatively cheap and quick to build. During the Second World War, the Type 7 formed the backbone of the German U-boat fleet, with over 700 produced. And it was this vessel that rose to prominence in the longest, largest, and most complex battle in naval history.
At the beginning of the Second World War, submarines were being deployed by the Germans to sink the merchant ships that were going from America to support the UK. And in fact, Churchill is quoted as saying the most dangerous thing for him during the Second World War was the Battle of the Atlantic.
The German U-boats, led by the Class 7, patrolled the Atlantic in dreaded wolf packs. With their small profile and tight living quarters for their small crew, the Type 7s were all about agility and armament. Running primarily on the surface under diesel engines, the Type 7 was capable of rapid crash dives, and this favoured manoeuvre saw them disappear beneath the waves in as little as 20 seconds. Here, their combustion engines could not be supplied with sufficient oxygen, and they switched to their less efficient electric motors. What was sacrificed in efficiency was gained in stealth, and listening from the depths with advanced underwater microphones, they set their torpedoes to sink dozens of warships and millions of tons worth of merchant cargo. But the tide eventually turned against the U-boats, and the hunter became the hunted. The breaking of Germany's Enigma code, along with new Allied tactics and weaponry that capitalized on the U-boats' limited underwater performance, rendered them little more than sitting ducks. In the closing stages of the Battle of the Atlantic, these craft came to be referred to as iron coffins. Developed in the years between the First and Second World Wars, the T-class submarine was the British Navy's attempt to command this new aquatic battlefield. Along with an enhanced hydrodynamic structure, the T-class subs carried twin 1,450 horsepower electric motors to provide a greater capacity for underwater performance. Nonetheless, along with other subs of the day, the T-class remained faster and more efficient on the surface. And here, the T-class ran on twin 2,500 horsepower diesel engines, with an increased fuel capacity to afford a wider range and longer mission durations. But the T-class submarine's real advantage was simple. It could fire more torpedoes. With 4 external torpedo tubes and 6 tubes built into the bow, it was the first submarine to ever carry such firepower. The design proved a success. Playing a major role for the Royal Navy in World War II, the T-class was upgraded during the Cold War to target Soviet subs, remaining in service until the 1970s. With submarines revolutionizing naval warfare from below, surface vessels needed to adapt to neutralize the threat. Employed by both sides during the First and Second World Wars, merchant ships carrying concealed weaponry were an early attempt to do just that. Known as Q ships, they were designed to appear as easy targets, luring submarines to the surface where they could attack via deck guns rather than firing their limited torpedoes. Even if struck by torpedo attack, Q ships carried a cargo of light wood in order to remain afloat, encouraging the sub to expose itself in order to finish off the apparently foundering vessel. When the submarine surfaced, the Q ship's panels dropped to reveal its own deck guns. Using the elements of surprise to overwhelm its otherwise superior adversary. But the submarine menace would never be neutralized without more sophisticated methods, and one naval vessel proved especially adaptable to the role: the frigate.
Today, post-war, the frigate is generally used to define a surface ship which has as its specialization hunting submarines.
Warships built for speed and maneuverability, frigates were increasingly retrofitted with anti-submarine technologies during World War II. And this capability would be built into new models in the latter half of the 20th century. Models like the Leander class. First commissioned by the British Royal Navy in 1963, the Leander class became one of the most numerous and long-lived frigates in modern history, with derivatives of the design being adopted by other navies around the world.
The first thing the frigate has to do is be very quiet. So one of the key things about the frigate is to make sure that the speed at which cavitation occurs is as high as possible, so that when it's hunting for a submarine, it's not making any cavitations.
Being quiet is one thing, but anti-sub vessels also need to be good listeners. To that end, they were equipped with an enhanced detection system in the form of VDS, variable depth sonar. Towed behind the ship, the Leander's VDS array emitted sound waves to echolocate objects underwater, determining bearing, range, and depth. With their position revealed, enemy submarines could be fired upon using an anti-submarine mortar system known as Limbo. Launching depth charges in any direction around the ship, Limbo used 3 barrels to drop the explosives in a triangular pattern around the target, maximizing the chances of a hit.
The other thing an anti-submarine frigate will have is a helicopter. The helicopter will be designed for anti-submarine purposes, and it will be able to fly and put a dipping sonar in the water and listen for submarines.
Due in large part to these enhanced capabilities, not a single ship among the 26 Leanders was ever sunk by enemy action. But the next leap in power would not only revolutionize submarine warfare, it would redefine naval forces the world over. The nuclear revolution of the mid-20th century boosted both the power generation and the armament of naval vessels like nothing before. Thanks to nuclear power, submarines became true submersibles. Capable of remaining beneath the surface indefinitely, subs were now limited only by the supplies they could carry and the endurance of their crew, giving rise to a new generation of vessel.
Mrs. Eisenhower took 2 hands to the job when she named and launched the American submarine Nautilus at Groton, Connecticut. The vessel is the world's first atomic-powered submarine. It's said to have cost over £10 million to build.
Launched in 1954, the USS Nautilus represented an unparalleled breakthrough for submarines. Taking its name from the vessel in the science fiction classic 20,000 Leagues Under the Sea, this deep-diving giant turned imagination into reality.
The key thing about the Nautilus, that was the first submarine to operate under nuclear power. And until that had happened, nobody really knew whether they could run a nuclear power station in a submarine. I mean, it's quite crazy thought, really, to take a nuclear power station and put it into the tiny little confines of a submarine.
With diesel-electric submarines required to spend the majority of their time on the surface in order to charge their batteries for limited dives, non-nuclear subs were limited mainly to coastal defence. The Nautilus was designed to travel much further afield and primarily underwater. Among the many records for distance and speed that this new breed of submarine set, in 1958, the Nautilus travelled beneath the Arctic ice to become the first watercraft ever to reach the North Pole. Core to the incredible range and ability of the Nautilus was its S2W pressurized water reactor. As the atoms of nuclear material split, they generate heat. A pressurized water reactor uses a primary coolant system to circulate water through the reactor and absorb this heat. Pressurized so as not to boil, the now heated water in the system passes through a steam generator, where it transfers its heat to the secondary, unpressurized coolant system. With the water in the secondary loop vaporizing, steam is formed, which is directed to spin the turbine generator and produce the vessel's electricity.
The small nuclear part, which is shielded, of course, from the people, is used to heat water into steam. The steam is then used to drive a steam turbine. The steam turbine then drives the shaft. So basically that's how the process works.
Silent, consuming no air and producing no emissions, nuclear power was perfectly suited to submarines, and the pressurized water reactor became the basis for nearly all the US Navy's nuclear-powered subs, as well as its surface combat ships. The first of its kind, in operation, the Nautilus revealed a number of design and construction shortcomings.
Nowadays, submarine hull shape design is quite different. It's not designed for running on the surface with the occasional trip underwater. It's designed underwater. And on the surface, it looks really odd because it's just making all the wrong waves.
Its record-setting feats notwithstanding, this vessel was equally influential in identifying areas that future subs needed to improve upon. The improvements in submarine technology led to a class of sub designed to combat an extremely challenging adversary, other submarines. Hunter-killer submarines, like the US Navy's fleet of 13 Virginia-class vessels, are designed specifically to attack and sink other craft, above the surface or below. And it's below, in conflict with other subs, where technical superiority is everything. The first thing is detection. Submarines sail blind, dependent on sonar and radar to navigate their way and identify targets. The Virginia class is equipped with an array of sensors to enhance its detection abilities, including thermal imagers, laser rangefinders, and low-light high-resolution cameras. Needing to remain ahead of the competition, upgrades are constantly installed.
Nowadays, submarines have tiles around the outside of the submarine to stop noise going out of the submarine.
Known as anechoic coating, these rubber tiles not only reduce the sound emitted from the submarine, they also absorb sonar pulses, decreasing the Virginia's return signal to any vessels listening in. After targeting an enemy and closing in undetected, the Virginia-class submarine can launch its attack. Fitted with 4 torpedo tubes and 12 missile tubes for its Tomahawk cruise missiles, once the command is given, the game is over for any vessel this hunter-killer has in its sights.
There would be very few places on this planet that could not be attacked by a nuclear submarine. Just even a nuclear conventional submarine, not a nuclear ballistic submarine. With the Tomahawk missiles, cruise missiles and so on, they can fire to just about anywhere on the planet.
And thanks to the 40,000 horsepower generated from its nuclear power plant, the Virginia and its 134 crew can clear the area quickly and quietly with a top speed of 25 knots. Known disarmingly as boomers, these vessels are the culmination of the underwater arms race. With the Cold War driving the proliferation of nuclear weapons, nuclear-powered submarines equipped to carry and launch ballistic nuclear missiles became the most powerful vessels in the world. It was Russia in the 1950s that claimed the dubious honor of becoming the first nation to equip a sub with nuclear warheads. The US was quick to follow suit, and these two superpowers have continued to dominate the deployment of nuclear ballistic submarines.
And the first of the ballistic missile submarines was the George Washington class. The George Washington was the first submarine to fire a ballistic missile from underwater.
Number 2 goes up, described by official observers as a little better than the first, and the first was excellent.
Featuring similar designs to hunter-killer subs, boomers were built larger to accommodate their nuclear missile payload. Beginning service in 1981, the 6 subs of the Russian Typhoon class remain the largest submarines ever built. they can comfortably accommodate their 160-member crews for submerged missions lasting months at a time.
The Typhoon was so big and strong, and it was designed to go under the ice, that one of the concepts of the Typhoon was that it would survive the first strike. The whole object of the deterrence in the Cold War is that nobody would strike because there's no such thing as a second strike.
Launched in the same year, the US Navy's Ohio class may have been smaller, but it came equipped with an overkill of 24 nuclear ballistic missiles, the largest armament ever carried by a submarine. Fired from the launch tube by gas pressure, boomers can project their missiles with sufficient velocity to reach the surface from 50 metres below. From there, rocket motors engage to carry the missiles, along with their multiple warheads, with pinpoint accuracy for thousands of kilometres. With the nuclear-powered submarine's range limited only by food supplies, these vessels can circumvent the oceans virtually without end and virtually unnoticed, posing an insurmountable threat to both sides.
Both the British and the Americans are actually actively, right at the moment, developing the next boomer class. It's still in the early design stage, and it would be highly classified.
To this day, boomers maintain an uneasy stalemate of mutually assured destruction. Just as the nuclear revolution changed what naval vessels were capable of, the rapid evolution of air power changed what naval vessels were for. With early 20th century fighter aircraft boasting greater range and precision than naval guns, a new kind of ship was needed to serve in a new kind of war. While the idea of a ship that could launch and recover aircraft is almost as old as flying itself, this is the vessel that first demonstrated the offensive power of aircraft carriers to the world, HMS Illustrious. Entering service in the British Royal Navy in the first year of the Second World War, HMS Illustrious carried a complement of approximately 1,300 men, along with 36 aircraft. Measuring 225 metres in length, she was not a big ship by modern aircraft carrier standards, and this was by design.
Originally it had capacity for just 14 aircraft, but had the Sea Dart long-range surface-to-air missile. Early in its career, the Sea Dart was removed to provide extra capacity, and then the ship could take about 22 aircraft.
In order that Illustrious protect its valuable payload of planes and aviation fuel against enemy attack, the below-deck hangar was heavily armoured. Placing a great deal of weight high in the ship, concerns over stability meant the hangar was limited to just a single level, essentially halving the ship's carrying capacity to ensure its survivability. Capable of travelling at 30 knots under full load, Illustrious was powered by 3 Parsons steam turbines. 3 drum boilers use a triangular layout to achieve a high rate of evaporation. With 2 water drums below and a furnace in the centre, the steam drum collects the saturated steam on top. Superheaters within the tube bank enhance efficiency by vaporising the remaining water droplets in the wet steam, supplying dry, high-pressure steam to the ship's systems. Using heat to generate steam, boilers preceded nuclear reactors as naval power plants and remain in common usage on ships today. And this is the height of naval power today, the US Navy's Nimitz-class supercarriers.
The Nimitz-class carrier is an American class of nuclear aircraft carriers. At the end of World War II, aircraft carriers grew in size enormously, driven by 2 things. One of them was the jet aircraft. The other was the development of the atomic bomb.
In service since 1975, each of the 10 Nimitz-class carriers stands 20 stories above the water, stretching over 330 metres across it. Capable of carrying 130 aircraft and crewed by a contingent of 6,000 personnel. Each vessel is simultaneously a ship, an Air Force base, and a small city. At the time of construction, the Nimitz-class were the biggest warships ever built. Having served in nearly every crisis and conflict the United States has been involved in over the last 40+ years, these trusty ships are projected to provide the bulk of the Navy's carrier force for at least another 20 years. A big part of the Nimitz-class's longevity is its nuclear power plant. With 2 Westinghouse 4AW pressurized water reactors, each ship generates 190 megawatts of electricity, enough to power 47,500 homes. Capable of operating for 20 years without refueling, these supercarriers use their reactors to drive 4 propeller shafts, achieving an official top speed of over 30 knots.
The advantage of nuclear power in these ships, it gives them in fact the ability to steam at high speed virtually limitlessly. But they have another advantage as well, and that is that if you have a nuclear power plant, you have a great deal more room in the ship for fuel for aircraft and munitions for aircraft.
Certainly people say that the most dangerous place on the planet is on the flight deck on an aircraft carrier, because there's aircraft taking off and landing and you're standing right next to them. If you've ever gone out onto an airport and stood where the aircraft are, you kept well away. But they have to be right next to it. They're manoeuvring the aircraft are turning, and then they're letting it go. And meanwhile, another aircraft is landing. If they step in the wrong place, they're going to get sucked up into the engines or run over by an aeroplane.
While the US government has neither confirmed nor denied the presence of nuclear weapons on its aircraft carriers, the Nimitz-class are known to be equipped with missile defense cannons as well as anti-aircraft and anti-ship missile launchers. Along with the Kevlar armour coating vital spaces, the supercarrier's armament is the last line of defence, and the real protection is provided by the strike force it travels with. Costing around $4.5 billion each to construct. In conflict, this makes them a prized target for the enemy. As such, they never sail alone. Made up of at least 1 submarine for protection from below and several varying warships and supply vessels on the surface, the already intimidating supercarriers are escorted by an equally intimidating strike force to ensure the objectives of their deployment are met. Evolving from aircraft carriers, a new kind of naval transport vessel emerged. One that could extend the Navy's reach from the sea onto the land. The amphibious assault ship. The first amphibious assault ships from the 1950s were converted from small aircraft carriers, and even modern purpose-built vessels bear a strong resemblance in their design. While amphibious assault ships have maintained the ability to transport fighter aircraft, their landing decks are typically used to carry attack and utility helicopters in order to land troops and supplies into hostile territory.
The Wasp-class landing helicopter dock, they're the largest amphibious ship in the world, and they have a combination of a flight deck, large helicopter hangar, a large vehicle deck for all the associated equipment that will be landed, a large troop capacity, and a well deck that can take up to 3 large landing craft.
Located at the waterline in the stern of the ship, the hangar-like well deck is essentially a floodable garage, housing everything from small boats to huge hovercrafts. Dropping its bow door, the well deck lowers to allow water to flow in, enabling landing craft to launch from and dock within the ship itself.
It's really designed for a large amphibious operation. It has quite elaborate command control facilities on board the ship. And also the air-cushioned landing craft, the LCACs, allow the troops to go to the beach at quite high speeds, so up to about 40 knots or 70 kilometres an hour, and that reduces the risks that the troops and stores have during that vulnerable period.
The amphibious assault craft allows the transport of troops, supplies, even tanks from the sea to the shore without the help of a safe harbour. Coming in an array of shapes and sizes, the versatile amphibious assault ship has proven its place in navies around the world. And in military engineering, the quest for improvement is relentless. This experimental craft is part of that quest. Known as a surface effect ship, or SES for short, it combines elements of a hovercraft with a catamaran to achieve enhanced performance. This model, the SES 100B, was built for the US Navy in the 1970s to test the feasibility of the surface effect concept for combat situations. With buoyant twin hulls like a catamaran, the vessel has excellent stability. By employing a hovercraft air cushion, the SES 100B is able to rise up, leaving just a small portion of its hull submerged. Operating almost completely above the water, the SES has achieved speeds in excess of 96 knots. Unlike fan-driven hovercraft, the 100B runs on twin semi-submerged propellers, and the key to its remarkable pace is in the ability of these propellers to achieve supercavitation. With cavitation creating steam bubbles in water, supercavitation takes advantage of the phenomenon by creating bubbles large enough to encompass an object. In this case, the propellers. With the propellers travelling through pockets of air rather than water, skin friction drag is greatly reduced, translating to much higher speeds. But with its rigid hulls, the SES 100B lacked the land-going capabilities of its amphibious counterpart, and whilst having great influence on civilian vessels, never made it into military service. Bridging the gap from ship to shore is the ultimate in amphibious vehicles. Gliding over water and land alike, landing craft air cushions, known in civilian terms as hovercraft, are capable of penetrating over 80% of the world's coastlines. All while carrying up to 180 troops, or even a tank.
So the LCAC is one of the largest of the landing craft that are currently in use. And to give you an idea of its size, it's about 190 tons in weight, and is able to carry about 60 tons of either passengers or equipment.
Serving in the US and Japanese navies, these craft literally fly over mines or shallow obstacles that would disable traditional hulled landing craft. And with their tremendous over-beach performance, landing craft air cushions, LCACs for short, can land just about anywhere, making them incredibly difficult for enemy forces to defend against. Powered by 4 gas turbine engines, LCACs rest on a rubber skirt which serves to trap a cushion of air under the craft, holding it high above the waves and any obstructions on the land.
Its main purpose is to take troops, soldiers, from an amphibious ship that is over the horizon and get to the shore as quickly as possible with the largest load of troops as possible.
With its 4 turbines providing close to 19,000 horsepower, LCACs can maintain speeds of over 40 knots for more than 320 kilometres. They can also carry payloads of up to 75 tons. While this carrying capacity and speed makes them ideal for rapid insertions of troops and hardware, the light touch of their air cushion also allows them to serve in mine countermeasure operations. But LCACs do have their drawbacks. Noise and spray levels are high, limiting the hovercraft's use in stealth missions. And akin to manoeuvring a puck on an air hockey table at highway speeds, handling is exceedingly difficult. With a turning radius of nearly 2 kilometres and requiring over 450 metres to stop. But this experimental craft could be the US Navy's ultimate solution in connecting sea to shore. The ultra-heavy lift amphibious connector, UHAC for short, is a half-scale prototype of the vessel that may replace the Navy's hovercraft fleet. Essentially a floating tank, the UHAC runs on 2 tracks comprised of dozens of dense air-impregnated foam blocks that provide buoyancy as they paddle through the water and traction as they roll across the land. While about half the speed of the current fleet of landing craft air cushions, the full-scale version of the UHAC is proposed to carry loads more than twice as heavy and travel twice as far. And with the ability to scale obstacles as high as 3 metres, the UHAC is set to extend the Navy's reach even further inland. Today, the large-scale naval technology is giving way to smaller and smarter systems of control over the seaways. This is the Sea Hunter. An experimental, unmanned vessel from the Defence Advanced Research Projects Agency. It is poised to patrol the open seas for the US Navy, guarding against intrusions from enemy subs. With its trimaran design, affording excellent seaworthiness even in the roughest conditions, the Sea Hunter will brave the oceans alone, maintaining a constant vigil.
So the trimaran shape definitely has advantages in seakeeping. You can have a very, very slender central hull and the outer hulls set back, so it can have advantages with the seakeeping performance of those vessels. By making the hulls extremely narrow, then you can reduce the amount of power required to propel those vessels going forwards.
Running on diesel propulsion, the craft's top speed of 27 knots allows it to keep pace with sprinting subs, and its transoceanic range of 19,000 kilometres means it can follow its quarry for up to 90 days non-stop. Highly autonomous, the unmanned Sea Hunter can patrol without human input, using optical guidance and radar to reliably avoid obstacles and other craft. Operationally, it will be observed and controlled when necessary by a remotely stationed human. Unarmed, the Sea Hunter's power is in its ability to detect even the best hidden vessels. Mid-frequency sonar will locate long-range targets, with high-frequency sonar refining tracking once the Hunter closes in. Built from lightweight radar translucent carbon composite materials, the Sea Hunter will be near invisible to the submarines it stalks. Ruling the waves with intelligent automated technology, the Sea Hunter is a vision of the future Navy, a future that is already upon us. From the age of sail to the age of steam, from battleships to aircraft carriers, and nuclear subs to alternative and autonomous craft, naval vessels have kept pace with the great technological shifts in history. And today, as ever, the naval forces remain at the ready, anticipating the next leap in seagoing power. The sea is where life on Earth began, and for man, himself a product of the sea, the journey to explore and better understand this primordial world is in many ways a journey of self-discovery. With waterborne craft the oldest vehicles known to history, the sea has driven invention since ancient times and continues to drive it today. In this episode, we set sail from the hydrofoiling catamarans that forever changed the America's Cup to the often fatal quest to set motorised water speed records, and from the unstoppable power of nuclear icebreakers to the unseen potential of interstellar solar sails. This is the story of sea power. Over 70% of the planet we call Earth is covered by water. And more than 96% of that water is contained in the sea. Beautiful and ferocious. The sea is a world unto itself, a world of legends and awe-inspiring power. Power that we have sought to harness, and power that we have done our best to withstand. Yet for the remarkable advances that have carried us further and deeper, we have barely scratched the surface of this mysterious world. And 95% of it remains unseen by man. This experimental craft is seeking to create a completely new mode of waterborne travel. Mimicking the anatomy of water-skimming insects, this Wave Adaptive Modular Vessel, or WAM-V for short, has already earned the nickname Spider Boat. Designed by Italian engineer Ugo Conti, this scaled-down model is testing the radical technology for smoother, more efficient motion on the water, with the ultimate craft set to be a total of 29 metres long. With titanium shock absorbers mounting the 4 legs that connect the superstructure to the catamaran outriggers, the WAM-V is able to travel with the movement of waves rather than through them. Skimming over the water for incredible fuel efficiency, the full-scale Spider Boat will carry more than 7,500 litres of fuel in its outriggers. And set to be powered by twin Cummins Marine Diesel Quantum Series engines, the final craft will be capable of crossing the Atlantic Ocean with an impressive top speed of 30 knots. With inflatable hulls, the Spider Boat can be beached without damage. Its unique properties allow the craft to fold down for easy hauling out of the water. Designed to carry a range of modular cabins, the Spider Boat is built to allow a range of interchangeable uses, theoretically switching from research operations to rescue work quickly and easily. Fast, efficient and versatile, the WAM-V has already attracted interest from the US Navy. While experimental today, Spider Boat technology may be commonplace on the waters of tomorrow. Rising up above the water to cut down on surface drag and boost speed, these are boats that fly.
It's an amazing thing to watch, and it's an amazing thing to be involved with some of the engineering and what's called the Moth International Sailing Class dinghy. They've been hydrofoiling since the early 2000s.
And it is these small single-sail, single-person yachts that did more than any other to demonstrate the technology, hailed among the most revolutionary developments in marine engineering. The hydrofoil. Like the aerofoil design of an aeroplane's wings, hydrofoils serve to generate upwards lift.
The first thing you notice once you come up on the foils is everything goes quiet. It goes completely. I mean, you don't get this slap, 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 slap on the water. It just goes quiet. And it's like, what happened?
As the craft gains speed, the angled shape of the foil creates different pressure systems in the water, essentially accelerating fluid downward to drive the hydrofoil, and the boat up. With the bulk of the craft now travelling through the air, an environment approximately 1,000 times less dense than water, the resistant force of drag is drastically cut down, translating to an increase in efficiency and therefore speed.
It's just lifted out of the water and the drag reduces by probably a factor of 5 and accelerates. And once it accelerates, you're actually moving through the wind faster as well. So you're actually harnessing more of the wind, because as you move through the wind faster, you can actually grab more power out of the wind.
First tested on motorised boats in the late 19th century, while hydrofoils proved successful in enhancing efficiency, the complexity and cost they added to construction prevented a wider adoption of the technology in large motorcraft. Small-scale racing yachts had more freedom and incentive to experiment, and it is in the moth class that hydrofoils have really made their mark. Upscaling the hydrofoil technology developed by the smaller moth class, the new generation of racing catamarans have made the next leap in power. Capable of travelling at more than twice the speed of the wind, these boats turbocharge the most hotly contested race in sailing, the America's Cup.
So in 2013, the America's Cup reinvented itself and made 72-foot catamarans weighing about 6 tonnes each.
Thanks to their wide multi-hull design, catamarans can accommodate a greatly expanded sail area while maintaining a lightweight, stable platform, making them the ideal vessel for hydrofoiling. Nonetheless, each of the carbon fibre hydrofoils must be able to withstand pressures of around 15 tonnes, more than twice the weight of the vessel, while maintaining a thin profile about the size of a surfboard.
We can now construct composite components on very high stiffness and very high strength and very, very low weight, which is exactly what we need to make these hydrofoil boats fly.
And it's in flight that these remarkable craft are achieving unprecedented speeds for sailing vessels.
And eventually the entire hull is out of the water, so we've got these large 6-tonne vessels being completely supported by hydrodynamics. That allowed those vessels to go from, say, 30 knots up to almost 50 knots very, very quickly.
Beyond the benefits of speed, the durability of the vessel may also receive a boost. Rather than slamming and crashing their way over the waves, hydrofoils travelling above the water are placed under less structural stress than traditional craft. These gains are not without losses, and there are concerns as to whether the power of these vessels is simply too much for a sailboat to possess. However, with the transformation of the America's Cup into something closer to F1 racing on water, the pursuit of speed shows no sign of slowing down. Combining speed with comfort, these commuter ferries are the Concords of the water. Australian manufacturer Incat has revolutionised the catamaran design to achieve the remarkable distinction of building some of the fastest ships in the world.
Well, a catamaran's a very old form of marine transport, of course. It's been around for thousands of years, one way or the other. Typically, catamarans are long and skinny hulls, which on their own would not be very useful, but when you put two hulls together, you get a nice big wide platform, which is very good for carrying light cargo, people, motor cars, etc.
Catamarans are ballast-free and therefore lighter, with lower hydrodynamic resistance than usual monohull ships. Because of this, they require less propulsive power from their motors, resulting in a very fast ship.
The boats today are replacing monohulls left, right and centre because they're more economical, they are lighter, they are wider, bigger, etc.
Incat has built a reputation on manufacturing these super-fast ships. In fact, Incat has built the last 3 consecutive winners of the Blue Riband, the prestigious award for the fastest crossing of the Atlantic by a commercial passenger ship. To date, they have built over 90 catamarans. The extraordinary speed of their vessels is attributed to 2 factors: state-of-the-art design and exceptional power. Their catamarans' long, thin hulls have a reduced buoyancy so as to pierce through waves rather than ride over them, providing a smoother, more comfortable ride for their passengers, as well as reducing mechanical stress on the vessel. Incat's fastest catamarans are powered by gas turbine jet engines, modified to breathe water rather than air. With water entering the jet units through intakes on the bottom of the boat, the engines accelerate and fire the water backward at high velocity, forcing the vessel forward in the same way a jet propels a plane.
A lot of the power of a normal propeller is lost off the tips. It goes sideways off the tips of the propeller. If it's in a tunnel, that power is more contained. So water jets are more complex, but generally at high speed more efficient.
With advanced acceleration over propellers, water jet propulsion affords high efficiency at high speeds and excellent manoeuvrability for docking at low speed, perfect for a quick commute and an easy disembarkation. When it comes to moving non-human cargo, the economy of scale has driven the development of true giants of the sea. And with big ships comes big engineering challenges and even bigger power. Giant container ships, or box ships as they are affectionately known, are the unsung heroes of mechanical engineering. And among these waterborne leviathans, it is the Maersk Triple E class that are the most advanced in the world. "400 metres long and 59 metres wide. The Triple E class is only a few metres larger than a standard box ship. But thanks to a clever layout, they can carry an additional 2,500 containers. In transporting their enhanced load, it is the slow and steady technique of the Triple E class that wins the race.
The vessel needs to actually float in a different position and orientation in the water, so that its hydrostatic forces are changed remarkably from when it has nothing on board to when it has everything on board. And the engineering actually needs to adapt to that. When a large bulk carrier is being filled, there's a very definite and very specific way that the weight needs to come on board. If it comes on board in an incorrect way, the ship can literally break in two, because the structure is not designed to carry that load in a particular condition.
While most container ships cruise at around 25 knots, the Triple E class are designed to use a technique known as slow steaming, running at an optimal speed of around 19 knots. Reducing fuel consumption by close to 60%, the slow steaming Triple E class can transport more containers with less power. But on this scale, going slower is not just a matter of easing off the throttle. The first challenge is finding engines that can run with slower revolutions. The Triple E class settled on twin two-stroke diesel engines, each with an ultra-long stroke. Fitted with a waste heat recovery system, the engines use their own exhaust gases to comfortably produce a total of 86,000 horsepower. But having efficiency in an engine is one thing, retaining it in a propeller is another. Propeller size is limited by the draft of the ship, the distance from the water surface to the lowest part of the hull, with the Triple E class requiring a propeller with a diameter larger than its draft. They opted for what's known as a twin skeg system, using two smaller propellers to achieve the combined diameter needed for maximum pushing power. And while a standard large propeller has 6 blades, two smaller propellers can each have 4. Less blades means less resistance, and less resistance means even better efficiency. At sea, big ships have plenty of room to operate. But when docking or departing from the confines of a port, they often require some gentle persuasion. Built to push around vessels more than 1,000 times their size, tugboats have an extreme power-to-weight ratio. Compact craft with disproportionately large engines, they are the muscle cars of the marine world. And without them, megaships would never be able to dock. with their oversized engines producing upwards of 27,000 horsepower. Tugboats pack a lot of punch.
The size of the engine compared to the size of ship is huge. So they can basically push or pull. They can either push with a rubber fender or they can put a rope to the ship and pull the ship.
And with a narrow margin of error between a successful docking and a hugely expensive crash, most tugboat engines feature 2 of each critical part to guard against failure. But being powerful and fail-safe isn't enough to pull and push 100,000-ton ships through narrow waterways. Tugboats need to be agile, making them half sumo wrestler, half ballerina. Most modern tugboats derive their agility from azimuth thrusters, propeller units capable of rotating a full 360 degrees. With the propeller directing thrust, the need for a rudder is eliminated. The addition of ducted shrouds, known as court nozzles, around the propellers provides enhanced efficiency. Directing the water entering and exiting the propellers into a linear configuration, the tugboat's thrust-to-power ratio is given a helpful boost at low speeds, right when they need it most. With most tugs confined to sheltered waterways, seafaring is not a priority, and their hulls have evolved a heavy displacement design to suit their purpose. Already low-riding vessels, when a tugboat powers up, its hull sinks even further into the trough of its own wake. In the exact opposite of a hydrofoil, this sinking effect provides more contact with the water. More contact means more friction, and when shoving oversized ships around, the more resistance a tugboat has against the water, the better.
It's difficult to predict the trajectory of a ship, given not just the control forces involved from the propeller and the rudder, but also from environmental effects such as wind or current. And so all those effects come into play. So the tugboats are used to mitigate any problems. For example, if a ship were to run aground, then it would be a major catastrophe in a port because the port wouldn't be able to operate.
A triumph of power and design. As mega ships continue to grow, the dependable tugboat will be there to shoulder the burden. While the transport of cargo has given rise to megaships, so too has the transport of people. For hundreds of years prior to the development of long-range aircraft, ocean liners were the dominant mode of travel between continents, driving the development of seafaring giants. With the travel industry powering the construction of ships, each bigger and more excessive than the last, this growth has not been without disaster. Once the biggest moving vessel ever made by man, today, the RMS Titanic looms large from its grave beneath the waves as the most infamous ship in history. This is all that's left of the vessel that was once celebrated as being unsinkable.
Titanic was built by Howland and Wolff in Belfast in Northern Ireland. She was about 47,000 tons, not particularly a big ship. The present famous liner, Queen Mary II, the Cunard line, for example, is 3 times the gross tonnage of Titanic. But she and her sister ship, Olympic, and the still under construction Britannic, were the largest ships on the North Atlantic.
Departing to great fanfare on its maiden voyage from Southampton, England to New York in April of 1912, the Titanic set sail with approximately 2,240 passengers and crew aboard. Powered by a combination of 2 reciprocating 4-cylinder triple expansion steam engines and a single steam turbine, the ship produced a total of 46,000 horsepower. With steam produced by 29 boilers, 600 tons of coal needed to be shoveled by hand each day. offering the highest levels of comfort ever seen in commercial transport. While the Titanic's first-class accommodations and services stole the show, even those travelling in third class, by far the largest group aboard, enjoyed superior amenities than any other ship of the era. Four days into its voyage across the Atlantic, the Titanic received warnings of drifting icebergs from other ships in the area. Not considered a serious threat to a vessel as large and as advanced as the Titanic, the doomed passenger liner continued at its full speed of around 22 knots until moments before the jagged underwater spur of an iceberg struck its starboard side.
The iceberg cut a series of quite small holes into the shell plating of the ship below the waterline. Had those holes been in one compartment, there wouldn't have been a problem. They certainly wouldn't have arrived in New York on time.
Following the collision with the iceberg, the seams of the buckled hull separated to allow 5 of its 16 watertight compartments to fill with water. The ship could only survive the flooding of 4. Although exceeding the safety standards of the day, the Titanic carried only enough lifeboats for 1/3 of its total capacity. And in the haphazard abandoning of the ship, these precious few lifeboats were launched underfilled.
The Titanic tragedy left such a mark on everybody throughout the world, because how could something like that possibly happen? Well, it can, and it did under those circumstances.
"20 years after the sinking of the Titanic, the next big thing in ocean liners took to the seas. 10 years later, it too would meet an untimely fate. Launched in 1932, the SS Normandy was the ocean-going pride of France. With its revolutionary hydrodynamic hull and lavish Art Deco stylings, the ship was heralded as the greatest passenger liner ever created. And featuring an advanced transmission system to address the shortcomings of traditional direct-driving steam turbines, the Normandy remains the most powerful steam turbo-electric propelled passenger ship of all time. Running on more conventional steam turbines, the RMS Queen Mary boasted what is probably the largest powertrain ever built aboard a ship.
In 1931, all work at the John Brown shipyard was suspended for 3 years. Ship number 534, as she was then, sat there rusting for all that time until work was resumed.
A great day for Clydeside. Work is resumed on the Cunard number 534. It is hoped that the liner will be ready for launching this autumn.
It was resumed and she was completed in 1936, having been launched as Queen Mary. She was 1,019 feet long and about 81,000 tons gross. A large, elegant ship and the biggest liner in the world at the time.
With the majority of space on its lower 5 decks occupied by boiler rooms and engines, the combined output of the 4 Parsons steam turbines allowed a whopping 160 horsepower, allowing the Queen Mary to wrest the blue ribbon from the SS Normandy in 1936.
Now, after 7 years, the Queen Mary has recovered the honour and arrives at Southampton to be hailed in triumph by Britain. Well done, Queen Mary.
While the Normandy reclaimed the honour the following year, the Queen Mary won it back by setting new transatlantic records in 1938. Records that remained unbroken until the early 50s.
Queen Mary could achieve 30 knots, but the service speed across the North Atlantic was generally about 27 knots. You kept power and reserve in those ships in case of bad weather so that you could make up time, because this was very much a scheduled service. You needed to arrive and depart at the right time. And that's a great speed in those mighty ships crossing the North Atlantic.
Undergoing a successful conversion to military service during the Second World War, the passenger liner cum troop ship survived the conflict unscathed. Often travelling without escort, the Queen Mary simply outran the threat posed by enemy vessels. And during one Atlantic crossing with over 16,000 American servicemen aboard, she set another record: most passengers ever transported on a single vessel. The rise of affordable and fast jetliners changed ocean-going travel forever. Unable to compete on speed or economy, passenger liners needed to offer something that air travel could not. This is what they came up with: the MS Oasis of the Seas. The first of the Oasis-class cruise ships, she, along with her two sisters, represent the largest passenger ships in the world.
Amongst the largest cruise ships in the world are the Oasis-class cruise ships, which have recently been built, and they're 225,000 gross tonnes, which is a very large ship indeed, with a very large passenger carrying capacity.
With 16 passenger decks, the Oasis towers 72 metres above the waterline. Powered by a combination of 3 16-cylinder and 3 12-cylinder marine diesel engines, the Oasis pumps out over 130,000 horsepower. These engines not only drive the 3 electric azimuth thrusters for the ship's propulsion, but provide electricity for its lights, elevators, water treatment plant, and all other systems needed to keep the residents of this floating city comfortable and entertained. Seafaring on this scale poses a big engineering problem. With rough seas capable of battering vessels from all sides, mega ships like the Oasis class are subjected to even greater stresses as its gargantuan structure faces uneven strain across the uneven water. The Oasis withstands these shifting stresses not by force, but by calculated give and take. With its cage-like internal framework allowing a significant amount of movement, the Oasis, like all big ships, constantly bends, sags, and twists by design. Spread across the entirety of its megastructure, the degree of movement in this surprisingly limber vessel is barely perceptible to those on board. Not everyone on the water is content with pleasure cruising, and the need for speed has had as powerful an influence on sea travel as it has on travel through air and on land. With water imposing greater uncertainty and greater resistance in the form of friction, the quest for speed here is not only difficult, but dangerous. Of those brave or foolhardy enough to launch an assault on the water speed record, over 3/4 have lost their lives. By 1930, with official rules set, the water speed record had become a source of national pride, hotly contested between Britain and America. This boat, the Miss England II, was to claim the honour for the Brits, but at great cost. With a twin-bladed screw propeller powered by twin Rolls-Royce V12 air racing engines, the Miss England II featured a single keel with a stepped hull to reduce friction and drag. With longitudinal notches running beneath the hull, as the boat gains momentum, these steps create a suction effect, drawing air in from the sides to generate lift. Raising the boat to reduce the wetted surface area, the area of the boat in contact with the water, stepped hulls improve efficiency, allowing more speed with less horsepower.
As a powerboat goes faster, if the design is in such a way that you can actually use some of those hydrodynamic forces, such as a very large surface for planing, when the water actually hits that surface, it gets deflected downwards and can actually make a significant vertical hydrodynamic force and literally lifting the entire boat out of the water in the same way that we talked about with the hydrofoils.
On the ominous date of Friday the 13th of June 1930, pilot Sir Henry Seagrave, along with his mechanic and chief engineer, set out on Lake Windermere to chase down glory. During 2 successful runs, they averaged a speed of over 85 knots, nearly 160 kilometres per hour. With a new record in hand, the third run sought to push the average even higher, but ended in disaster. With the boat thought to have struck a floating branch, when the spray from the crash cleared, the engineer was dead. While the mechanic survived with a broken arm, Seagrave regained consciousness just long enough to ask the fate of his men before dying from acute lung injuries. Salvaged and repaired, the boat itself went on to set new water speed records throughout the early 1930s. But as the race continued, it was to be rendered slow by a new breed of speedboat. In 1955, this boat, the world's first successful jet-powered hydroplane, started a revolution in speed. The British-built K7 Bluebird reigned over the water for more than a decade, setting 7 world records and adding nearly 160 kilometres per hour to the target. Nicknamed the Blue Lobster for its forward set of stabilising sponsons, the K7 Bluebird was representative of the departure from single-keel speedboats to a 3-pointer hydroplaning design. Operating on the same principle as a hydrofoil, at speed, the Bluebird generated sufficient lift to raise the majority of its hull out of the water, minimising drag to maximise speed and efficiency. Constructed with a lightweight aluminium body, the K7 was built around an ultra-rigid steel frame and powered by a Metropolitan Vickers Beryl turbojet engine that produced a whopping 16 kilonewtons of thrust. Developed by British speed demon Donald Campbell, the first person to set both land and water speed records in the same year, the K7 was both his glory and his downfall.
Once you start going at these very, very high speeds, a very small change in that force balance could create quite a catastrophic change in how the boat's going through the water.
Modifying the Bluebird constantly throughout his career and piloting it to even greater speeds, it was in the bid to set his 8th water speed record that Campbell paid the ultimate price. With his sights set on being the first to break the 300 mile per hour mark, a goal that meant increasing his current record by over 40 kilometres per hour, Campbell took to Coniston Water in the English Lake District in 1967. Now under the power of a lighter and more powerful Bristol Siddeley Orpheus engine boasting 20 kilonewtons of thrust, Campbell's initial run was just below his 300-mile target, averaging 479 kilometres per hour. His second dash was even faster. But when travelling at an uncharted speed of over 510 kilometres per hour, the craft began lifting from the surface, ultimately going beyond its critical pitch and taking off from the lake before cartwheeling to a violent stop. Campbell was killed instantly. Above and below the surface, the sea is a world of extremes. To carry us further on and deeper into the sea, we have to develop vessels that are equally extreme, penetrating some of the most inhospitable places on the planet.
The ocean surface is ever-changing, and it creates an environment that I would suggest as a naval architect means that putting structures into that environment that is one of the most challenging engineering opportunities we have as modern scientists and engineers.
Icebreakers are among the most robust vessels on the sea. Operating where others fear to tread, they clear the path for merchant vessels needing to transport cargo through frozen trade routes, as well as conducting research missions in Arctic and Antarctic waters.
Suppose the sound of a ship breaking ice at speed is like living inside a coffee grinder or something. It's incredibly loud, and it's accompanied at the same time by the motion of kicking back and forth, because even if the ship is going fast and breaking ice very efficiently, it's still being buffeted. And you can feel it. You can feel it, and it's intense.
Since the age of sail, ships operating in the polar regions have been built with various measures to combat ice. But the modern steam or petrol-driven icebreaker took shape in the early 20th century. While design has continued to evolve and breakthroughs, both literal and figurative, continue to be made, perhaps the most significant advance was the incorporation of nuclear power. Launched by the Soviet Union in 1957, the NS Lenin was not only the world's first nuclear-powered icebreaker, but the first nuclear-powered surface vessel. Raw power counts for a lot when coming up against a substance with roughly the same tensile strength as concrete.
Crunching and crashing her way through the frozen Arctic, the Russian atom-powered icebreaker Lenin was on an unusual assignment.
And the ability to run continuously for years without refueling is a great advantage when operating in some of the most remote regions on the planet. Today, the nuclear-powered variety of icebreakers remain the most powerful, and all of them are Russian. In terms of design, for icebreakers, hulls are everything. Built with double hulls to ensure integrity against the increased loads placed upon them, they are constructed with a particular grade of steel, resistant to brittle fracture in extremely cold temperatures. The sloping shape of the icebreaker's bow allows it to be driven up on top of thick ice, where the weight of the ship presses down to break it apart. Also in the icebreaking arsenal can be a bubbler system, which forces compressed air through holes in the bow to form a cushion of air between the ship and the ice. If the ship becomes trapped, a healing system can be used, pumping tons of water from one side of the ship to the other in order to rock it free. And with abrasion-resistant coating, the last job of the icebreaker's hull is to safely clear broken debris, forging a path for others to follow. The crushing, pitch-black waters of the deep sea remain the least explored region of our planet. And the safest, most efficient way of venturing to these mysterious depths is with unmanned craft. Remote-operated vehicles, ROVs for short, represent a new breed of sea power. Considered the Swiss Army knife of underwater robots, ROVs have applications in everything from surveying wrecks to military mine hunting.
Tethered systems have a wire going back to a control, and the person controlling it will look through a camera or a sonar system and then detect, see what it is, and then they'll make the decision what needs to be done and they'll bring it back.
By far, the greatest use of ROVs is in scientific research, shining a light into some of the planet's most challenging and poorly understood waters. Operated by the US-based National Oceanic and Atmospheric Administration, the Deep Discoverer, nicknamed D2, is a cutting-edge ROV, bringing us closer than ever to the mysterious biology and geology of the deep sea. Operating in tandem with a camera sled unit serving to illuminate the D2 and provide a wide-angle view for the topside pilots, the Deep Discoverer is connected to its launch ship by an umbilical cable. Neutrally buoyant, this cable effectively separates the ROV from the motions of the ship whilst powering the D2 and instantly transmitting its data back to the surface. With its high-definition camera and specialised robotic arm for sample collection, D2 is providing scientists with a clear look at environments that have never been seen before. Constrained by their connection to a ship and the stamina of their human handlers, ROVs provide a detailed but limited picture of the ocean. But it is autonomous underwater vehicles, AUVs, that offer a broader understanding of the vast marine world. Once programmed for their long-range missions, these vehicles are let loose, returning to base on their own once the assignment is complete.
When things are under the water, radio waves don't transmit under the water. So you either have to use sound or they have to be pre-programmed and they'll come up to the surface and then do a radio transmission or go back under, and that's where autonomy is really important. So it gets told what it needs to do and it can make decisions while it's down under there.
While AUVs are in keeping with the trend toward autonomous craft in the air and on the roads, in the aquatic environment, a greater degree of engineering challenges needed to be overcome. The first was communication. With radio waves unable to travel very far through water, unmanned underwater vehicles had to get smart.
When they detect something or on their preset pattern, if something's in the way, it can then make a decision to reprogram itself for what search pattern it needs to go on or what it needs to look for. So it has a limited level of artificial intelligence.
Travelling without GPS and with minimal contact with human handlers, AUVs navigate via sonar or dead reckoning calculations, with many changing their mission profile in response to the environmental data they collect and analyse. The high drag inherent in water means that propulsion is another challenge. Typically running on long-range electric motors, AUVs tend to employ efficient propellers, often with ducted quart nozzles. For even longer stints at sea, underwater gliders use their aerofoil wings to convert the vertical motion of repeated ascents and descents into horizontal propulsion.
They can either look like an aircraft or some of them look like just simple torpedoes. They have a device in there that simply changes the buoyancy from one end to the other, so it just pumps a little bit of liquid in a tube forward and back. And what that does is change the buoyancy of the system so it starts to sink. So this thing will dive down. When it gets to a set depth, it changes the buoyancy back and it just comes back up. So it's actually gliding in the ocean.
Innovating to meet the challenges imposed by the sea, AUVs are at the forefront of the modern quest to better understand the ocean.
Part of their mission is to go to places we haven't been before, to help us collect data that we haven't been able to collect in the past, to collect samples that we don't already have, and to fill in our understanding about how things look, what their history is, why they work the way they do, and what the future holds.
And the innovations do not stop with the sea. The technology developed here is powering travel beyond the waves and beyond the planet. A planet-detecting satellite launched in 2009, the Kepler spacecraft's mission was to monitor the brightness of distant stars within the Milky Way. With its high-powered photometer, Kepler was set to keep watch for the periodic dimming around stars that would indicate the orbiting of potentially Earth-like planets outside our solar system.
What is really cool about this telescope is how it's actually controlled in space. It is literally floating through space. It is being steered through space like a sailboat.
Aiming and stabilizing its photometer via a series of 4 reaction wheels, when 2 of these wheels jammed, the mission was on the brink of failure. But one radical idea offered a solution, a concept first dreamed up by the 17th century astronomer for whom the Kepler spacecraft was named. By harnessing the power of solar winds, the pressure exerted on spacecraft by photons within sunlight, the Kepler could be stabilized against this force.
We point Kepler at a direction of the sun so that as the wind comes from the sun, it keeps it in spot and keeps it pointing. So as Kepler moves around the sun, we keep pointing it so that sail is pointing at the wind of the sun.
It was harnessing the solar wind that steadied this craft, allowing it to continue its planet-hunting mission. While the Kepler became a solar sailboat out of necessity, spacecraft like the light sail are doing it by design.
So this is a giant satellite that's going to deploy a sail. They want to point the sail at the sun, and when a big burst of wind comes from the sun, push it, and that will accelerate the satellite through space.
The light sail aims to be the first controlled solar sail in the Earth's orbit, testing the viability of the technology for transporting scientific payloads, potentially even human passengers, through space. Launched by conventional rockets, once in space, the light sail unfurls its 32 square meters of reflective mylar sail. As the photons of sunlight continually hit and bounce off the sail, they transfer their momentum, propelling the spacecraft in a similar manner to a sailboat on a sea. But unlike the water, the vacuum of space offers no resistance to movement, and a solar sail is able to constantly accelerate, theoretically building speeds 5 times faster than rockets.
In space, there's nothing to stop you. So once you're going, there's no air, there's no wind. So if you can get a burst of speed, 20% the speed of light, you can get a satellite that goes through space 20% the speed of light. So we can actually have interstellar travel in only a few decades with the same technology and same style of boat goes through the ocean.
Reimagined, the ancient engine that is the sail is set to gracefully carry us further than ever before, opening the door to new galaxies. Power. Brute power, belching from a smokestack or roaring from a diesel. The power to cross continents, move armies, destroy distance. Artists, writers, poets, everyone seems to have found the greatest fascination and the greatest romance in the powerful engines they have watched cross bridges, climb mountains, and drive through the heart of cities. The romance of trains. The story of rail travel is the story of huge loads, extravagant luxury, and astonishing speed. For century after century, the power to move ourselves, our goods, our crops, our armies was generated by our own muscles or the animals we could harness. And then came steam. In this episode of Power, we explore the greatest steam engines that crossed continents and tell the story of how the rails, bridges, and tunnels on which they ran changed the world. This is the story of rail power. The steam locomotive. Wherever it ran, stopped enthusiasts and small boys in their tracks in its heyday and still exerts a very special appeal. Perhaps more than any other machine, the steam locomotive says power. The Bayer Garrett 6029, a workhorse loco from the 1950s, was manufactured in Manchester, England for heavy goods service. Number 6029 pulled its loads around Eastern Australia for the New South Wales government. And fully restored is the largest working steam loco in the Southern Hemisphere.
The Bayer Garrett is 265 tonnes fully loaded. Fully loaded includes 40 tonnes of water. Now, this locomotive burns through 430 litres of water a minute. So to go anywhere of a reasonable distance, it needs a lot of water. Also needs a lot of coal. It goes through 37 kilos of coal a minute at full power. In fact, it goes so quickly through the coal that a fireman couldn't shovel it fast enough. The draft is so strong in the fire that it would suck the shovel out of the fireman's hand. And so it has an automatic stoker to draw the coal through from under the tender, to pulverise it on the way through, and then jets of steam are used by the firemen to fire it round a firebox, the grates which are the size of nearly 4 grand pianos. And so everything's on a massive scale. And you get up in that cab and it's almost intimidating how big this machine is.
In service for 20 years, the 6029 incorporated the most modern technology of its time, hauling export coal to the ports, or concentrate from the mines, and goods from all over the state.
It certainly has its own sort of personality with its noise. It's so noisy that the drivers have to have loudspeakers placed in the cab. They had to put megaphones in. Going through tunnels, they had to have leather jackets and hoods over their heads to protect them from the heat. It was really out in the fringe. It's sort of like, you know, being an astronaut in our times. You were really riding a big machine.
The power to move mountains or populations is no longer supplied by steam. Modern trains look faster, much sleeker. But the Bayer Garrett remains a formidable expression of power. The first trains to be hauled along rails did not even have the benefit of steam. Horse-drawn and man-powered trucks took advantage of the lower friction of pulling loads along rails. Steam brought power to the railways when pioneers like Watt and Trevthick made steam engines practical.
What was going to be the most effective way to move people by rail? Should it be horsepower? Should it be steam power? Should it be this? Should it be that? Should it be dragged by ropes, chains, whatever? But steam, with Robert Stephenson's extraordinary technological advances, with the creation of locomotives like the Rocket, won the day.
The history of steam power stretches back 2,000 years. 2,000 years of development. But the principle of steam power has remained constant. A steam engine uses heat to produce a gas that powers mechanical work. The gas is steam, which is produced by applying heat to the working fluid, typically water. Heat can be produced by burning any fuel. In steam locomotives, typically coal and sometimes wood. The water separated from the combustion is heated in a boiler, where at high pressure, it expands through pistons to power the mechanical work. Then, men like Stephenson and trains like the Rocket transformed life and with bridges, tunnels, stations and permanent way, transformed the landscape.
The Rocket was one of the locomotives that he built of a series that won the Round Speed Trials, which then led to the first public passenger railway, 1830. That led to a revolution. By 1835, Germany had opened a railway, America was opening up, 1837, Russia, on it went. The railway age and the railway revolution changed the world.
The Rocket seems to us today to have been a rather ambitious name. Its maximum speed was 45 kilometres an hour. At the time, such propulsion seemed beyond reckless, but people survived the journey, and the age of rail was born. Trains were first made to carry freight to compete with the canals. The first lines brought power to horse-drawn railways or tramways that had been hauling tin or coal or iron out of mines. But with the Industrial Revolution and the migration to and growth of the cities came a mobile population. And the beginning of the story of famous trains, romantic names like the Flying Scotsman.
The Flying Scotsman's probably one of the most iconic steam trains ever built. 1923, the early 20s, we're seeing the golden age of railways and particularly steam traction. And you have one of England's great designers, engineers, Nigel Gresley, coming up with a design that sets a new benchmark for steam passenger locomotives.
The route was operating by the 1860s, but the name was not attached until 1923. 630 kilometres, linking the Scottish capital Edinburgh to London. The Flying Scotsman is a name that had been carried by some of the most powerful steam locomotives and is carried today by their modern successors. The classic Flying Scotsman, the first loco to carry the name, is the LNER, London and North Eastern Railway, Class A3. Built in 1923, the first steam locomotive to officially reach 100 miles an hour, 160 kilometres per hour. With a coal capacity of 9 long tonnes, the A3 could complete the journey without refuelling, and was retired from regular service in 1963, having clocked up more than 2 million miles, 3,220,000 kilometres.
Romantically, but certainly from an engineering point of view, the Flying Scotsman remains an icon, a symbol of progress.
The most famous of them all, the Flying Scotsman, the epitome of all that a massive steam engine should be: noble, powerful, fast. A champion bearing the torch for an age that will never come again.
But it's another LNER locomotive, the A4 class of 462 bogie arrangement that followed the A3 into service in 1938, that best captures the power and romance of steam. Particularly an engine named Mallard. Wind tunnel tested and aerodynamically designed, the Mallard was intended to haul high-speed trains and still holds the world record for a steam locomotive, 200.4 kilometres per hour, which was perhaps the limit for steam. The Mallard had a 3-cylinder engine and repeated problems with the middle cylinder overheating. To alert the driver to this problem, a stink bomb was fitted to the middle cylinder, which popped on overheating, alerting the driver through the offensive smell of hot aniseed oil. And the bomb went off shortly after Mallard broke the record. Neither as fast nor as streamlined as Mallard, but significantly more powerful, and with an appearance that totally justifies its name, is this North American steam locomotive. This is Big Boy. The 4000 Class 4884 articulated Union Pacific monster of the 1940s. The only locomotives to feature the 4884 arrangement, which gave stability negotiating curves.
The Big Boy in America just makes the ground shake when you think about the zenith of rail technology because of the size of the thing. And nothing has beaten the Big Boy in size or scale.
Big Boy was designed to haul freight over the Wasatch Mountains between Wyoming and Utah. To get the job done, Big Boy, where the A3 Flying Scotsman had a coal load of 9 long tons, had a fuel capacity of 25 long tons and a water capacity of 95,000 litres, firing up a 4-cylinder engine that could haul massive loads at up to 130 kilometres per hour. Firing up boilers was a common characteristic of steam locomotives. But not all coal is the same. Big Boy's operator, Union Pacific, owned the mines that supplied the coal that fired the boilers. But it was low-grade bituminous coal, more needed to be burned for the same effect, so Big Boy was fitted with extra-large grates. The sight, sound and smell of the steam locomotive was fundamental to building the 20th century. But as the century wore on, its days were counting down. Cheaper, less labour-intensive and more efficient, the diesel and diesel-electric power plant was taking over.
And so in the 1940s, you saw advances all over the world in the implementation of diesel engines into locomotive traction, signalling the end of the steam era. Probably a lot quicker than many people would have expected, because the steam power was such an important part of everyday life at the time. However, diesel technology and the advances allowed for great savings in the labour that it took to fire up a steam locomotive and operate a steam locomotive, and in speeds and traction effort, and in efficiencies that could be achieved in running trains.
But in some parts of the world, steam still has a place. The earliest of the power plants that we have looked at. It was built in England in 1855. This is living history. This is the Fairy Queen. Producing 97 kilowatts of power and a maximum top speed of 40 kilometres per hour from her 2-cylinder engine, the Fairy Queen was in service hauling troop trains during the uprising of 1857. Which to Indians is the first War of Independence and is known in British history as the Mutiny. By comparison with the mighty Mallard and Big Boy, Fairy Queen carries 2 long tons of coal and 3,000 litres of water. The Fairy Queen continued in regular service into the 20th century, was withdrawn, rediscovered, restored, and now hauls a luxury train regularly between New Delhi and the Rajasthani city of Alwar. These, then, are some of the locomotives that powered the spread of the railways. We look next at how those rail networks, spreading across different parts of the world, powered global change. In Russia, that spread of railways was vital to stitching together the furthest reaches of the largest land empire in the world. In Europe, the spread of railways through the Victorian era required some sort of planning. The timetable was invented, And with the timetable, for the first time, came the need for clocks in different towns and cities to be synchronised. But it was the speed with which railways allowed young countries to develop not just their industrial strength, but their sense of common identity that most powered the growth of Australia, of Canada, and of the United States. Over 250,000 kilometres, the track length of the US rail network is the longest in the world. Perhaps most astonishingly, that comprehensive crisscrossing of the country had been achieved before the end of the 19th century. The last spike ceremony joining the continent from sea to shining sea by rail was driven in 1869. 5 days later, the Continental Express departed New York, and 4 days later, ended a journey that, with frequent changes of horse, had previously taken months. It arrived in San Francisco. In the great age of steam, American coal and wood-fired locomotives, with their pointed cowcatchers or pilots, so familiar from so many Western movies, opened up the States. And many made and many lost large fortunes building railroads. The famous locomotive, the General, is an outstandingly restored example of the type. Built in 1855 and finding fame during the American Civil War as the engine stolen by Union spies endeavouring to cripple the Confederate rail network, the General hauled passengers and freight for the Western and Atlantic Railroad before the war and continued in service into the 1890s. The General and the similarly specified William Crooks remind us today of the pioneering age of American railroads. In its golden age, travel around America by rail inspired a folk culture and countless popular songs romanticizing about the Chattanooga Choo-Choo, the Atchison Topeka and the Santa Fe, Pullman trains and the A-Train.
So people like George Pullman, who developed new ways for people to travel in comfort and style. For goodness sake, the Orient Express and Pullman's amazing series of parlour cars that he built at huge expense, which changed the way we travel and became synonymous with what you would consider to be, oh, I'd love to fly to London business class. Well, that's what people were saying 150 years ago. Oh, I'd love to travel by Pullman.
With the spread of the motor car, the development of highways and the affordability of flying, the railways in America suffered.
Days of the railways are over. Nah, she's all over, mate. Done and dusted. Trains are finished, particularly in America where the oil companies rule sway, and trains are on the nose. They're out of fashion. And the great name trains of America were wound down and ceased to exist.
But by adapting to new markets and new technologies, they have powered back. Across the United States border, Canadian railway engineers had the same ambition, to link their country coast to coast. They faced particular challenges from the landscape and the climate. Historian George Stanley wrote in The Canadians, without railways, there would be and could be no Canada. A fact recognised by the authors of Canada's Constitution Act of 1867, a condition of which was the building of the Intercolonial Railway. But the proposed line, 1,600 kilometres longer than the first US transcontinental, represented an enormous expenditure for a nation of only 3.5 million people. Construction began in 1881, and the last spike was driven on the 7th of November, 1885. The first passenger train left Montreal in June 1886, arriving in British Columbia on the 4th of July. Completion of the railway was one of the great engineering feats of the day. The Canadian Pacific Railroad had a profound effect on the settlement of the West, and new cities, from Winnipeg to Vancouver, were heavily dependent on the railway. Some of the engineering feats that had to be overcome, crossing mountains and traversing Kicking Horse Pass, were extraordinary. Though it is not the Canadian Pacific, but another route in North America, a remote and isolated railway that best expresses the engineering power that has driven railways into almost every part of the planet. The White Pass and Yukon is a route that doesn't link to any other railway. It runs between Skagway in Alaska and the Yukon. Built in 1889 to service the Klondike Gold Rush, the line is testament to the power of railways to transform country and of men to create railways.
The old-timer at the station gives the passengers a send-off on their 110-mile trip. The first 20 miles carries the train 3,000 feet into White Pass, where so many fell and died trying to conquer the mountains and cross over into the gold country.
Considered an impossible task, tens of thousands of men and 450 tons of explosives literally blasted the White Pass and Yukon through coastal mountains in only 26 months, creating a spectacular engineering achievement that climbs more than 900 meters in just 32 miles and features steep grades of up to 3.9 degrees, 2 tunnels, and numerous bridges and trestles. There were very few such obstacles facing those joining the two coasts of another continent. As its name explains, Australia's transcontinental railway joins the Indian and the Pacific Oceans. The Indian Pacific.
In Australia, 80% of our freight is moved by rail. And nothing is more efficient than a steel wheel on an iron road.
The great interior of the island continent of Australia is arid, has poor soil, and is sparsely populated. The coastal margins on the Pacific coast in the east and the Indian Ocean coast on the west house the great majority of the Australian population. For many decades, travel between these two developing centres of population was almost exclusively by sea. And then, they built the railroad. Distance and remoteness, rather than challenging physical obstacles, were the main problems that the builders faced. And it was power that asked one of the most difficult questions. How is a train journey that will take several days to be maintained, fueled, serviced, as it crosses an empty landscape? A landscape so featureless that it crosses a plain called Nullarbor, from the Latin for no trees, and so flat that it has the longest dead straight track in the world, 478 kilometres. When the lines advancing from the east and west were joined in 1917, the answer to the supply requirement was the construction of a number of railway halts, less than settlements, small maintenance depots where tiny isolated communities would exist to maintain the tracks and stockpile the water and fuel that the Indian Pacific needed to complete its journey. The train runs now, linking Sydney and Perth, and is very popular with tourists and those wanting to see the big country. But almost all of the halts are deserted now as the diesel locomotives cross the continent. Almost, but not quite all. In most countries, as railways have spread, engineers have faced challenges.
Progress report on the tunnel under Mont Blanc. It's a two-way task. Here are Italians tunnelling from their side, and a pretty dirty job it looks. They started about 3 years ago and have not yet gone 2 miles into the mountain.
Not everywhere is like the Nullarbor Plain. To allow the locomotives to power across the landscape, bridges and tunnels of often extraordinary ambition have added to the story of rail. Of course, wherever tracks were laid, one fundamental principle had to be understood: how to keep the train on the rails. Whether steam or some other power source, the question, as trains get heavier and faster, is what keeps them on the rails? Train wheels are restricted horizontally by the flange on the inside of the wheel, which bears on the track, keeping the wheel from moving towards the outside of the track. But this flange is not enough to keep a train on the rails. Train wheels aren't perfect cylinders. They're beveled to make them wider on the inside. The wheels are connected by a fixed axle, meaning that the wheels on both sides of the train always turn at the same speed. This can present problems when turning because one wheel has to cover more distance than the other. Most vehicles solve this problem by decoupling the wheels, but unlike conventional automobiles, trains do not have a differential. So how do locomotives stay on a bending rail? What keeps them on track is the conical nature of the wheels, with the outer portion narrower than the inner. The conical edges help in translating angular velocity into different linear velocities. A train that can be as long as 3 kilometres, hammering along at speeds of up to 110 kilometres an hour, creates quite significant problems. One is drag, because drag literally drags down fuel economy. So aerodynamics is important to the operation of freight trains.
So certain ways that you can look at improving drag on intermodal freight trains is to look at how you stack them. So you often see very large gaps in the stacking of these wagons and the loading of them. So if you can optimise that, then it's quite possible to reduce the actual drag and therefore the energy used when you're transporting goods.
Freight trains frequently travelling long distances across exposed landscapes are often exposed to high crosswinds.
Those side forces can cause an interaction between the track and the wheel, and that can lead to increased friction, which then feeds into fuel economy. So it increases the actual frictional load, and that can be very significant if it's not detected.
In heavy winds, it is also not uncommon for containers to be blown off of trains, which can result in damage to the track as well as damage to the goods.
One of the challenges in loading a freight train is that quite often you've got containers of different shape and sizes, and you've also got wagons that carry those containers, and they're often of different shapes and sizes, and you've got to put them all together a little bit like a jigsaw puzzle and come up with a finished product. And sometimes that even involves stacking the containers on top of each other so that the train can be double stacked.
By optimising the layout of the train and spacing, fuel efficiency savings can be as high as 10%. The Hawkesbury River Bridge. North of Sydney, Australia, the Hawkesbury River flows through Broken Bay to the sea. For many decades, passengers travelling north left their trains on one side of the Hawkesbury, crossed the river by paddle steamer and connected with a train waiting on the further shore, an inconvenience replicated in many places around the world. And the reason why so many of the great engineering feats from the 19th century onwards are railway bridges. The bridge across the Hawkesbury is an example. The present bridge, the second, was built to replace the first, which had been built by the Union Bridge Company of New York in 1886. The second bridge was completed in 1946. Its 3 spans, standing on piers, sunk 56 metres into the riverbed, a total length of 890 metres. Significant, but dwarfed by other bridges around the world. The longest structure that carries trains is the Great Belt Link in Denmark. A combination of bridges and tunnel linking islands across a length greater than 6.5 kilometres. The Great Belt Link joins islands. The Channel Tunnel joins countries. There are bridges and tunnels in many parts of the world that cross borders, but the Channel Tunnel is unique. It fulfills a dream that goes back well over a century, of allowing traffic to move between the British Isles and the continent of Europe. The engineering feat involved is prodigious. It has the longest undersea portion of any tunnel. It is the third longest railway tunnel and the longest international tunnel. The pursuit of speed and comfort has transformed rail travel in many parts of the world. Seemingly destined to obsolescence by road and air travel, railways have rebounded strongly with very fast services, and Eurostar is an example of such a service. Taking passengers from the middle of one capital city to the heart of another with speed, comfort and convenience competes more favourably with other options. The Eurostar, formerly the British Rail Class 373 or French TGV TMST, Trans-Manche Supertrain or Cross-Channel Supertrain, run up to 300 kilometres per hour with a top recorded of 334.7, drawing power via pantograph from electric overhead lines and delivering power through sets of powered axles in each car. Each set generating 12 megawatts of traction power and having the lowest power-to-weight ratio in the TGV family of trains. Each Eurostar has a number of special safety features to minimise issues that may arise during the traverse of the tunnel. The braking system, for example, is capable through a combination of disc brakes and rheostatic braking, a form of dynamic braking in which the electrical energy produced by the motors is dissipated as heat by a bank of onboard resistors, bringing the entire train travelling at 300 kilometres per hour to a standstill in 65 seconds. When trains power out of tunnels, there are places in the world where they encounter conditions that could stop them on the tracks, which is why much ingenuity has been applied to the problem of extreme weather. China has built a high-speed railway network which accounts for more than 60% of the world's total. Some of it reaches into exposed and inhospitable landscapes. In Xinjiang, a region with an arid climate, the railway passes through 4 major high-wind areas using a high-speed train based on Japan's Shinkansen that can operate in temperatures as low as -40 degrees Celsius and at altitudes as high as 3,600 meters. Some of the high-speed lines operate in very high wind zones, where crosswinds can prevent trains from operating because of the danger. Trains in such regions monitor the winds and sometimes will stop in sheltered zones and resume operating when the winds die down. But designers are reluctant to allow wind power to interfere with the power of the train.
Part of what we're looking at is the design of the train or the forces that the train is going to experience associated with its geometry. So, how the geometry interacts with the crosswind flow. But also important is, whether there's a requirement for some sort of fence along next to the trains to mitigate the winds, whether the embankment that the train might sit on, how that should be designed to reduce the load and the risk of the train blowing over.
In different countries, less harsh, but still potentially crippling winter conditions are countered by point heaters to prevent points from being frozen, and by landslide snow fences, which in countries like Japan and Canada prevent drifts from falling across the track. Where snow does block the permanent way, other solutions must be found. The rotary snow plough. A Canadian invention, the rotary plough made its first appearance in 1869. Since then, it has been throwing snow off tracks with great efficiency. The rotary plough improved on the wedge plough, the first mechanised device for clearing tracks. When the wedge found the going too tough, the snow too deep, the rotary could push a way through. The rotary snowplow is pushed by one, or conditions requiring it, two locomotives. A motor inside the plough body, originally a steam engine, later diesel or electric engines, rotates the circular assembly. The snow dislodged by the spinning blades is forced back behind the cutting face and out through a channel behind the disc, then thrown through an output chute. The chute is adjustable, an operator behind the blade assembly being able to direct the output left or right and also control the speed of the blade. Expensive to maintain, snow ploughs have now been largely superseded with flexible blade ploughs, pushed by powerful locomotives capable of dealing with all but the most extreme winter conditions. The power to haul the train, the equipment to keep the track clear, the engineering to join countries and continents is all about one thing: the power to travel. A foreign correspondent once complained that flying was not travel. It is, he said, effecting a positional transfer. But every time we board a train, we go on a journey. Steam is at its most romantic in some of the famous trains that steam locomotives have pulled through exotic landscapes, such as the toy train. A legendary 78-kilometre narrow-gauge railway between New Jalpaiguri and Darjeeling, 2,000 metres above it in the Himalayas.
The lower Himalayas in the distance are being revealed, leading up to the township of Darjeeling itself, which unfolds as classic British architecture in parts, and these sweeping views of the mountains. It really is one of the great train journeys of the world.
Between 1879 and 81, the British built the line that is now a UNESCO World Heritage Site. Escaped to the hill stations when the heat of the summer was at its worst, and the suitability of the area for tea growing made construction a viable proposition. The steam locomotives in use, some updated with oil firing, are B-class design and date back to the late 19th century. Diesel engines are also in use. But it is the B-class locomotive, known as the saddle tank loco, that most perfectly captures the romance of the bygone age.
It hits the part of town where the railway is in the main street, on the main road to Darjeeling. And so the train is rattling along with two guys sitting on the front of the locomotive with red flags, telling people to get out of the way. And there's all sorts of negotiating of the train with traffic and passengers and pedestrians in a way that only India can do.
Where other locomotives we have considered carried many long tons of coal, the engine of the toy train weighed only 14 long tons. But they were far from fragile, and two, Tusker and Victor, are still shuttling up and down the mountain. The UNESCO-listed Kalka-Shimla railway line ran up to the British Hill station north of Delhi. Because it was the seat of government during the entire hot Delhi summer, Shimla was very important to the British, and so was the little train.
Interestingly, the railway's very, very popular today. It's one of those sort of honeymoon destinations. So the train is often full of honeymooners and young lovers. The scenery is astounding, and the engineering and the different climate zones that the railway travels through as it rises all the way up to more than 2,000 metres.
But engineering the line was not without its challenges. More than 400 bridges, all stone-lined, wonderful multiple arched aqueducts and more than 90 tunnels stand today. A testament to extraordinary engineering skills. Getting up and down mountains has posed an engineering problem in many parts of the world, where friction, traction and gravity have not always worked together.
Because it's steel on steel, trains are much more limited to the angles that they can climb up and down. And that's just because steel on steel has got a much lower friction than rubber on a road.
Various systems have been invented for keeping the train on the tracks, including the sophisticated rack and pinion system on Swiss railways. The rack, the central toothed rail with an appearance similar to that of teeth on a gear wheel, is engaged on steep inclines, typically 7 to 10 degrees, by lowering the train's pinion, a gear wheel lowered from the locomotive when the gradient requires it. With rack and pinion mesh, it prevents the train from slipping on the rails. There are a number of different designs for both rack and pinion, but the principle is constant. Teeth engaging from a pinion on the locomotive onto the fixed rack rail.
The ratcheting systems are just a way of overcoming the metal on metal. So you've got a set of cogs, and the cogs are what provides you the forward momentum, rather than the metal sliding on metal.
There are rack and pinion railways around the world, in addition to the many operating in Switzerland. Three times a week, a train pulls out of the main station of Chongqing, southwest China, on one of the longest journeys in the world. 11,179 kilometres through 5 countries to Duisburg in the west of Germany. The trains, which are 2 kilometres long, reach Germany in just 13 days, reviving ancient trade routes with modern efficiency. Most of the cargo on the trains, with up to 50 40-foot containers, comprises laptop computers, of which Chongqing is the world's largest producer, with 25% of global output. This is the New Silk Road, named after the route in the 2nd century BC that took Chinese goods to the Middle East and Europe. If ever the journey is opened up to passenger traffic, it will surely be one of the great travel experiences. Around the world, there is strong competition in the growing market for train travel experiences. The luxury train that bisects Australia, north to south, offers insight into both a dramatic landscape and a unique culture. The Afghan Express, as it was originally called, the GAN, was named to honour a particular group who played a major part in opening up the interior of Australia.
The interior of Australia was dependent upon camel trains. These camel trains, using camels, imported from Afghanistan mainly, were driven by and led by people from Afghanistan. So when the train became a reality, it was named the GAN in honour of the Afghan camel drivers who had been the only means of transport for a lot of the inland areas of Australia.
The GAN links the southern city of Adelaide to the tropical northern city of Darwin. A journey of almost 3,000 kilometres through the red centre of Australia and the iconic Central Australian city of Alice Springs. The Alice was originally the northern terminus of the route, which was initiated in 1929. The line was not extended to Darwin until 2004. Diesel-powered, the GAN pulls 30 carriages at a quite leisurely pace.
The track now, from Adelaide to Darwin, is almost 3,000 kilometres. Clearly though, if it takes 54 hours, they're not travelling at huge speeds.
The train averages 85 kilometres per hour and takes 54 hours to complete the journey, and it weighs 1,400 tonnes. Passengers get to enjoy the view, the food, and the odd stop along the way. A train travels through Mauritania in Western Africa, fringing the Western Sahara. It has some similarity to the GAN, crossing an arid, sparsely populated landscape. But the contrasts are great. Like the Silk Road trains from Chongqing, the train in Mauritania carries chiefly freight. It carries iron ore, and with between 200 and 210 cars of 84 tonnes of ore each, they are among the longest and heaviest trains in the world. As mineral resources of the region are further developed, more and possibly bigger trains are going to travel the 704-kilometre line. Hauling the cargo takes 3 and often 4 locomotives capable of operating in the region's searing heat.
So trains might often need 6 engines just so that they can get the train and the rest of the carriages up to the speed required, and also more importantly to make sure that they can stop. More often than not, it'll probably be the stopping requirements of the train that drive the number of carriages. Just because once the train is moving, it's got a certain amount of inertia. You need to be able to put enough power into the braking system such that you can stop the train and overcome the inertia.
The SD70 ACS engine is used, as it is in similar parts of the world, including the Arabian Peninsula. The American company EMD, Electromotive Diesel, manufactures the equipment with a diesel-electric power plant producing 3,400 kilowatts. Variants operate the longest ore trains. Between the iron ore ranges of Western Australia and the port facilities, where the record was set by a train that stretched well over 7 kilometres, had a gross weight of almost 100,000 and was pulled by 8 locomotives. Now that is power. Railways delivered the power to move people, freight, armies, raw materials, the power to move huge loads, and the technology to be fast. In this episode of Power, we investigate the high-speed trains that link cities, the futuristic visions of magnetic levitation and pods, and tell the story of engineering marvels from the longest train to the miniature wonderland. This is the story of rail power. Speed. Almost 200 years since trains became familiar intruders on almost every landscape, the sight and sound of steam has become a romantic memory. Replaced by more efficient, more powerful, more reliable, less polluting forms of power. Replaced above all, in the name of speed. This is the Shinkansen, the bullet train. Not quite faster than a speeding bullet, the Shinkansen redefined intercity rail travel for the modern age. Shinkansen is actually the name of the rail network across which the high-speed trains travel.
They decided to build a completely separate railway, and the word Shinkansen means new trunk line. giving you the idea that it's a separate railway altogether.
A network that revolutionised domestic travel in Japan and set the standard for high-speed rail travel in the second half of the 20th century.
More passengers travel by train in Japan than anywhere else in the world. Sells more tickets, about 1 billion tickets a year.
The first bullet trains began their journeys in 1964, linking Tokyo and Osaka. This line, the Tokaido Shinkansen, remains the busiest fast train line in the world. Over the years, a number of different train sets have entered service. The technology has evolved, as has the design. Aerodynamically refined in wind tunnel testing. The current Shinkansen have a maximum operating speed of 320 kilometres per hour, though they could go faster.
Another key challenge with high-speed train aerodynamics is how trains interact when they're passing one another, and also how they enter into tunnels. So the nose shape on trains can be very different, and it depends on how they're going to be used and the environment they're going to be used, because there's a range of aerodynamic effects that are really important in the design of the train. So if you look at some of the trains around the world, some of them seem quite blunt and some of them are more streamlined, like a ICE3, and then others almost have a duckbill type shape, and that's got to do with the environment that they're going to be operating in.
All Shinkansen are electric multiple units, with the most striking of current designs being the H5, the latest of the 700 series that features the duck-billed nose, an aerodynamic shape which reduced the piston effect, the force of air displaced as the train surges into tunnels.
So when a train enters into a tunnel, it can create a very high pressure wave, and that can cause all sorts of problems, and that pressure wave can also propagate down through the tunnel. So some trains are actually designed to limit or reduce that pressure wave. So when you see duck-billed type trains, it's designed for that purpose.
Aboard these trains, 3 classes of comfort speed passengers to their destinations. Grand Class, Green Car, which is the equivalent of business class, and Ordinary Class. Like almost all Shinkansen, the H5 draws power from overhead wires by means of a pantograph. In the context of railway operation, a pantograph is a device for collecting electrical current. The power supply is carried in overhead wires, and contact with the pantograph's metallized carbon strips draws power to the unit's drive system. For low-speed vehicles, trams, slow trains, trolleybuses, the pantograph uses springs and air. Air pushes the cylinder, which raises the pantograph into position. Springs then maintain contact with the wire. For high-speed units, such as the Shinkansen trains, springs are not efficient, and contact is maintained through a pressurized air system that holds the contact in place through constant force. From the 1960s onwards, the very fast train concept has developed on intercity routes in most parts of the world. But it is a very different type of power source that drives the train that holds the record for speed. That record belongs to a train that does not travel on rails. In fact, it doesn't travel on anything. This is the maglev. Maglev, magnetic levitation, uses the principle of magnetic attraction to both lift and propel the trains. Lift removes friction, maintenance is reduced, wheels are not worn out, and speeds can be tremendous. The record stands at over 600 kilometres per hour.
Japan has been developing a magnetic levitation railway for a number of decades now. And interestingly, there is a test track that you can go to see the train rip by once a day at close to 600 kilometres an hour.
There are regular maglev lines in China, Japan and South Korea, with others in development. A maglev system depends on 2 technologies, the power supply and the suspension. In some systems, a single technology provides both levitation and propulsion. electromagnets powering an onboard linear motor. But other systems levitate the suspension system but do not propel. EDS, or electrodynamic systems, use superconducting electromagnets, or strong permanent magnets, to create a magnetic field, which induces currents in metallic conductors to push and pull the train towards its designed levitation position. Such systems require a separate propulsion source. Some EMS, or electromagnetic systems, can both power and levitate. Onboard magnetic fields interact with metallic loops set into the walls of the maglev guideway. The loops are made of conductive materials, and when a magnetic field moves past, it creates an electric current that generates another magnetic field. Different types of loops perform three important tasks. One type creates a field that makes the train hover about 12 centimetres above the guideway. A second keeps the train stable horizontally. The third is a propulsion system run by alternating current power, where both magnetic attraction and repulsion are used to move the train car along the guideway.
Principle of magnetism. Everyone's played with magnets, and they know that if you put the North Pole and the South Pole together, they attract each other. And if you turn them around and you try and put the North Pole and North Pole together, you can't. They push each other apart. And so they use that principle, except they use electromagnets to cause the train to be held in the air.
The concept of the magnet design means that the only source of friction is air, and the result is a smooth trip at any speed. Unlike other attempts at evolving high-speed rail transport, experiments with power systems that have been abandoned. Trains run on rails, that's why they're called railways. But inventors have been attracted by the idea that trains encountering no friction would be efficient, fast, and quiet. We have seen that the maglev effectively suspends the train above the track, keeping it there through magnetic attraction. Hover trains used a similar principle, suspending the train so that the only resistance it meets is movement through air. Instead of magnets, hover trains employed the cushion of air concept that was developed for and is still the basis of hovercraft. The RTV, Research Test Vehicle 31, was a British experimental train. Work started in the 1960s and accelerated when the hovercraft principle was married to a second British invention, the linear motor. Eric Laithwaite began developing the linear induction motor, LIM, in the late 1950s. LIMs provide traction through the interaction of magnetic fields on the vehicle and a fixed external conductor. Such a motor eliminates the need for physical contact with the track, has no moving parts, and so lends itself to the hovercraft concept. In Laithwaite's original design, two sets of windings positioned a few centimetres apart were positioned so that an aluminium stator plate would fit the gap between the windings, the forces pulling one set of windings towards the plate and thus balanced by the opposite forces in the other set. The hover principle ideally requires a smooth surface so that the cushion of air contained by the skirt has minimum leakage. The hover train was designed to run on a concrete track, and a development track was built early in the 1970s. In 1973, RTV-31, the first vehicle to test all of the innovations, made its first run. The train travelled at 167 kilometres per hour over the 1 mile, 1.5 kilometre track with great publicity. But meanwhile, development had been progressing on the advanced passenger train for intercity transport. Arguments about cost, speed and efficiency went back and forth, but in the end, the hover train project was cancelled and the APT system was adopted.
Now nearing the final stages of its development, the French Aero train will be a considerable boon to intercity commuters when it's brought into service.
The Aero train, France's rival to the British hover train, used a similar principle, but like the RTV-31, was mothballed by the government in favour of a fast train that travelled on rails in France, the TGV. Before its cancellation, a number of test trains had been built with different power plants. Several of them were large enough to take passengers. The Aerotrain 02 was powered by a Pratt & Whitney turbojet, the S44, a full-size passenger-carrying car intended for suburban commuter service was equipped with a linear induction motor. And the Aerotrain I-80 was a full-size passenger-carrying car for intercity service. The growth of railways to their present status as mass transit transport systems in every part of the world did not, of course, rely on these exotic experiments. Everywhere, the workhorse for passenger and freight has been the diesel or diesel-electric locomotive. Despite their names, diesel trains are not driven by the power of their diesel engines. They are driven by electricity. The diesel engines power the shaft that drives the generator that powers the large electric or traction motors that turn the wheels.
The diesel engine does not produce mechanical motion directly to create the motion of your locomotive vehicles, but it's used to generate electricity, and then electricity is used to run the AC motor, then you go forward. Diesel engine can be optimized at a fixed engine speed and fixed operating condition. That's how you get the best efficiency.
Typical of the most powerful of the diesels is the AC6000CW, generating 4,500 kilowatts or 6,000 horsepower. The only units that produce more power are dual engine designs. These are the great machines that haul the huge loads. The ore trains massive freight loads. The versatility of the power source means that the power spectrum is wide. The first regularly operating diesel locomotive produced 883 kilowatts of power. The robustness of the diesel and its fuel efficiency compared to the standard internal combustion engine explains its ascendancy in railway, marine, and heavy road applications. But there are drawbacks. The cost and availability of the fuel, the need for regular maintenance, the environmental issues of noise and smell. Where the pros and cons have been weighed, many operators have preferred systems that deliver electricity direct to the train's motors without the need for diesel generation. As with the Shinkansen, this means connecting the train to a live supply, either by an overhead wire or a live rail. The first electric train was demonstrated in Berlin late in the 19th century. It achieved a top speed of 13 kilometres an hour. The technology has advanced since then, and power is now produced in abundance. The power is generated not on board through a diesel engine, but by plugging the railway into the national electricity supply. The Shinkansen, the TGV in France, the Eurostar that links Great Britain to the continent of Europe are some of the high-speed types of train that derive their power directly from a live source. France's TGV, Très Grande Vitesse, or very high speed, is a typical electric train.
They're fast. The track is built with that train in mind. So the track has to be long radius curves and not rough, but a smooth track. I think the engineering innovation is the design of the whole system to be reliable, to be fast and to be safe at the same time. So that was a rethink of railway technology.
Sleek, streamlined, some even with the duckbill that was first seen on the Shinkansen. The TGV network links every part of France and France with its neighbours. The service was initiated in the early 1970s, and the original concept was for gas turbine power. The oil price crisis of the period put paid to that. Electric traction became the power of choice, And though the look of the locomotives and their performance has progressed since the service was initiated in 1981, the basic principles that get the power to the wheels have not. The TGV's traction components include the pantograph, which maintains contact wire pressure at about 70 N. The main transformer, which converts 25 kilovolts, 50 hertz single-phase overhead power into 1500 volts, 50 hertz, and a number of parts that deliver this power to the traction motors. Thyristor-controlled rectifier bridges, the common block consisting of DC circuit breakers and the main filter capacitor, traction inverters that convert DC into a three-phase, variable frequency AC waveform combined to get usable power to the AC traction motors, which on the TGV are slung from the vehicle body, substantially reducing the mass of the truck, giving it exceptional tracking stability. Each motor can develop 1,100 kilowatts and can spin at a maximum rate of 4,000 RPM. This power arrangement has enabled the TGV to set the world speed record for conventional trains. Line voltage had been boosted to 31 kilovolts and extra ballast tampered onto the right-of-way when on April 3, 2007, a modified TGV reached 574.8 kilometres per hour. Elsewhere in Europe, another very fast train, the ICE, Intercity Express of German railways, has, like other trains in the category, a distinctive nose shape to deal with the power it has as it pushes through the air.
You know, one of the challenges that we're looking at, in particular with the ICE3, is the slipstream effect of the train. So the ICE3 is just one example of a train where which is travelling at high speeds, and we need to understand how that train is going to induce flow behind it and how that flow is going to impact on surrounding infrastructure, for example. So the shape of the nose, which in the ICE3's case is also the shape of the tail, has a large effect on the flow that's induced. So we see a large downwash occurring, and that's associated with flow over the back of the train. And we can actually see large vortices, which are a little bit like tornadoes, if you like, on a different axis. And those vortices actually move around within the wake, and they can impact on different objects or on people as the platform goes through. So if you're looking directly behind the train, you have a vertical component of the velocity, so you have a downflow, and then you have that interacting with flows coming around the side of the train at the rear. And the way that they interact can be such as to introduce vortices. So you have the flow coming down through the middle of the train, and then you have a large rotation, and you get two vortices that a little bit like angled tornadoes originating from the rear surface of the train, and then they can move relative to one another, and they cause a lot of drag. They're associated with low pressure regions, and when you've got low pressure on the back of something, it's acting like suction, so it's pulling it back. And they're not dissimilar in nature to the vortices that you see behind a plane.
Other trains draw their electricity not from overhead wires, but from live rails. Perhaps the most famous of these travels beneath the streets of a city, the London Underground. When trains first started to run through tunnels beneath London, it was 1863, and power came from steam engines. The network, which continues to evolve, now covers more than 400 kilometres and carries almost 1.5 billion passengers a year, serving 270 stations and travelling at an average speed of 33 kilometres per hour. The first electric trains ran in 1890. And since the early 1960s, all London Underground trains have been electric multiple units, self-propelled carriages using electricity as the power source. A contact shoe beneath the rolling stock draws power from the live rail, which is the power source throughout the network. The onboard plant translates the delivered 750 volts of direct current and produces the power that drives the traction motors. The London Underground. known to all Londoners as the Tube, is the oldest underground system in the world. But the Seoul Metropolitan Area system in South Korea holds the record for route length at over 900 kilometres. The New York subway serves the most stations, 468. The busiest is the Tokyo Metro, with 3.3 billion passenger journeys each year. With its Art Nouveau stations, Paris may be the most decorative. And famously, the decor of many stations on the Moscow subway is of extravagant opulence. The technology is in place on many established lines, including the London Tube, for driverless trains. That future is already the norm in the Persian Gulf. The Dubai driverless metro opened in 2009. It covers less than 75 kilometres, serving 49 stations, with further expansion planned. What places it firmly at the forefront of technology is the fact that it is fully automated. Its trains are driverless.
The main thing it's known for is that it doesn't need drivers, and that's an increasing trend with new train systems. It's quite a comprehensive system running the length of Dubai.
Power is drawn, as with far older rapid transit systems, from a live third rail, delivering 750 volts of DC, powering trains on the Red Line at up to 47 and the Green Line at up to 38 kilometres per hour.
It's about 75 kilometres of track, and they're increasing that. It started operating in 2009. It's not an unusual type of metro system. A lot of it's elevated. I was there watching it being built for a while. One thing that's a little different to some of the other systems is that its power supply, it's obviously electric, is from a third rail and not from an overhead catenary. The problem with that is that you need to have a secure right-of-way so that people don't get in contact with the electrical circuits. The alternative is overhead catenary that uses a pantograph on top of the train to pick up, and that's certainly the system we see more of in most countries.
The power to move people in rapid urban transit has not always forced trains beneath the ground. Elevated trains may travel on raised rails, like Chicago's L. Maybe monorail designs from Disneyland and Tokyo to the Bangkok SkyTrain. Or they may be hanging trains.
Interestingly, railways don't have to be terrestrial in nature all the time. There are a collection of very interesting suspended railways where the carriages are actually hanging from an overhead rail.
The Wuppertal-Schwebebahn. The Wuppertal-Schwebebahn has suspended cars reaching speeds up to 60 kilometres per hour on a line running more than 13 kilometres above the streets of Wuppertal since 1901. The cars are suspended from a single rail built underneath a supporting steel frame with 486 pillars and bridgework sections. Each car hangs on wheels which are driven by multiple electric motors operating at 600 to 750 volts of direct current supplied through the conductor rail. The onboard power supply drives 4 direct current medium voltage motors per articulated train. Special trains have always had a special place in the affections of people. The Wuppertal-Schwebebahn is fondly known as the Old Girl. Trains associated with long, exotic journeys and spectacular luxury have a particular hold on the imagination. The extraordinary, futuristic and very expensive Shikishima is not a train to anywhere. It is exclusively a vehicle for taking short tours in northern Japan. a golden piece of modern design with Michelin menus, all suite accommodation and wonderful observation cars, this vision of tomorrow rides on a rather traditional diesel-electric power plant with a top speed of 100 kilometres per hour.
Japan's very interesting because there are this new breed of luxury trains, the Shigashima, which is ultra-luxury. Michelin chefs on board, beautiful state-of-the-art decoration, comfort, the technology underneath, the running gear, the spring systems under the carriages, ultra smooth, and you never hear clickety-clack anymore and things like that. You've got welded rail for a start. But the appointments inside these trains is something superb. But it's also the uniqueness, I guess the thrill of running on something that's a bit exclusive, something a bit special. Because luxury trains have always been the preserve of the ultra-rich.
The Indian Palace on Wheels is also a train dedicated to tourism. One of the luxury trains making journeys around the subcontinent, it takes its cue from the decorative traditions of princely India, the distant days of Maharajas and the British Raj. The Orient Express, a legendary name in train travel, is a luxury destination in its own right. In its heyday, linking Paris and Istanbul, the Orient Express was a powerful train that carried powerful people, heads of state, and every sort of celebrity for every sort of success and scandal. And in Agatha Christie's famous story, murder mystery.
Earlier 19th century, in order to realise a market that was there for the wealthy, but also to attract the middle classes to train travel. So the rise of trains like the Orient Express in the 1880s, essentially a very smart business plan to provide comfort and a quality accommodation on a train that you didn't have to change. So it was a matter of doing deals along the way with different governments across different borders to create one train heading across multiple borders.
Equally exotic, but a train with a real and vital communications role in joining the extremes of the world's largest nation, is Russia's Trans-Siberian Railway. The vastness of Russia can be understood by realizing that if Siberia was an independent country, it would be the largest country in the world. The Trans-Siberian, really a network of railway lines that link Moscow to Russia's Far East, is a journey of more than 9,000 kilometres, the longest railway line in the world. Building the line began in the 1890s and was completed in 1916, the year before the Russian Revolution.
Russia, interestingly, has a unique developmental railway story where the Tsar decided that he would have a different gauge when it came to the construction of railways on a large scale in that country, and randomly came up with 5 foot as a broad gauge, unique to his system. The Tsar broad gauge, it's referred to. And that, even though it caused all sorts of problems when it comes to transshipping at the borders with Poland and with China, ultimately, when the Trans-Siberian Railway got that far, it did create all sorts of bottlenecks when it came to the First World War and the Second World War. So it did do its job in helping to protect borders.
The Trans-Siberian is no tourist novelty. It continues to be the most important railway line in Russia. 30% of the country's exports travel on the line, and its connection to the Trans-Mongolian makes it an important outlet for Chinese exports to Europe. About 200,000 freight containers a year reach Europe on the Trans-Siberian. The fastest train on the route, which was fully electrified in 2002, takes just over 6 days to link Moscow to the Pacific Ocean. an average speed of 64 kilometres per hour across 5 time zones. After the Russo-Japanese War of 1905, in which inadequate railways meant the failure to reinforce the Far East, the Trans-Siberian received heavy investment, which paid off in the Second World War, when moving the Siberian Reserve to meet the German invasion was crucial to the Soviet Union's survival.
Here are 3 of many good reasons why there'll be a warm reception for the Nazis if they try an invasion.
Almost since the first train pulled the first wagon, trains have been part of military planning and military weapons.
It was the 1850s that also saw the first use of trains extensively in war, something that was to become a major theme for the next 100 years. Troops were brought to the front en masse by train in the Crimea War, helping to create one of those interesting things that we saw a lot of in the late 19th century and certainly through the 20th century, the stalemate of war, trench warfare, and the use of heavy artillery that could be brought to the front pretty quickly by train, creating massive war front and huge loss of life, of course. The American Civil War, effective use of trains.
During the American Civil War, volunteers from the Union Army commandeered a train and took it north. As they went, doing as much damage as possible to the vital rail line from Atlanta to Chattanooga. They were pursued by the Confederate forces at first on foot and later on a succession of locomotives. The event was reproduced in one of the great achievements of silent cinema, Buster Keaton's 1926 film, named for the featured locomotive, the General. Since that event in 1862, trains have often played a role in the massing of armies, their supply and support, and the carriage of heavy weapons. In the Second World War, with industry in America from coast to coast gearing up to be, in President Roosevelt's words, the arsenal of democracy, it was the railways that were vital to moving war materials and personnel to the ports, and so to the battlefields.
Then, railways allowed troops to be delivered to the front, like a sausage factory, continually.
And it was railways that made possible the carriage and the use of the largest caliber rifled gun ever used in combat, Schwerer Gustav, Heavy Gustav. Originally designed to take on the fortified French Maginot Line.
You had some very interesting technologies developed specifically using railways. The massive rail-mounted armoured guns and cannons, which were as big as anything on a battleship, if not bigger, where they would fire 14-inch, 16-inch shells, I believe, as far as miles into the battle zone from track-mounted guns, recoiling great distances down the line as they fired these extraordinary salvos, much bigger than anything could be managed on conventional land arrangements.
Also produced by Krupp's was the slightly smaller but far more practical K5, which could fire a 255 kilogram shell 64 kilometers at the rate of 15 rounds an hour. "25 of the guns were produced and they were used in France and in Italy. The limitation in sighting the gun was that its effective aim could only be achieved vertically, limiting the gun to targets in line. To track targets on a horizontal axis, either a curved length of railway was used with the gun shunted backwards or forwards to aim, or for 360-degree traverse, a turntable could be constructed, consisting of a raised rail section, the firing bed, which carried the gun, running on a circular track. It was the K5 that formed the basis for the M65 atomic cannon. Developed in the USA after the war and nicknamed Atomic Annie, Although based on a railroad gun, Atomic Annie was towed by special tractors and was capable of firing a nuclear shell.
So the M65, the Atomic Annie, or the atomic cannon, was very much a product of its time. This weapon was designed to be used by land forces to fire a small nuclear round, bomb, at enemy land forces and create what you'd call the nuclear battlefield. This is quite an enormous weapon. Its caliber is, I believe it was 280 millimeters, which is the equivalent of an 11-inch gun. And its origins would have been from some of those very heavy artillery pieces that existed in the First World War and in the Second World War. And weapons of that size were originally mounted on railway carriages because that was the only thing that was strong enough to pull them around.
In military use, trains have not only been valued as a means of transporting weapons and manpower, they have been used for speed.
One of the uses of a high-speed rail track is to test the flight characteristics of a guided missile submunition. So in the very early developmental stages, they'll run a new missile down the test track. At the end of its travel, they can stop the sled dead, which will release the missile going forwards, and then allow it to impact with a target, and that way you can simulate in a very closed environment the impact of the missile with a target array.
The 846th Test Squadron of the US Air Force broke the world speed record for a vehicle travelling by magnetic levitation on a test track in Otero County, New Mexico, when a rocket-powered maglev sled reached a top speed of almost 1,020 kilometers per hour. The Air Force used superconducting magnets to move the sled without it touching the ground. The maglev system is the most recent rocket sled, and its speed record surpasses that of the sled that powered by 9 solid fuel rockets with 40,000 pounds of total thrust for 5 seconds that accelerated Colonel John Stapp of the US Air Force to a speed of 1,017 kilometers per hour at an Air Force base in New Mexico on December 10, 1954. Stapp, who was known as the fastest man on Earth, was not concerned with how fast a man could go, but what would happen to a man subjected to major G-forces on rapid acceleration. And he demonstrated that a human being can withstand 46 G.
Colonel Stapp, the fastest man on Earth.
From the start, the appeal of railways has been their ability to move large loads over long distances. Power has been decisive in determining how large the load, how far the distance. In one great and barren part of the world, where distances are vast and loads enormous, the train is king.
The task for a heavy haul railway is the same the world over. You want the cheapest method of getting from mine to port. One way of doing that is to have the optimum number of locomotives and the optimum number of wagons with as much as you could possibly fit in, which comes down to how well your track is constructed for how much you can actually put per train.
In Western Australia, there are mountain ranges made of iron ore. The job of getting the ore from the mines to the ports is work for the longest and heaviest trains anywhere.
A long iron ore train, fully loaded, will take several kilometres to stop. It will stop quicker if it's on an uphill grade, and it will take longer if it's on a downhill grade. These are the simple Newtonian laws, and they apply to iron ore trains as well as everything else. So you need a really good braking system, and you need very powerful locomotives to get you up the grades. And it isn't a solely downhill run from mine to port. There are some uphill grades as well.
In the Pilbara region, ore trains typically approach 240 cars, or around 30,000 tonnes. The standard for Rio Tinto operations is 29,500 tonnes of iron ore, carried in a train 2.4 kilometres long, hauled by 3 locomotives. A BHP Billiton ore train has typically 268 cars and a train weight of 43,000 tonnes, carrying 24,200 tonnes of iron ore.
The skill in driving a fully loaded iron ore train is considerable, because if you accelerate or decelerate incorrectly, you could break the train. So if you're imagining you're going over a hump, you have to be careful that you don't put so much tension between the couplings of the wagons that could actually cause the train to break in two. So it's very difficult to drive such a train.
The record was set on the 21st of June 2001, when a train comprising 682 wagons with a total length of 7.352 kilometres, hauled by 8 6,000 horsepower General Electric AC 6000 CW diesel electric locomotives and controlled by a single driver, travelled the 275 line to Port Hedland in Western Australia. Each AC 6000 CW 6000 horsepower, 4,500 kilowatt loco was powered by a V16 twin turbocharged engine. There is a spectrum in train travel, and here is the opposite end of it from the ore-carrying behemoths. This is Miniature Wonderland in Hamburg, Germany, the world's largest display of model railways. Construction began in 2000 and is set to continue into the future. The present scale of the operation is remarkable. More than 7,000 square metres of floor space house an exhibit that boasts almost 15,500 metres of track, along which more than 1,000 trains run through 1,300 signals, in a world populated by about 265,000 figures. The exhibit suffers the theft of about 3,500 every year. So far, building Miniature Wonderland has cost about 20 million euros and employs some 270 people. Included in the landscape is the world's largest model airport, an advanced automated system to move cars around the layout, and a control system operating through 50 computers. There is something fantastic about the world of the Miniature Wonderland. But there are even more fantastic, futuristic plans on the drawing board for train travel into the future. And the most futuristic thing about many of the designs is the power source that they will use. The Hyperloop concept, in an advanced stage for Dubai and proposed as a high-speed link between cities such as New York and Washington, promises to revolutionise not just the speed, but the way in which we travel by train. The Hyperloop concept operates by sending specially designed capsules or pods through a steel tube maintained in a partial vacuum.
One approach to ground transport in the future that's being considered is if you can have trains effectively or capsules operate in a vacuum, then you've removed the aerodynamic problem. Now, this is a really long way off, but if it was to work, that aerodynamics wouldn't be a problem, so you could achieve extremely high speeds.
The first thing to imagine afresh is the railway station. Pods constantly shuttle into and out of terminals, and passengers step on and on arrival step off the moving car. Each car with perhaps a capacity of 6 to 8 passengers. The original concept for the look came from Elon Musk, whose design envisages each capsule floating on a 0.5 to 1.3 millimetre layer of air provided under pressure. This thin layer provides a more achievable and more practical tubular concept than the original vacuum tube from which it has evolved. The vacuum tube, offering zero air resistance, could accommodate theoretical speeds of thousands of kilometres an hour. The thin layer buoys the pods while still allowing for speeds that wheels cannot sustain. Linear induction motors located along the tube accelerate and decelerate each capsule, with rolling resistance eliminated and air resistance greatly reduced. The capsules effectively glide for the bulk of the journey.
You remove the air, so you're removing the aerodynamic force, and so it's like travelling in space. Effectively, that's what you're trying to do. Create a little tunnel, space tunnel, but you don't have aerodynamic drag. Which is why you can travel so fast in space without having so many problems. Because if you were to travel at those sort of speeds that space shuttles travel at through the atmosphere, you would generate enormous amounts of heat.
The original Hyperloop concept placed an inlet fan at the nose of the capsule to transfer high-pressure air building at the front of the vehicle. Pods are projected to reach a top speed of 1,220 kilometres an hour, meaning that the journey from New York to Washington would be accomplished in just under half an hour. The story of power on the rails started with the search for a smooth journey and reduced friction. It continued with streamlining and improved ways of producing power, and with the Hyperloop, it reaches the points of almost eliminating friction, getting rid of rails and generating enormous speed, but requiring the expenditure of very little power. Podcars, PRTs, or personal rapid transport systems and hover trains are on drawing boards and in some cases exist and are being tested in various parts of the world. In some places, typically airports like London's Heathrow, PRTs are already an important part of the transport infrastructure, as podcars shuttle passengers between terminals, from terminals to public transport of car parking hubs. Designs that not long ago belonged in the realms of science fiction are now carrying paying passengers, and the power of the railway, transformed though it might be, shows no signs of diminishing.